Okay, we shall start. So good day, everyone. I'm Chen from Nanyang Technological University, Singapore. The title of our workshop is Mobile Intelligent Photography and Imaging. It's a full-day workshop. So first of all, on behalf of the organizing committee, I warmly welcome all of you who attend the workshop today. I also wish to thank the organizing team, especially Chong Yi, who has diligently organized the workshop. And our workshop would not be as successful without the generous support from our sponsors, the Shanghai AI Lab, Sony, and Nanyang Technological University. And the central theme of our workshop is mobile intelligent photography and imaging. Mobile photography has massively harnessed machine learning over the years. It is used for tasks like noise reduction, object shadow reflection removal, reducing video jitter, and more. And this is clearly going to remain one of the biggest focus areas for smartphone brands and chip makers, as well as researchers in computational photography, alike in the next few years. So there are plenty of innovations coming in the field. And the main reason for organizing this workshop is to promote the research on these topics. We focus not only on developing various deep neural networks, but designing new AI models for mobile devices, considering new sensors, and their efficiency for real-world applications. And to promote the research in such specific areas, we have been discussing closely with industries to identify some open problems. And the discussion leads to 5 challenge tracks this year. And to facilitate the challenge, we released more than 22,000 pairs of data. And the challenge attracted over 40 submissions. And from these submissions, we awarded over $11,000 to the top 3 entries in each challenge. And apart from a challenge, we accepted 8 workshop papers of excellent quality. And we also invited 4 renowned researchers to give a keynote. And we are very proud to have Peyman, Tomo, Michael, and Mohit, who will share their latest research and the development in the field. And Peyman will give us the first keynote. And welcome. Is already close to midnight at California, and we really appreciate his effort and support to this workshop. Apart from the keynote talks, we also invited the winners of each challenge track to share their winning solutions. So there are 5 tracks altogether. The first track is RGB plus TOF depth completion. And the second one is quad joint remosaic and denoise. And the third one is RGBW joint remosaic and denoise. And the fourth one is RGBW joint fusion and denoise. And the last one is image restoration for under display camera. So these are the winners for each of the track. So these are the winners for the first track. And we will invite the champion to give a talk later. And this is the winners for second track, the third track, the fourth one, and the final one. And from the workshop papers submissions, the committee has selected the best paper and the best paper honorable mention. The best paper goes to event-based image deblurring with dynamic motion awareness from Huawei Technologies Zurich Research Center. Dr. Patricia Vitoria will give us a talk later. And the best paper honorable mention goes to continuous spectral reconstruction from RGB images via implicit neural representation. So Mr. Ruikang, he will introduce his work later. And this is the schedule of workshop in Israel time. So after the opening later, we will have the keynote by Peyman, and then followed by the presentation from the best paper award for the best paper and the best paper honorable mention. We have our schedule till 11:10, then we have a tea break. Then after the tea break, we'll follow by a series of talks from our challenge winners and invited talks. And then we have a lunch break at 12:30. And after the lunch break, then we will continue with other talks and 3 more keynotes. And the workshop is going to close at 5:20. So it's a full day workshop. So if you want to check the full schedule, then you can click the link here and you can see the latest schedule. So, okay, let's start the first keynote. Before we start, I would like to introduce Dr. Peyman Milanfar. So the title of his talk is Denoising as a Building Block for Imaging Inverse Problems and Machine Learning. Now, Dr. Peyman Milanfar is the principal scientist and director of Google Research, where he leads the computational imaging team. And prior to this, he was the professor of electrical engineering at University of California, Santa Cruz from 1919 to 2014. And he was the associate dean for research at the School of Engineering from 2010 to 2012. And he was on leave at Google X from 2012 to 2014, where he helped to develop the imaging pipeline for Google Glass. So I still keep the Google Glass that I bought, the first Google Glass. And I'm huge fans of Google Glass. And his team at Google developed the digital zoom pipeline for Pixel phones, which includes the multi-frame super resolution, super res zoom technology, and the Razor upscaling algorithm. And in addition to that, in the light side mode, our Pixel 3 uses the super res technology as well. So without further ado, so let me invite Dr. Peyman Milanfar to give his keynote.
Great, thank you very much. All right, just one second. Let me make sure I can share my screen. Can you see my screen?
Yep.
Okay, so let me go to full screen here. And turn on the laser pointer. Okay, you can see everything okay?
It looks good.
Okay, great. All right, so thanks again for inviting me. It's my pleasure to give this talk. So let's go ahead and get started. So what I'm going to address is the simplest sort of all the inverse problems, and that's the problem of noise reduction. So, you have a clean signal U, and it's corrupted by noise, and we'd like to recover it. So basically, the general principle here is that we're going to design some sort of filter that produces an output that is as close an approximation in some metric as possible to the input. So denoising, as a practical matter, has come a long way. It has delivered very impressively in terms of the kinds of things that we can do these days. As a matter of fact, we can denoise, full-size mobile images on the order of 12 megapixels or so in just a few hundred milliseconds on a phone, with almost state-of-the-art quality, which is really great. You can really see this in the devices that you carry with you. There's a history to denoising. It's sort of, the whole field of imaging and image processing sort of started in the 1970s. At the beginning, there were some fairly straightforward sort of mean squared approaches, things like the Wiener filter. Then in the 80s, some heuristics for spatially adaptive filtering were introduced. And some robust statistics were introduced into these problems. PDE methods, things like anisotropic diffusion, Beltrami, total variation, wavelets. Then some of these heuristic adaptive methods were formalized a little bit more in the late 90s with things like the bilateral filter and then the non-local means, BM3D, and various concepts of self-similarity. Kernel regression, some of the techniques that we worked on, empirical Bayes, sparsity. And so by the time we hit around 2010, as I indicated here, there was a sense that many of the denoising algorithms that had been introduced up to that point had very similar performance, very different algorithms of very similar performance. And so the question arose, and my student Priyam Chatterjee and I wrote a paper in 2010, and we posed this sort of provocative question: is denoising dead? It turned out the answer to this was that it's not dead, but it was very close to being kind of reaching performance bounds in the mean squared error sense, like indicated here. And other papers like Levin and Nadler also confirmed the same idea, more or less. Now, the bottom line is the classical Gaussian denoising image problem seemed largely solved. There was still some additional room for improvement, and that came later. But we were certainly not done with denoisers just yet. And of course, since then, since the advent of machine learning, sort of the resurgence of machine learning, I should say, starting in around 2012 up until the present time, there have been, of course, dozens of papers written about denoising. I won't go through all of these ones in detail, but the bottom line is that the work continued on denoising, not just to improve the quality of denoising, but just to harness the power of denoising for doing all kinds of different things. And so the theme throughout this talk is not just to talk about what denoising is and what it does, but also how it can be used to solve all kinds of different problems. So as an application of this, as just an example of this, I want to bring to your attention a work that we recently did with some colleagues in Germany at the time, now in Italy, Florian Yoga and one of his former students, Mangal Prakash, where we applied this unsupervised approach to denoising scientific images. And so these images, the input image that you see in the first column here, are microscopy images, very, very noisy. And the best that could be done at the time, at least with some of the more standard methods like the noise to void methods, were this column in the middle. Now, our method is able to extract much more detail, and the design here has been something that is basically a hierarchical autoencoder with which learns these very specific structures for biological imaging. This doesn't necessarily apply to general images, but for this particular application, it's state of the art, and it's really quite amazing what we can do from the input to the output. Okay, so denoisers can do much more than just denoising. That's kind of the common theme here going forward. You can solve more general inverse problems. You can form the basis of many neural networks. Of course, we know this, especially recently with diffusion-based methods. You know, the core engine of those methods is, in fact, a trained denoiser. So let me give you what I think is a sort of unexpected example of what you can do with a denoiser. So suppose you start with this image on the left-hand side, which is blurry, of this image of the sea star. And the image on the right-hand side has been reconstructed. The blur has been removed using a median filter. Now, it seems really counterintuitive that somehow you could use a median filter to remove blur, but I'll explain how this happens later on. Okay, so now let's talk about very general and not necessarily linear denoisers. So just to put a little bit of mathematical structure around the problem, you start with an image X, which has been corrupted, and you perform some operation F on X, and that's this filter, and the output is X hat, which is supposed to be the clean version of it. Now, these functions F are typically, but not always, sort of non-expansive. You can think about it, if F was a linear function, if it's a linear operator, it would be like a low-pass filter, right? I mean, it's getting rid of the high frequencies that correspond to noise. The complexity here is that the high frequencies could be due to the image, or they could be due to the noise, and so that's where the complication arises. Also, this function F is not from an arbitrary range to an arbitrary domain. Images live in a bounded range of numbers. So if you have an 8-bit image, for example, the values that you have are from 0 to 255, or somewhat more generally, let's say 0 to 1. So you're mapping a kind of interval 0 to 1 crossed with itself and times to the same interval, right? So the input and output have to be in the same range. So what that means is that these functions F can't be arbitrary things, right? There are some very special properties that they have to satisfy. Before I go into the various properties that denoisers have to satisfy, let me just let's just assume we know what a denoiser is, and let me show you a very simple but extremely useful natural decomposition that you can extract from denoisers in a way that gives sort of rise to a perfect reconstruction, multi-scale decomposition. Now, it sounds like complicated words, but the idea is actually very, very simple. So let me show you. Suppose you start with an image X, and you apply a filter F to it, and this could be a nonlinear filter. And this nonlinear filter is a smoother or a denoiser, let's say. And you don't have to really think about it as a denoiser. You have to think about it as something that sort of behaves like a denoiser. It's kind of this low pass quality. Now, if you have f of x, then you can add this component x minus f of x here, and you will get x back, right? I mean, this is just an obvious bit of algebra. This first piece we call the smoothed version of the signal, and the second piece is the residual. It's what's left over. And typically, this is also, in a broader context, is called the Laplacian. So now imagine if I were to take this first part where I've applied f of x, and I were to repeat this process. So I apply f of x a second time to this decomposition. So f of x, and then compute the residual of that, and then carry over this x minus f of x to the next line. Okay. So I can repeat this process, and I can repeat it, in fact, as many times as I like. The result is that I get something reasonable if this f is non-expansive. What that means is that if I keep applying f many, many times, this component is not going to blow up. Okay, this component is just going to get smoother and smoother and smoother. All right, so let's do this with a little bit more formalism. Suppose your denoiser has some parameters in it. You can imagine these parameters could be, if the denoiser is a learned convolutional network, these could be the weights. Or alpha could be the variance of the noise for which you are training or specifying the denoiser. So this is exactly the same expression I showed you before, except that f is now parameterized by some alpha. So now I repeat this process, right? I apply f a second time, look at the residual, et cetera, and I repeat this n times. And you can repeat this as many times as you like. I've just chosen to stop here at n. All right, so what do you have? You have here in this term, you have the filter applied n times. And then in this second term here, you have the accumulation of all the residuals from the different steps, okay? So you have a very smooth version of x, and then you have all the details captured in this. And each detail rk is f applied k times minus f applied k plus 1 times. Okay, it's very, very simple algebraic structure. All right, so this is the decomposition, right? It's still a perfect reconstruction. So I can add these two pieces together and I just get x back, right? So now suppose I wanted to do something and get not just x back, but some modified version of x back. I could do this. I could take this term and I could put some coefficients in front of it. And I could take this term and put a bunch of coefficients in front of it. And I could normalize so that the sum of these coefficients, beta, adds up to 1. And I would get a different image, not x, but g of x. And this g is now parameterized by two sets of parameters, alpha, which came from here, and beta, which came from these coefficients that put in front of us. Okay. So this recomposition is really just a very general way of doing image processing. It's basically taking x, decomposing it, and then taking those pieces and putting them back together to get a new image back. So let's show you some examples. So again, this alpha and beta, you can think of them as control knobs that allow you to control how this filter behaves. All right, so now let's say I have some example pairs. Suppose I take an image into Photoshop and I perform some operation on this image and I get x hat, okay? So now I have paired examples, x and x hat. And now I construct a loss where the first term of the loss is the difference between x hat and the recomposition that I just showed you in the previous slide. Okay, and then I have another term here, which is a regularization that somehow regularizes the alpha and beta, which are the control parameters. Okay. By doing this, if I minimize this loss, I'm able to learn the coefficients that best approximate the output given the input. Okay, so I learn a way of approximating the operation that I did, let's say inside Photoshop, with this classic decomposition that I just showed you based on a denoiser. And this is kind of what it looks like. In mathematical terms, x hat is basically a smooth component, and this is f applied n times to the input image. And then there's a bunch of detail components, and I put a bunch of coefficients in front of them. I've denoted the filters here as kind of powers of some operator. W to the K means some filter applied K times, just for notational simplicity. And then there's the coefficients beta. If you want to be a little bit more general, you can also put the output of this process through some nonlinearity, and then blend them back together, and you get this. Okay, so if you put it through nonlinearity, now you begin to look like a neural network, but I'll get to that a little bit later. But the bottom line is you can start with an input image like this, and then go to an output image that's a very general image processor, if you like, and it's controlled by some set of parameters. All right, so what kinds of things can you do with this? Well, there's various visual effects. This image actually was captured by a professional photographer, Andrei Dragan. It's not really noisy. So what we can do is build a filter that acts like a wrinkle reducer. Okay, that's just reducing high frequency components in this image. Or we can build a cartoonizer. All of these are, again, from that basic structure that I showed you with different alphas and betas. Very straightforward. Another thing you can do is you can change dynamic range. So when something is hazy, you can reduce haze, again, by the same process with different coefficients. This is another dehazing example. This is an example image in London. And you can get this, again, by very simple construction of those filters with some adjusted coefficients. Okay, so up until this point, I've given you a very broad overview, a little bit of history of denoisers. I've talked about what denoisers are a little bit, and I've talked about a very simple way of doing general image processing with the denoiser as the base. Okay, so if I were to stop here, hopefully you've taken away something from this, that not only are denoisers useful on their own for reducing noise, but they're also very useful for the purpose of doing other general things. So now let me go through a kind of categorization of nonlinear denoisers. So the first ones to start with are so-called pseudo-linear denoisers. And these include things like non-local means, bilateral, BM3D, etc. The second category are Bayesian denoisers, based on basically having prior information, things like maximum a posteriori, minimum mean squared error, like Wiener filter. And then there are many others, of course. There are PDE-based denoisers, CNN-based denoisers, and so on and so forth. So this is a very general categorization, but I want to talk a little bit about the specific form of each of these denoisers, and then show you how they relate to each other. So let's go to pseudo-linear denoisers, but let's just first start with linear denoisers, right? Okay, so what's a linear filter? The linear filter is you take a bunch of coefficients like these from the input image, a bunch of pixels from the input image, you multiply them by some coefficients, and you get an output pixel, right? That's just a linear filter. Now, if you were to just change this description so that the weights are not just independently chosen, but somehow depend on the input pixels, now what you have is what I call a pseudo-linear filter. The form of the filter is still linear, but the weights depend on the input pixels. Okay, so let's be a little bit more formal about this. If this is a description of this linear filter, I can take all the coefficients that point to a particular output pixel I, and I put them into a vector. Then I can take all of these vectors and stack them into the rows of a matrix W. And then the output is going to be W times X, right? So the output image is some matrix W times X. Each row column, so X is scanned into a column, okay? So W times X. The only thing that's kind of fancy about this is that this matrix W depends very generally on X. It can depend on X. Let me show you how. So here's an example. You can start thinking about, for example, non-local means. What does non-local means do? It takes a weight matrix like this. It takes xi minus xj, looks at the difference of 2 pixels, and normalizes it by some h, and then produces this kernel value, k, and then normalizes these kernel values to get you the weights that you use to average. So for example, this blue pixel, if you measure the similarity of all the other pixels, in this image to this blue pixel, using this similarity measure, you get a weight image that looks like this. Okay, and for this pixel, the weight image looks like that. So if you take this and you scan it into a vector, that is one row of that matrix W before you normalize it. Why are these interesting? Well, first of all, they're very widespread and they're very easy to use. And it turns out they can be, they are in fact approximations of Bayesian denoisers. They're so-called empirical Bayes denoisers. The other reason for their convenience is that they work in two stages. There's a nonlinear stage where weights are calculated, and you see that's where this W of X is computed. And then there's a linear stage where that weight is applied to the vector that's the images, and then that gives you the output. Okay. Just as a side note, let me also mention that if you take the residual x minus W times x, we often refer to this as the Laplacian action on x as well. You can write this as L times x, where L is identity minus W. So just set this aside and remember it a little bit later. It'll become handy. All right, so now let's talk about Bayesian denoisers, maximum a posteriori versus minimum mean squared error. So both of these work with the posterior PDF of u given x. Now, in the case of maximum a posteriori, you get the argument that maximizes this, so it's the peak of this posterior. And in the case of minimum mean squared error, is the expected value of this conditional density. So they don't coincide. They might coincide if the distribution happens to be perfectly symmetric, and if the variance gets very, very small, then they might coincide. But generally speaking, they're not the same. All right, so in more specific terms, maximum a posteriori denoisers have this form. So it's basically an optimization problem where the mapped denoised image is the result of minimizing this loss function. This loss function has two components to it. The first part is basically a manifestation of the Gaussian assumption on the noise. So that's just the L2 term here. And the second part is the negative log of the prior on u. So this is sort of P of u. And that, when you take negative log of that, you get phi of u, and that's this term that you see here. It turns out, and this is well known to folks in optimization theory, that this operator can in fact be written, it is in fact what's called a proximal operator. It's got these two things that it depends on. It depends on this phi, which I described here, and it depends on sigma, which is this term here. And in particular, when phi is convex, this is exactly what is known as a proximal operator, although in general, we use non-convex phi in denoising as well. All right, so if you think about this as the proximal operator, it turns out there is a sort of semi-implicit or a semi-explicit, if you want, way of describing this map estimate. And it looks like this. It's x minus sigma squared, the variance of the noise, times the gradient of this phi that's up here, except that it's not quite phi, it's phi sub sigma. And this phi sub sigma is a smooth version of the phi that you saw up here. This phi sub sigma has a name. It's called the Moreau envelope. Again, that's from optimization theory, and you can look that up. But the most important thing to take away from this is that the map estimate is x minus sigma squared times the gradient of a scalar function. And here's a visual example of it. So let's say this L1 function is the phi that we started off with. And then this red function here is the Huber loss. It turns out it's the Moreau envelope exactly is the Huber loss. So it's basically quadratic down here, and it's linear for the rest of the way. And if you take x minus sigma squared times the gradient of this red curve, you get precisely this green curve, which is the well-known soft threshold in the algorithm. All right, moving on to MMSC. So as I said, MMSC is this expected value of this posterior P of U given X. Now, you would think that this requires you to somehow do this integral with du against u, but it turns out there's this amazing result due to Tweedy, and it's been rediscovered many, many times. It turns out that explicit knowledge of this P of u is not needed. And it turns out this MMSC estimate can be written in this form: x plus sigma squared gradient of P of x divided by P of x. Now, P of x is the marginal density of x, which is the marginal density of the noisy image. So basically what this says is that the MMSC estimate can be computed from only knowledge of the noisy image and its distribution. You don't explicitly need the prior P of u. So when you have this, this is an indication that you should be able to construct the MMSC estimate as an empirical estimate based on just the images that you have in a sort of unsupervised way, right? And this is the key to many of the results where various denoisers have approximated the MMSC estimate. So let's do a little bit of algebra on this right-hand side. Let's write this as x plus sigma squared gradient of the log of P of x. That's just simple algebra from here to here. And then I'm going to just introduce this minus sign here. X minus sigma squared gradient of phi sigma x. So this looks exactly like the phi sigma that I had before, which was the Moreau envelope, except that I put a little tilde on top of it because it's not the Moreau envelope. What it is, in fact, is the blurred prior. So remember, when you have noise added to a distribution, noise added to a signal, so U plus E, the clean image plus noise, in the distributional sense, adding two random variables results in convolution of their probability densities. And that's exactly what this is saying. Basically, you start with a prior, you blur it with a Gaussian, which is your noise distribution. And then you take negative log of this, and that's precisely the definition of this phi sigma tilde. But again, the important thing to take away from this is that the form of the MMSC denoiser is, again, very, very similar to what you started off with from the map estimate. It's x minus sigma squared times the gradient of some smooth version of phi. And that's key. All right, so here's a visual illustration again. So this is the L1 loss. The red curve is the Bayesian posterior. It's again a smooth version of the L1 that we started off with, but it's a very differently smoothed version. It's just a blurred version of it. And again, if you compute this x minus sigma squared times the gradient of this red curve, you get this green curve, which looks a lot like soft thresholding, except that it's actually it doesn't have any discontinuities, right? So it's sort of it's differentiable everywhere. All right, so let me review the summary of the denoising operators. So pseudo-linear denoisers, you could write them as W of x times x, and that's basically x minus the Laplacian times x. The map estimates can be written as x minus sigma squared gradient of the smooth version of phi, where smooth means Moreau smooth loss in this case. And the MMSC estimate is x minus sigma squared, again, the gradient of a differently smooth version of phi. The bottom line here is that the general form is f of x equals x minus something of x. And the big lesson to take away from this, the message is that these denoisers are all basically perturbations of identity. And they are a form of shrinkage. So you can see you take x and you take something away from it. And you could also think of it as a gradient step on some energy function. It's important to understand why I'm calling these a perturbation of identity. Think about what a denoiser does. It takes a clean image, you take a clean image, you add noise to it, and the denoiser takes the noise back. So ideally speaking, if the image that you feed to a denoiser did not contain any noise, then the denoiser should just give you that image back, right? So ideally, the denoiser should be the identity, right? In the case of noise-free images. And so therefore, when you add noise by amount sigma, you should be perturbing identity so that you can get rid of that sigma. And so that's the very general interpretation here. You can see that sigma shows up here. This is the identity operator, and this is a perturbation away from identity. Okay. All right, so you can be even more general about this. You can say, okay, well, you know, if the denoisers are of this form, let me write x minus v of x, where this v of x is just some vector function applied to x. And I can think of v of x as, generally speaking, the gradient of some energy field. Okay, so this e of x is a scalar function of a vector variable. This x is the same as that x. The font is just messed up here. And this energy function could be, in fact, trainable. In fact, there's been this nice paper by Cohen and several other folks, Regev Cohen, that talks about building denoisers that are gradient driven, and so basically constructed in this way. So if you think about this v of x in terms of the gradient of this e of x, then the f of x, if you were just to write it by pulling this gradient out from the whole thing, is the gradient of 1/2 the norm of x squared minus e of x. So you can think of f of x as the gradient of e bar, where this e bar is just a normalized version of this. By the way, if you work in optimization, you would note that if E is a convex energy function, and this is a convex, this is the difference of two convex functions, so it's got all kinds of interesting properties as well. All right, so if you think about this formulation right here, it says f is the gradient of a scalar function, right? Very simple. What that means is that f, if you think about it as a vector field, it's a conservative vector field. And because of this particular property, the gradient of f, or the Jacobian of f, if you like, is symmetric. Why is it symmetric? Because you know, if you take the gradient of, or the Jacobian of f is the gradient of this, and therefore it has to be symmetric. And so anything that is of this form, where v is the gradient of some scalar, satisfies these properties. It's that function, that denoiser, is a conservative vector field, and it has a symmetric Jacobian. This means that both MAP and MMSE also satisfy this property. What about these functions? This seems a little bit less obvious. Is it true that denoisers of this form also are expressible in terms of an energy function? That it turns out the answer is yes, if a certain set of properties are satisfied. So if W of x is a symmetric matrix, and if W of x is scaling invariant. So if the weight matrix that gets applied to x is scaling invariant, so if you multiply x by some constant c, that c is able to just come out, then if these two conditions are satisfied, then this matrix can also be written, this matrix vector operator can be written as the gradient of an energy function. That energy function turns out to be just this, okay? And then where this E is, in fact, a quadratic form. It's not exactly a quadratic form because W depends on X, but it turns out if these conditions are satisfied, then things sort of simplify. It seems a little bit mysterious. I know I'm not giving you all the details, but basically all the forms of the denoisers that I described so far, with the proper conditions, can have these nice symmetry and conservation properties. Okay, so very related to applications to machine learning is this idea of score matching. So I'm sure most of you, if not all of you, have heard about score matching, and this has been used very recently for solving all kinds of inverse problems, for designing diffusion networks and so on and so forth. And the idea kind of makes sense if you think about it in this context. So think about f of x again as x minus the gradient of some energy function. And now let me, and these were some examples of this, right, that we just showed you earlier. Now let me just rearrange this equation, right? If I can in fact write a denoiser in this form, then the gradient of E is x minus f of x, right? I've just rewritten this equation. I've done nothing very fancy. What this means is that this right-hand side now is the residual of the denoiser, okay? And the left-hand side is if this E of x, in fact, somehow captures the geometry of the manifold of images in the vicinity of x, then this gradient of E is measuring the geometry, the local geometry of the manifold around this E of x. And in fact, what it says is that the geometry of the manifold of images is captured by the residual of a denoiser. Okay. Now, this has been explained in all kinds of complex ways, but at least intuitively, it's the easiest way for me to understand it. So to put it in other words, if you have a good denoiser at hand, if you've managed to design or train a really good denoiser for getting rid of noise from natural images, what you have at your fingertips is something that has learned the local geometry of the image manifold. And a good denoiser can allow us to sample from and project onto this manifold of images. And this has, of course, become a very useful way of thinking about a generation of images using denoising diffusion models. Here, what you do is you're basically projecting on onto the manifold of images. You know, again, in one direction, you're sort of taking an image and you're adding noise to it until all structure disappears. And then in the other direction, you're trying to see if you can go backwards. And the short part of the story is that in order to go backwards, you need access to this gradient of the log of P of x. And this, as I showed you previously, is precisely available to you if you have a good denoiser and if you have the residual of that denoiser. That residual can literally be plugged into this, and that allows you to take these steps and go backwards. Okay. So we've used this idea by, but also conditioning on. I'm personally not necessarily interested in just image generation. I'm interested in image enhancement. So let's say you're not starting with just noise and trying to generate an image like was done here in this reverse direction. Instead, let's say you're starting with a degraded image, like this input image, which is noisy and blurry, and you want to recover. So what you do now is you're not just doing diffusion, you're doing conditional denoising diffusion. And it turns out one of the very effective ways of doing this is to split it into a deterministic component, which is basically an initial predictor. It's completely deterministic. Let's say you have a simple deblurring method. You just apply it, you get an initial condition. And then you use the conditional denoising diffusion model to predict not the image itself, but the residual that when added to this initial prediction gives you a good sample of the posterior. Okay? And so it turns out this is very, very effective in terms of giving you very high quality reconstructions, and it speeds up sampling by a great deal as well. So again, the key insight here is, of course, you use denoisers here, but predict the residual instead of predicting the actual image. Okay, so I just said these things, and it allows you to get a flexible perception distortion trade-off. All right, so the last topic that I want to talk about is that, as I said, again, if you have a good denoiser, you have some idea of what the distribution of natural images is, and you also have some sense of what the geometry of the manifold of natural images is. And it turns out we can use these to establish priors if we want to solve these kinds of optimization problems for inverse problems. So there's two ways that this has been done. One is this plug and play prior method that came out in 2013. And then we were inspired by this work. And in 2017, we came up with this work on regularization by denoising. Whichever method you use, the idea is that basically in order to solve an inverse problem, very general inverse problem, the solution turns out to be you take your data, you apply some linear operator to it, you put it through a denoiser, you apply another linear operator to it, another denoiser, and so on and so forth, and eventually you converge to a solution. In principle, it's very, very similar to the diffusion-based models that I just mentioned to you. And there's some deep connections between them. So in order to describe the regularization by denoising, I need to tell you a little bit of background. So one of the ways people have designed these priors is to think about the Laplacian. So imagine you do it this way. So your regularization is X transpose LX, where this L is this L of X. Okay, so this LX is exactly this term here, L of X. This was tried for a number of years, all the way from 2008 all the way to about 2015. And it's fine. You can use this method, but why not be more general? This method itself actually does have some shortcomings in the sense that, explicitly speaking, this Laplacian matrix is actually rather hard to compute because it's huge. And of course, L or W is also a function of X. So it's a little bit difficult to keep track of things, but that's okay in the sense that with a numerical optimization scheme, you can optimize this step by step, and at each step you can compute X and then keep this term fixed. So you can treat it as a linear problem or a linear operator at each stage. All right, so what we did was kind of the very natural next intellectual step, if you like. So if this regularization is what we used before, which is Laplacian, X transpose LX, you can write it as X transpose X minus W times X. So why not just take W of X, which is a linear or pseudo-linear denoiser, and just replace it by an arbitrary denoiser? And that's exactly what we did. Okay. So regularization is 1/2 X transpose times the residual for an arbitrary denoiser f of X. And it turns out that by some very interesting magic, the gradient of this regularization term turns out to be exactly the residual, as long as certain conditions are satisfied. And those certain conditions are Jacobian symmetry and homogeneity. And you might remember I referred to this Jacobian symmetry earlier as one of the conditions that these standard and a very well-constructed like MMSE and map estimators satisfy. So it's not necessarily the case that an arbitrary denoiser will satisfy these conditions, but some of the more principled denoisers like MMSE and map will satisfy this condition. All right, so how do we compute this? It turns out, you know, for the sake of time, I'm not going to try to go into too many details, but the bottom line is that the conditions are, you know, if you have differentiability of f, you have some local homogeneity where this coefficient just pops out, and you have Jacobian symmetry. And if these are satisfied, then the gradient is relatively straightforward to compute. And there are a couple of interesting consequences of this. It turns out that the assumptions that we make about these properties that the denoiser has to have, one of them implies that the f of x, the denoiser, behaves like this. It's sort of is its own directional derivative. That says something about the geometry of what an f of x does. And then the second condition is the stability of the filter, which is to say that if you perturb the input by some small h, you get the Jacobian times x plus h. So you don't go too far if you slightly perturb the argument of the denoiser. And you can think about this in more general form as well, in the sense that if this denoiser for very general f of x looks like the gradient of f dot x, that's a very general form of just the pseudo-linear denoiser. In any event, once these conditions are satisfied, after some algebra, you get that the gradient of r of x is in fact the residual, which is a very nice property to have. So now let's actually look at a couple of steps where you solve the inverse problem. So if you have this, the conditions that are posed allow you to get a solution, a numerical solution. I'm going to just show you one of many possible numerical solutions. This is a fixed point solution. You can ignore the details if you like. Just think about this first term here. It's fixed. It doesn't depend on iterations. So this is just like a fixed vector B. You can think of it as a bias. This is just a fixed convolution matrix. this is a denoiser. And if you define this z of x to be the output of the denoiser, then what you see is z of k plus 1 is equal to f m zk plus b. And this is precisely the formulation that I showed you earlier, an affine operator denoiser, affine operator denoiser. And if you continue this, you will get the fixed point solution to this optimization problem, which solves your inverse problem. And so here's a couple of examples of this for both deblurring, and that's what I showed you earlier, I think. So with that, I think I'll wrap it up. So the conclusions are denoisers are a very fundamental building block for image processing. They form stable perturbations of identity, and they can solve very general inverse problems. And if you have a good denoiser, again, they give insight to the nature of images. And with that, I think I will stop, and I think we have maybe a few minutes left for questions.
Thanks, Peyman, for sharing with us the many different forms of denoising operators, their origins and their motivations. I'm not sure whether we can see the questions here from the participants that view online. Maybe I can start with question first.
Sure.
So yeah, Peyman, so there are many research papers on denoising that actually build that huge deal based on very deep neural networks. And obviously, due to the size and the memory consumption, they wouldn't fit into a smartphone. So I think many researchers, they are wondering whether this is the right research direction, and if not, how we should design effective or efficient denoiser for mobile devices. Can you share your view?
Sure. Yeah. So if you remember in the early part of my talk, I mentioned that even by 2010, we'd gotten very close to basically having essentially MMSE optimal denoisers, and there was very little room for improvement. So what has happened since is that the quality of denoising with neural networks has improved, but the amount of room you have for improving on classical denoisers is really not that giant, right? I mean, it makes a difference in terms of benchmarks and kind of competitive academic papers and so on and so forth. But in terms of having a practical denoiser on a mobile device, it doesn't necessarily need to be neural based, right? You can actually build very smart denoisers that are relatively thin, maybe just a few layers of a neural network, but they're smartly constructed to optimize and get very, very close to optimality. And so you don't really need the kind of giant neural networks that you might otherwise need for other applications. I hope that answers your question.
Yeah, I think that's the right way to go, designing smarter neural networks for mobile phones.
Right.
And I think it's especially hard when we are dealing with like denoising and like brightening the dark environment, dark images at the same time, getting more difficult. Yeah. So yeah, in our group, we are doing a lot of research on that, and it's a really hard problem. Let me give the chance to other participants. Any questions from the floor before we switch to the next talk? Okay. Then if not, maybe we can end the first keynote here. And thanks, Peyman. I know it's close to midnight at your time.
Yeah, no problem. My pleasure.
Yeah. Okay, thank you.
So take care.
Take care. So our next talk will be a talk by Dr. Patricia Vitoria from Huawei Zurich Research Center. So she will deliver the talk about her best paper with the title Event-Based Image Deblurring with Dynamic Motion Awareness. Dr. Vitoria, please.
Do you hear me?
Yes, we will hear you very well, and we can see that slide.
Okay, so good morning to everybody. And first of all, I would like to thank the organizers for the Best Paper Award. So today I will present the paper Event-Based Image Deblurring with Dynamic Motion Awareness. So actually this is a work done in Huawei Zurich Research Center. So here you can see also my colleagues. So let me start this talk by explaining the problem that I want to tackle, that is motion blur. So what is motion blur? Motion blur is the blur that you can see in an image due to camera or scene motion during the exposure time. So this means that or the camera or the scene has moved too quick such that the sensor was not able to capture a sharp version of it. And so here you can see two examples. The one in the left is one of the typical examples where you are trying to take a photo in a night scene, and due to the low light conditions, you need a long exposure time. So it's normal that so the person in the image or the camera is moving. Or also it can happen in daylight scenes, like the one in the right, where the object, in this case my dog, is moving too quick, and then you have a blurry version of it. So actually, this is a problem that has been studied a lot in the literature. Is like, we call it image deblurring. And learning-based image deblurring methods, they mainly tackle the problem by estimating a one-to-one mapping from a blurry image to a sharp version of it. So actually, for every blurry image, we have infinite possible solutions, and this makes the problem really ill-posed. So actually, you could output every single image in between the exposure time, and all of them will be a correct solution. Also, due to, if you have a look in the blurry image, we don't have any kind of temporal information, so we don't know if the object is rotating to the right or to the left. And also in the blurry regions of the image, we are missing textural information. So this actually makes the problem really challenging. To overcome this issue, in our work, we use the complementary information provided by an event camera that is able to capture this temporal information, so we can see how the object moves during the exposure time, but also we can estimate, like, we can see the high frequency details of the image. And thanks to this additional sensor, we will pose the problem in a more tractable way. So for the people that is not familiarized in an event camera, so let me explain. So an event camera is a sensor that responds to local changes of brightness. So if in a pixel there is a local change bigger or smaller than a threshold, then it will trigger an event. So let me show an example. So in the upper part, you see a conventional RGB camera, where at a given frame rate, it outputs the intensity values for all the pixels. Even if there is no movement, the conventional camera will continue outputting this information, this intensity information. And if there is movement during the exposure time, or the object has moved too quick, we will have motion blur. In the bottom part, you can see the output of an event camera, where we will only see events if there has been local changes of intensity. So in this case, where there is the disk moving. If there are no movement, then there is no event, so we don't trigger anything. And actually, these kind of cameras, they have a really high temporal frequency, so you can see all the information without any kind of blur. So actually, you will see something similar to what you see in the right side as an output of an event camera, that you will have like asynchronous events, where for every position X and Y, you will have a polarity that will tell you if the change were positive or negative, and also the timestamp. So at what time this event was triggered. So, and why we want to use this kind of event cameras? Why we want to use this additional sensor? So this is one of the big questions. So actually, this sensor have a set of really attractive properties. So for example, they have a really high dynamic range compared to RGB cameras. So there is a dynamic range of 120 dB compared with the 60 dB of a regular camera. It has a really low latency because we don't need to wait to send all the information from the events, but we can send them separately, asynchronous. So actually they make it really suitable for real-time applications. Actually also has a low power consumption. As I said before, a high temporal resolution. So actually we know all the information that happened in terms even of microseconds. And what is important for us for image deblurring, there is no blur. So actually there is not this problem of blur, so we can see what is happening, actually what is happening during this exposure time. So let me explain the pipeline that we propose in this work. So actually the main idea of our work is to split the learning of the per pixel motion. So actually we want to know how every pixel in the scene has moved, and then we split it from the learning of the blur operator. So to do so, first we estimate blur image features at different scales. So we take as an input the blur image, conditioned to the events, and we generate a set of blur image features. The event information in this case is so it is represented as a voxel grid representation. So actually we divide it by different times. So we split it in time, and we sum the polarities over it. Then we have a second encoder that take a chunk of events. So we divide all our events in different chunks, and then we create voxel grid representation out of it. And actually what we want to do is we want to exploit the inherent temporal information of the event data. And we want to use this event to dynamically estimate the per pixel trajectory. So for every given image, we will estimate the per pixel trajectories. Actually, this per pixel trajectory in this case will be how every pixel has moved during the exposure time. And we will estimate this in terms of offsets and mass. So here you can see an example. In the left, you will see like a vanilla convolutional layer where you have a regular grid that is always the same. But in our case, for every pixel, we estimate offsets and mass that will move this grid following the motion of the pixel. So if a pixel has moved to the right, all this grid will deform to the direction of the motion of the scene. Also, if it will attenuate or amplify positions depending on how long it stayed at each position of the blurry scene. And this type of convolutional layer that is called modulated deformable convolutions, we will use it to deblur the blur image features from the first encoders. So once we apply this, every feature will be already deblurred. And then finally, what we do is a coarse to fine residual decoder. So we estimate the sharp image in a coarse to fine way to be robust to regions of the image where they don't have events or they have noisy events. So actually, if you see previous methods on the literature, event-based deblurring methods, they either have one of these problems. So sometimes they are restricted to the low resolution grayscale image that is given by the event camera. So they only work in this kind of grayscale image. Either if they work in RGB image, then they need RGB events. So they need this change of intensity for each one of the channels. And actually, right now, the event cameras, they work with grayscale events. So actually, they are sensitive to the lack of events or noisy data. So if there are regions of the image that they don't have events, they don't work really well, or if the data is really noisy, because actually event cameras are really noisy by nature. So you can also see this noise in the output image. So it's not really, it doesn't have a really pleasant output. And most of the methods, not only event-based method, but also image-based methods, one of the problems that they struggle is to generalize to real data. So in our work, we work with high resolution RGB images. We actually use monochrome events, so we exploit the intercorrelation between the RGB channels in the image. Actually, we are not sensitive to the lack of events or noisy data due to this multi-scale approach and coarse-to-fine reconstruction. And as we will see, it generalizes really well to real data. So let me show some results on GoPro. So GoPro is a synthetic dataset that is actually really spread in image deblurring to benchmark the results. And the difference with image-based methods that we use is that we also average the different frames, but we also need to simulate the events. So these results are results that are given by simulated blur images and simulated events. And here you can see an example where in the upper part, like in the upper row, you can see results by state-of-the-art methods on image-based deblurring, and in the bottom part, you can see the results by public methods in the moment that this was published, event-based methods, so Pan et al. And us. As you can see, in the case, for example, of the numbers in the car plate, our results look much more clear, and previous event-based methods, they struggle quite a lot with this noisy nature of the events. Let's see like a little bit more difficult example. So here we have an image where, for example, the girl in the background is walking. And if we have a closer look, you can see that for image-based methods, as they don't have temporal information and they lose all the high-frequency details, it's quite difficult to reconstruct, for example, the leg of the girl, in this case, that there is such a big movement, or also the main characteristics of the face. And in our case, you can see all the details of the face, so you can see the eyes, the nose, and the mouth, and there is a good reconstruction of the feet of the woman. And now that we have seen how our method works with synthetic data, it comes the real question. That's actually our work. It works well with real data, so we will be able to use our algorithm in a real case scenario. And to answer this question, we have built a real data set that we call RGB blur plus E dataset that actually is composed by high resolution RGB images together with the corresponding events during exposure time. So actually this dataset it is composed by two subsets. One is recorded in high speed. This is the first subset that it contains real events and real sharp images, but we synthesize blur images. So in this case, the blur image is not real. But then we have a second set where we have real events and real blur images, but we don't have ground truth sharp image. So the first subset, we will use it more for quantitative evaluation, and the second one for qualitative evaluation. In the right, you can see some of the examples of our dataset. So actually, our dataset is quite diverse. So you can see that it has indoor and outdoor scenes, and we have different light conditions. So we have day scenes and also like afternoon, night scenes, and also like indoor, outdoor, global, local movement, and a combination of them. So let me show some of the results. So here again, you have the original image in the left, and in the upper part of the slide, you have two image-based methods. And in the bottom part, again, the previous event-based method and our method. So as you can see, image-based methods, they typically degenerate to an identity solution when working with real images. So the output sharp image is quite similar to the input one. And this is due to the model gap between the synthetic trained images and the real one. Then if we go to event-based methods, we can see that actually working with real events already it helps, so it makes it more robust. And in the case of the previous method, Pan et al., it generates, so it is able to deblur, but it introduces quite an unpleasant artifacts in the image. And in our case, we are able to deblur the full image and all the colors without any kind of problem. Another example here, you can see like again, this is more a global camera motion, and we are able to deblur all the floor and all the building without any problem, and another one with a quite strong blur. Again, image-based methods struggle and our method, and it's able to create a really pleasant sharp image out of it. So let me show to conclude a little bit the quantitative evaluation. So actually, if we compare in the synthetic GoPro data set, we outperform image-based and event-based methods. And also, if we check our method in the proposed high-speed data set, we also outperform previous image-based methods and event-based methods. So let me conclude the presentation. So to wrap up, we have proposed a novel deep learning architecture that actually it decouples the estimation of the per pixel motion from the deblur operator. We also, as we saw, we have this characteristic that we will adapt the receptive field of the convolutional operator to adapt to the motion of the scene. And this is done dynamically for every image. And to evaluate and facilitate future research on the topic, we have collected a new data set. That is the first data set that actually contains high resolution RGB image plus real events. So thanks a lot. And if you have any question, just ask.
Okay, thanks, Patricia. Yeah, we really liked the idea of like divide and conquer, and having the cost to find multi-scale reconstruction, and the data is a real contribution to the community. So congrats again for getting the best paper award.
No, thanks to all of you.
May I know, I mean, the speed of your algorithm, and would it have a chance to improve it further?
Yes, so in the size of the GoPro image is around 1 second, a little bit more, if I remember well. But yes, I can send you probably later the details. I don't want to say exact number, but I think I remember that it's 1.5 seconds.
I see. Okay.
So it's for now it's not real time, but yes.
All right. Yeah, we received a question from the audience. So the question is, what hardware did you use for the real data collection?
So we use a beam splitter setup, actually with a mirror lens that both RGB camera and event camera are recording the same. So actually in the paper there is like an illustration, but the idea is that actually they both record the same, and because of this we were not able to record blur image and sharp image at the same time, because actually the beam splitter setup has the event camera and the RGB camera. So for this we have these two subsets, one that has blurry image and one that has the ground truth image.
I see. Okay.
And they are hardware synchronized so that we can find the beginning and the end of the exposure time and all.
Do you need like specific RGB cameras for this setting?
We are using a FLIR camera, and then by post-processing we kind of register both images and all. So and actually the resolution of both cameras are not the same, so we finally do a registration. So we use a FLIR camera, but I believe that other cameras could be used for it.
I see. All right, and thanks, Patricia, again. So we are going to have the next talk delivered by the best paper honorable mention. The talk will be delivered by Ruikang. Ruikang, please, you can share a slide. So the title of the winning paper is Continuous Spectral Reconstruction from RGB Images via Implicit Neural Representation.
Hear me?
Yes.
Yeah, 好，start. Okay. Thanks for organization the workshop. It's a great honor to introduce our work. Our work is a continual spectral reconstruction from RGB image via implicit neural representation. Okay. At first, we generally introduce what is spectral images. It can be regarded as a set of images with one channel. Each image represents the wavelength of a spectrum, also known as spectral band. These images are combined to form a 3D spectral disk cube. Therefore, spectral image can record the spectrum information for different air, like the tree and the storm. Relying on the rich spectral information, spectral images are beneficial to many computer vision tasks, such as tracking and routing sense, and so on. Generally speaking, there are three technologies to obtain the spectral cube: spectral scanning, cassette system, and the CT system. But this technology is suffering from the problem of high cost, complexity, acquisition, and large hardware. So reconstruction from RGB image is a low cost and convenient approach. Nowadays, exciting method for spectral reconstruction from RGB images has the improved performance, such as HSCN plus and MST plus. But this method reconstructs the spectral image by discrete mapping and fix the output numbers. On the other hand, Naor first introduced the implicit neural representation for generate the narrow view of natural science. Then Leaf used a local implicit neural representation for reconstructing 2D images. Inspired by the continuous spectral nature of the spectral signature, we first proposed to address the continuous spectral reconstruction from RGB images. Okay, in this part, I will introduce our method. As mentioned previously, exciting method aim to learn a discard mapping to reconstruct the spectral image as a blue dance. But our work aims to learn a continual spectral representation and sample it to the target number of such band as a red cover. So this is the overview of our method. We call it narrow spectral reconstruction, called as NSR. And give a RGB image. We cascade a feature encoder to extract the deep feature as one put. Following the continuous spectral representation, we also take a 3D coordinate as the data input. Specifically, we normalize the spectral wavelength to control the output band numbers. Specifically, we first set the spectral profile interpolation modular to upsample the feature. And then we devise the narrow attention map modular to exploit the spectral correlation. And finally, the latent code is fed to MLP to reconstruct the corresponding spectral significance. Before introduce the two modulars, we first overview the profile operation for inverse problem. For video and light field reconstruction, we can say that the profile operation is effective to exploit the correlation of the high dimension data. So inspired by this work, we propose the spectral profile interpolation modular. Specifically, we first convey the feature into the vertical and horizontal profile, then interpolate them respectively. Finally, we fuse the features to generate a 4D tensor. This modular is simple and effective. On the other hand, the attention machine system is widely used in spectral reconstruction, such as the spectral attention machine system and the spectral attention. So in this work, we designed the neural attention mapping modular to follow the spectral correlation. Specifically, we first fusion the information of the feature and the 3D coordinate and feed it to the attention block. The attention block first compress all information to one dimension. Enhance the attention can exploit the all correlation of the dimension. Next part is the experiments. We perform 4 comparison experiments for where the effectiveness of our mind. The first experiment is the spectral reconstruction with fixed band numbers. We can see that our NSR boosts the baseline performance with a little per meter increase. And also, our NSR can be plugged in wireless backbone, which is effective for both simple like HSCN and complex architecture like AWN. For vision comparison, we can see that our NSR take a significant error decrease. And also the spectral signature reconstruction by our NSR is close to the ground truth. The next part is the continuous reconstruction with arbitrary band numbers. Okay, in this, we compare with the SOTA method and see that our NSR can reconstruct the arbitrary band numbers and keep high fidelity. And the vision comparison further demonstrate the effective of our NSR. It also have lower spectral error than other methods. Next part is extreme reconstruction band instruction beyond the training sample. Our NSR can reconstruct extreme band numbers even beyond the training sample. The experiment results are shown as such. During the training stage, the target space number is roundly sampled in the range of 7 to 31 bands. But in inference stage, our NSR is able to reconstruct space image with extreme bands, such as 16 bands. Next part is spectral super resolution. Our NSR also can be used for spectral super resolution, and it boosts the performance of a baseline method. Finally, we perform the ablation study for verify our SPI and NAI modular. We can see that the baseline show limited reconstruction fidelity without our proposed modular. In summary, our NSR enables the spectral reconstruction of arbitrary band numbers for the first time. And we developed the SPI module and the NAI modular to exploit spectral correlation. Experiment demonstrates that NSR can improve the performance with a little per meter increase. More importantly, NSR can reconstruct spectral images with extreme bands even beyond the training sample. Okay, that's all. Thanks.
Thank you, Ruikang.
Hi,
Congrats for getting the best paper honorable mention.
Oh, thanks.
Yeah, we really like your method that basically can reconstruct like arbitrary brands. Yeah, for the first time using that really nice idea of nerve.
Yeah.
So, do you see any limitations of your method?
Yeah. We have tried that reconstruct the band number out of the training sample. Like we just say that we can train the Lucy band, but the wavelength is in 400 to 700 nm. But if it out of this wavelength, it will fail. I think because the RGB is in the visualize spectrum. If so, we can't reconstruct more information out of this. Yeah.
Okay, I see.
Yeah, thanks.
So, yeah, I got one question here for you from the audience. How many pair images did you use for training, and how about the speed of the proposed algorithm?
Oh, okay. We can see that in this part. We use the ICVL dataset as known as the NTRE 2010 NTRE dataset. It have 100 close to 100 samples. And the training time is long. Nearly, I use one GPU and take 3 days for training. Because I just yeah.
Okay. Thanks for your answer. And I think due to the time, we've got to move to another speaker. So thanks, Ruikang.
Yes, sir.
Okay. For the next talk, we will have Eyal to present his ECCV paper on combining internal and external constraints for unrolling shutter in videos. Yeah, I hope I pronounced your name correctly.
Hello, can you hear me and see the slides?
Yes, they look good. They look good. Yeah, so please.
Thank you very much for inviting me. I'm Eyal Naor, and I will be presenting our work about combining internal and external constraints for unrolling shutter in videos, a work done together with Itai Antebi, Shai Bagon, and Michal Irani in the Weizmann Institute of Science. Okay, so let's begin with talking about what is the problem of rolling shutter. Let's observe a real-world dynamic scene. Normally, when we think about a camera or an images, we think about a global shutter frame where the entire image is captured at the same time. All the pixels are taken and captured at the same moment in time. But in fact, common and unprofessional cameras, such as in smartphones, usually capture the image row by row. And this results in a variety of spatial distortions that appear under fast camera or scene motion. For instance, here you see the camera stretch out because the top part is taken at a different point in time as the wheels. A few more examples are that lines may become tilted. For instance, here it's as a result of a horizontal global motion of the camera. Shapes may become distorted. You can see how circles become ellipses, as well as the angles and positioning of the spinner arms become distorted. And there are many other distortions that depend on the motion type of both the scene and the camera. And another main difficulty in solving the problem of rolling shutter is that there are very few available data sets, and even these are with limited motions. That's because to capture a corresponding pair of rolling and global shutter pairs, you need to either use synthetic data or an extremely high frame rate camera, or use a beam splitter, which as a result, there aren't many training data sets for really deep neural network solutions. And as a result, existing approaches either need to assume simplistic motions, either a full translation or a rotation, or train a different model for each new data set. And as a result, it comes with limited generalization capabilities, as we will see next. So our key observations on which our method is based comes from observing the continuous space-time volume and doing so in the camera coordinate system. What we see here are the frames of the global shutter, and you can see that all the pixels in each frame are taken at the same point in time. In contrast, the rolling shutter frames depicted in green are tilted, since each row is taken at a different time. This tilt is what causes the visible artifacts that we've seen before. Now recall that all pixels in a certain frame, in a certain row in a rolling shutter frame are taken at the same point in time. So let's observe the XT slice at a specific row Y. Here you see the pixels of the global shutter images. They are depicted in purple circles, and they are the intersection points of the continuous XT slice with the global shutter frames. Similarly, the rolling shutter pixels depicted in green are the intersection points of the same continuous XT slice with the rolling shutter frames. Now notice that the temporal distance between the pixels is constant and also easy to calculate. It depends solely on the row number. Or in other words, the rolling shutter and global shutter video pairs share the same XT slices and differ only by a known 1D subframe shift. Also, since its observation is done in the camera coordinate system, it is invariant to the type of motion or distortion, and thus applying to the vast variety of distortions that we've seen earlier. Let's see this visually in a video. Here is a corresponding video pair of global shutter and rolling shutter video. Notice again the distortions in the shape. Let's focus on two specific rows. Here are the corresponding XT slices at those specific constant rows, where the vertical axis is the temporal one. Now you can see that the XT slices between the rolling shutter and global shutter slices differ by a 1D subpixel shift, meaning that if we apply the correct subpixel shifts on the rolling shutter XT slices, we can solve for the correct global shutter frames. Moreover, since the XT slices do not involve the vertical axis, they do not exhibit any rolling shutter distortions. The rolling shutter artifacts stem from different rows taken at different points in time. When we are reviewing a specific single XT slice, we are looking at one specific row, so it is irrelevant whether the row above or below it were taken at the same time or not. Or in other words, when you're looking at a single XT slice, we theoretically should not be able to discern if it is taken from a rolling shutter or a global shutter video. In particular, small XT slices in the rolling shutter video are undistorted, and we show in the paper empirically that they bear high similarity to the small XT patches in the global shutter video for which we want to solve. Or to put it in other words, the two videos share a similar pool of XT patches. Now, previous works have shown empirically that there is significant internal patch recurrence in both images and videos. They show recurrence both in XY patches in single images and in XYT patches in videos, whether across scales or even across dimensions. Now, these previous works have also utilized this similarity for various computer vision tasks. With similar tools, in this paper, we show empirically that there is also significant recurrence of small XT patches, for example, 5x5 or 7x3, across the rolling shutter and global shutter videos. This observation enables us to leverage video-specific constraints at test time, as we will see next. Please see the paper for more details and for the empirical analysis and for what it details. Now, following our observation, our method is composed of 3 consecutive steps. Let's dive into them one by one. The first one is temporal upsampling and resampling. We begin with the rolling shutter frames, which again in the space-time volume are tilted since each row is captured at a different point in time. We aim to solve for the global shutter frames, which are axis aligned in the space-time volume. In our algorithm's first step, we fill out the space-time volume using Dane, an out-of-the-box, state-of-the-art temporal interpolation network that was exhaustively trained on a huge bulk of regular videos. Then next, we In fact, we recast the rolling shutter problem to a temporal interpolation one. As a result, any advancement of temporal interpolation tools will result in better rolling shutter solution in the future. For the, yes, okay. In the next step, we resample the space-time volume and take the relevant row from each frame to build our global shutter proposal. Now, while ideally this would be enough, since the temporal interpolation tools were trained on regular videos and not videos with harsh rolling shutter artifacts, they often struggle with these videos with significant rolling shutter artifacts. And for this reason, we continue to our next steps. First, we generate multiple global shutter proposals. We do so by applying a variety of augmentations on the input video and applying the temporal upsampling and resampling on each one of them to get an ensemble of multiple global shutter proposals. In the next step, we merge these multiple proposals using MergeNet, a rolling shutter dedicated neural network. Now, since the heavy lifting was already done in the previous step by the temporal interpolation tool, our network can be light and with a small receptive field. You can see here that the network is composed of only 8 layers of convolutions and activations. Also, because this network is light, we can train it on a single synthetic rolling shutter dataset, thus solving the problem of scarce training sets for the rolling shutter problem. Unlike other existing methods, our network is trained only once and does not need to retrain on each new dataset. Lastly, we want to leverage our observation that I detailed before about XT patch similarity. We want our global shutter prediction to have small XT patches that have a high similarity to the distribution of the input rolling shutter video, to the input XT patches in the rolling shutter video. To do that, we apply a nearest neighbor loss on the small XT patches, whether 5 by 5 or 7 by 3, to get the distribution closer to the wanted one. Simultaneously, we apply a validity loss to remain relatively close to our initial solution. We saw empirically during our work that the nearest neighbor loss improves results specifically best around edges. And so we use canny edge detection to properly weigh between the nearest neighbor loss and the validity loss. Please see the paper for more technical details about this step. Okay, now for the results. You see here on the left, the rolling shutter input, and on the right, the ground truth global shutter frames. In order to properly evaluate the results, we also introduce a misalignment visualization. We convert the prediction in the ground truth to grayscale and place the ground truth in the red and blue channels and the prediction in the green. Properly rectified areas will be depicted in gray, while green or magenta areas indicate misalignment. Here are our results. You can see that there are almost no remaining misalignments. For comparison, here are the results of the state-of-the-art results, competitors. You can see the huge remaining misalignments as their method cannot solve for these harsh rolling shutter artifacts. Here are also a few zoom-ins for emphasis. Okay. Numerically, we achieve state-of-the-art results on existing datasets, and let's break it down. Here are the results on the Carla synthetic dataset. This is the dataset on which we trained our MergeNet that I detailed before, and you can see here a large improvement on the state-of-the-art results. But perhaps more interestingly are the results on the FastTech rolling shutter dataset. Despite our competitors training a model specifically on their dataset, on the training set of the FastTech dataset, they train a different model for each dataset, and us never seeing the training set of this dataset, we still achieve better results. In addition, since each one of these datasets contain a different limitation, Carla is synthetic and the FastTech one has almost entirely horizontal motion, we curated a new dataset. We named it In the Wild. It is composed of real-world videos with non-rigid motion and also multiple difficulties for a better evaluation of new models and where they stand. This dataset also best shows our better generalization capabilities. The results we show here for the competitors are the best ones from their multiple models, and our results are from our single model. Okay. Here is an example video from the Carla synthetic dataset. Notice the shape of the reconstructed pole and the remaining misalignments on the car. Here is an example from the FastTech rolling shutter video. Here you can see the horizontal motion that I detailed before, and focus on the readability of the sign, as well as the proper alignment of the window and the woman. And here is an example from our in the wild data set. You can see that it is complex, non-rigid motion. And I want you to focus on the proper placement of the feet of the cheetah, thus properly understanding the motion in the scene, and as well as the shape of the reconstructed head. Okay. To sum up, we first recast the rolling shutter problem as the temporal upsampling problem, thus enabling us to leverage tools, advanced tools that keep advancing, as well as they can train on the vast available datasets of regular videos instead of the scarce datasets of rolling shutter corresponding pairs. Then we bridge the rolling shutter gap by using first a rolling shutter dedicated neural network that can be trained on relatively scarce training data, followed by a real-time optimization step that leverages our observation on XT patch similarity between the rolling shutter and global shutter videos. Thank you for listening. Please come by on Thursday to check out our poster, as well as see the paper, project website, and use our official code and available data set. Thank you, and I'll be happy to answer any questions.
Thank you, Eyal. So you may ask question in the chat room. So while waiting for the questions, maybe I can ask the first question. So your method is based on the temporal upsampling method. Mm-hmm. So do you see any problem with this component? I mean, when the motion is very fast, because we know that sometimes the synthesis might fail.
Yes. Yes, the networks also struggle, of course, when the temporal interpolation tool fails. I think actually the most interesting fail case for the temporal interpolation problem is when we have severe aliasing. For instance, the rotors on airplanes or ceiling fans, you can see there, once you have aliasing, the temporal interpolation tools, they do an interpolation. They don't do actual super resolution that solves for the aliasing. So that's the main problem. But I think the most interesting part about our work is that it's plug and play. When we have improvement in the temporal interpolation tools, you automatically have improvements here. So we are not fixed in this moment in time and these results we show for the rolling shutter, but we can actually leverage, as you say, the current limitation is the problem with the temporal interpolation networks, but as they improve, because it's a hot problem that people are continuing to work on, there are much more, I think it's especially because there are more training data there than in the other problems. You can use any video to train these networks. So we can leverage any improvement there to get here also. So I actually think it's a feature, it's not a bug, that we are linked to that problem.
Okay, got it. Thank you. Yeah, that's one question from Chen. So the question is, since rolling shutters are usually caused by fast motion or long exposure, which can also create motion blur, did you consider motion blur when simulating the pair data and designing the network?
We actually didn't really see much motion blur. There are works that deal with motion blur together with the rolling shutter, but since the problem, it's actually quite counterintuitive, at least for me. It has long exposure time and image, but since the exposure time for each row is separate, then actually we didn't see that significant motion blur, because it's like one of the other. You can't have also a long exposure time for a single row, and then if you have for one single row a long exposure time, then for entire image, because it's hundreds of rows, it becomes non-practical. So we actually didn't. We did a small survey of the existing data set, and we didn't see much motion blur, but that's a different problem that we didn't solve. But again, it's like I've said before, it also depends on the temporal interpolation methods. There are methods that solve for interpolation together with blur. They try to both sharpen and solve for the interpolation. So I believe that if you can plug and play that temporal interpolation onto data sets onto rolling shutter datasets that have blur in them, then it could work on these as well.
Okay, all right. Okay, thanks, Eyal, for sharing your work. So we now move to the next talk. The next talk will be delivered by Shrisudhan. It's a ECCV paper, oral paper, with title "Synthesizing Light Field Video from Monocular Video." Yeah, Shrisudhan, you can share your screen.
Yes, yeah. So, hi, I'm audible, right?
Yep, we can hear you.
Yeah, good. Sure. And my screen is also visible, I guess. Hey, my screen is visible, right? Hello.
Hello, yep, we can see the screen.
Yeah, my screen is visible, right?
Sorry?
Excuse me. So is my screen visible?
Can you say again?
Is my screen visible?
Yes, we can see your screen.
Okay, yeah, sure. So, yep, I'll get started then. Hi, I'm Shrisudhan. I'm from Indian Institute of Technology, Madras, and I'll be giving a talk on synthesizing light field video from smartphones. So the thing with smartphones is that like most of the photography in cameras now they capture 2D projections of a rich 3D world, but then with the images we lack the images look flat and they lack the 3D structure. And also when an image is captured, we capture the image in a fixed focus and aperture, which restricts the image from like modifying the focus or aperture later that we want to. In the last decade, a new technology came where we use light field cameras to capture the 3D information from the scene. So this helps us in actually synthesizing images with refocusing applications being possible, which allows for post capture focus controls, and also synthesizing novel views, which is another way to get the 3D information out of the scene. And this is a main solution that we will be mainly looking at as a way of enforcing refocusing and novel view synthesis from normal photographic images. And when you get into videos, it's really difficult to capture light field videos because light field cameras use micro lens arrays. And with micro lens arrays, for let's say some significant angular resolution like a 7x7 angular resolution, you will be using 49 micro lens arrays, which will give you 49 times the resolution of a normal video capture. So this gives you a high data bandwidth, which will mean it is really difficult to capture a huge sequence of temporal resolution and restricts the light field video acquisition to only 2 to 3 frames in general sequence. But then, like in recent times, there have been approaches which helps us and works towards synthesizing light field videos from normal camera setups. So one such first technique is to use a litro camera and a DSLR camera in combination, where the litro camera gives you that light field image in 2 to 3 frames per second, whereas your DSLR camera runs at 30 frames per second. And the litro camera's light field is interpolated using the DSLR frames, which will finally give you a 30 frames per second light field video. The issue with this is that it is a highly bulky setup and it cannot be easily used everywhere. And another easy way to solve this bulky setup was introduced in a compressive light field camera, which used a dictionary-based learning setup, and this used a coded aperture between the camera and the lens, which was another constraint because you have to impose this coded exposure in every camera that you want to use. And one of the latest and the most attractive setup that came is using a monocular video, but then you synthesize the light field video out of it. But here the constraint is that this is mainly trained on synthetic data, which is not really good in terms of generalizing it to normal scenes, which are taken in real world scenarios. And in the mainstream, in another direction, there have been a lot of development in hardware and software technologies that are being used for cameras in mobile phones. We initially started with one camera, but then we have multi-camera setups in our phones. And these cameras also have software technology set up in such a way that you can actually capture videos parallelly from multiple cameras now. In this paper, we basically try to exploit this multi-camera setup in smartphones and try to synthesize light field videos from there. So just to synthesize light field video, what are all the important information that we need? So we need three pieces of information. One is color. We need the colors in the light field, basically a scene. And we need depth information, which will basically give you the structure of the light field that you reconstruct. And you need the temporal information, which will give you the light field video acquisition process that needs to be happening. Given these three setups, what are the two main configurations of cameras that we can consider is stereo camera, which will have the depth information from the two stereo views, and you get the color and temporal information from the video. And monocular camera, which is basically the most simple setup in a camera in a smartphone. And also you have the possibility of getting the depth information using SVM or learning based methods from a monocular video. Now we consider these two setups, and how do we learn a light field video from here? So as I discussed before, training a network just based on light field video ground truth is difficult because it is difficult to acquire light field videos. Another alternative here is self-supervised learning, which is basically what we use. So the advantages other than lack of data with self-supervised learning is that you can actually fine-tune your network on the test sequences that you want to synthesize. And you also have the possibilities of baseline extrapolation, where you can train it on one baseline and then generate light fields of various baselines. And you also have the flexibility to generate light fields with various angular resolutions. So I'll first start with how to synthesize light field from stereo videos. And so as I told before, we do it in self-supervised fashion. And one of the most crucial important part for this is low rank regularization based on tensor display model, which actually regularizes the predicted light field. First, we look into that. So what a tensor display model basically does is, it is a 3-layer stack of LCD screens, and then there is a backlight which will project light onto these screens. And when you look at this light from one different angular view, so one different angle, you will get one angular view. And when you look at it from another perspective, you'll get another different angular view. And when you look at it from a third perspective, you will get another angular view. This is basically how a light field also works. So when you look at it from different angles, you want to have different projections of the same scene. This makes it very simple, as it can be used as a regularizer directly to contribute and projecting a light field. And another advantage with this is a simple moving and multiplication operations, which makes it computationally less expensive. And after this, for imposing the constraints for predicting the light field, we basically use 3 consistency constraints. First one is photometric consistency constraint, where once we have our light field predicted, we compare it with our left and right stereo pair. So basically, leftmost predicted frame, the leftmost predicted light field frame, and the input left image is compared with each other, and the rightmost predicted frame is compared with the right stereo pair image. So this helps in learning the color information, which will be used to train our regularization model. And next is basically the epipolar consistency, where we have the left and right frame, and we learn the disparity information from this left and right frame. Once we have this disparity information, to impose a structure on the light field, what we do is we move all the predicted light field frames to the center, to the left frame based on the disparity information. So this is done using inverse warping. Once this is warped, what is expected is that this warped light field frames and the left image should be identical. So we impose this constraint, which makes sure that the predicted light field has the same geometry that is expected out of it. And finally, we do what is called as temporal consistency, where we take the current current left frame input and the previous left frame input, and we estimate the optical flow from there. So once this optical flow is estimated, you take the warped light field frames from the geometry consistency setup and move it to the previous light field frames using this optical flow that is estimated. And you expect these the warp frames from to the previous left frame and the previous left frame to actually be identical. This will enforce that there is a consistency in the temporal dimension as well in the predicted light field video. Given that this is our network and the training approach, we show some results taken, for which we capture the inputs using Google Pixel 4 image, Google Pixel 4 camera, and we show the predicted light field for the same view. Here we show a similar setup which is captured using Google Pixel 4, and we show the only output light field views which contribute to the novel view synthesis. And with this novel view synthesis and with this predicted light field frame, we actually show the applications in synthetic depth of field capture, and this is the near focus on the same video, and this is the far focus application on the same video. So to summarize with the stereo paper, what we actually understood from that is that with the use of tensor display model as a regularization framework is really crucial, because without that, directly predicting the light fields gives you poor generalization, because we are using unsupervised learning techniques, which actually needs support in enforcing the geometry of the scene. And with tensor display model as well, there is something called time multiplexing, where we predict multiple frames for the same second and then average it to get better performances. And the factor of time multiplexing is called rank, and using higher ranks gives you better performance up till a rank of 12. And this actually, we stop at 12 because it takes longer time to capture this, so to predict every frame after 12, after a rank of 12, which makes it less feasible for real-time usage. Some key takeaways from this stereo paper is that we showed a way to make sure that we can synthesize light field videos from stereo video using just self-supervised learning. And the paper also showed that low rank regularization in the form of tensor display is really good in helping us predict light fields. And this also enables us in multiple applications such as novel view rendering and synthetic depth of fields. And getting back, so our key aim is to make sure that we are able to predict light field videos, which helps us in these applications for every smartphone. And most of the smartphones support monocular cameras rather than equivalently available stereo videos. So we will now start looking at the monocular camera version, and this monocular camera version is built on top of the stereo version, which means the tensor display model and the 3 consistency constraints used are easily adapted to this, or actually adapted to this monocular video paper as well. So to start with, we made one simple improvement for the tensor display model. The tensor display model having 3 layers, these 3 layers represent one disparity level in the scene. And we understood that, like, rather than fixing it to some particular levels for the whole data set, what if we are able to move this disparity levels to each scene based on the actual objects that are there in the scene. So here we perceive the objects in the scene and then understand their depth levels and place the tensor display model based on where the objects are, hence enabling us to capture the information better. So for this, what we do is we take the successive frames from the video and then the current depth map that you want, so current disparity map that you want the light field to have, and you pass it through a mini vision transformer, which is actually an inspired network from Madabin's paper. And this mini vision transformer gives you 3 disparity plane outputs. So these 3 disparity planes are the positions in which the tensor display layers has to be placed for each scene. So once you have this tensor display layers position, we adapt the tensor display layer for that, and we actually reconstruct this light field. This helps us in solving the issue with case of easier understandable low rank representations, which helps you in better reconstruction. And other than that, we also face multiple issues that are that in terms of monocular video, which is not observed in multi-camera setups. So one of that is occlusion handling, which basically means in case of stereo, you had 2 images, and occluded pixels that are needed to be estimated in light fields can be observed from either left or right frame. But in terms of mono, you have only 1 image, and it is impossible to gather the occlusion information from just a single frame. And another issue with this is that there is no disparity scale information from just a single image, which is available in stereo or multi-camera setups. And we propose 2 changes again to adapt to these changes. So first is an explicit occlusion handling technique, which helps us in learning the occluded pixels. So our intuition basically here is that given a current frame in any temporal sense, and we need to capture the pixels that are being covered by the girl's head in and around this place. So for this, we look at the previous and the next frame. The intuition here is like once the person is moving or the camera is moving, the uploaded pixels will automatically be visible now, and you can use that to fill in this frame. So to do this, first we need to find out what are the uploaded pixels in any frame, and then only we'll be able to learn a way to fill this uploaded pixels. For that, we take the monocular frame and we warp the monocular frame based on the disparity map, disparity level that we want the light field to have in a forward warping fashion. So while doing a forward warping, we obviously will leave holes in the places that doesn't have the occlusion information. And these holes are basically the regions where we want the occlusion to be filled. So this becomes our occlusion mask. And to learn the occlusion now, what we do is we take the current predicted light field frame and the previous input frame from the monocular sequence. Now we estimate the optical flow between the previous input frame and the current predicted light field frame, and we get a light field. So, and we get an optical flow for that. And we use this optical flow to forward warp the previous input monocular frame to the predicted light field frame. So in the intuition here is that wherever there is an uploaded pixel in the previous input frame, that will be available in the forward warp frame now, and that can be used to learn the model. That can be used to teach the model to learn the occlusion. So we repeat the same for the next frame as well, because some information will be available in the previous frame and some information will be available in the next frame. And now to make the network learn this, what we do is we apply an occlusion loss, which says that whenever there is an uploaded pixel, you either look at the previous frame or the next warp frame, and look at that information. If it is there, learn to fill that. So this helps us in improving the occlusion learning problem. And to get with the next one, which is basically understanding the depth scale, what we an easy observation here is that a light field will have a better like a really good information about the depth scale when compared to monocular image. And for training a network which takes the light field as input and predicts the light field, you kind of need a data set to train it on. So what we do is we train our light field on we train a network on light field image data sets now. As we said before, it is difficult to get light field video data sets, but it is easy to get light field image data sets. So we apply a refinement block on top of the predicted light field from our recurrent network and use that refinement block to correct the depth scale information and all, which is not actually easily understandable from just the monocular video. So the way we proceed was we take the predicted light field from the recurrent network and then we pass it on to a supervised refinement block. So the supervised refinement block, what it does is it takes the predicted light field input and it applies an angular attention where it considers all the angular views of the predicted light field and understands the information from each of them and uses the information within each other to correct each other. So if an information is there in the top left angular view and if it is not available in the next view, the information in this top left angular view will be used to correct the other views. So this is the intuition here. And the advantages with this is this type of angular refinement network allows us for geometry correction where you can easily use other angular views to understand one view, and it can help you in baseline correction within data sets. And you obviously will be able to do color correction, and it will also help us in inherently solving the disk occlusion handling if it is not solved in the previous level. So the idea behind inherent disk occlusion handling is like you will be able to easily interpolate between different frames when you have the structure of the light field rather than just with a single video. So the way we do this supervised attention refinement block is we take the predicted light field frame and we crop the image, crop every angular view into 4 parts. So you take the crops and you make one particular structure out of it, and you get the top left crops from all angular views and bottom right crops from all angular views and all the other crops as well. Now you apply a ResNet block to get the feature embeddings from each of these crops. You also take the feature from the input image, which helps you in getting the color of the scene. And once you have these crops, you apply angular attention where you make sure that vision transformers learn the information from each of the angular views and modify the crops feature embeddings based on the other angular views as well. So once you have this, you reassemble the patches again to make sure that you get the angular views again, and you pass it through a decoder network to predict a mask which will be used for combining this defined light field and also a refined light field. So when you get this mask, you combine the defined light field and the predicted light field using this mask. So this will give you a final reconstruction, which is the final refined light field. So as shown here, we show like stage-wise improvement from each of our implementation. So base is basically the implementation that we directly did using the ideas given in the previous stereo work, which were adapted to monocular. And then we did stage-wise improvement where we added occlusion handling and then adaptive, and the proposed is finally with refinement as well. As shown here, like each of the stages give you some really good performance improvement, showing that each of the stages are able to handle the challenges that are being shown in the monocular work. And here I show some of the results with other state-of-the-art techniques for light field reconstructions from monocular images. Yeah. Okay, going ahead, this is an example where we show that our light field video reconstruction is more temporally consistent compared to other state-of-the-art techniques, because we use an explicit temporal loss, which helps us in guiding the network to produce better light field videos. And one of the main improvements that we did is in the terms of low rank regularization model, where we converted the simple adaptive tensor display layer to simple tensor display layer to adaptive tensor display layer. And the advantage with that is, like when you have a simple tensor display layer, you will be able to predict light fields only to a certain extent, because you have placed the tensor display layers based on the disparity level in the whole scene, so whole data set. But then when you're able to adapt the scene, tensor display layers disparity levels to the scene, this means that you can actually learn the tensor display layers position based on every input scene, which will help you in adapting it to much higher depth scales as well. So this helps us in estimating light field with higher disparity scales, and the tensor display layer will automatically find proper positioning for placing the tensor displays based on the given input disparity scale. This is shown in this figure, where you see that the red marks, which are the tensor display planes disparity levels, are being adapted and moved farther away from this from the disparity scale 1x to 2x. And as I said before, since we have adaptive tensor display layer, we will be able to predict light field with various baselines. And an application on predicting light fields with various baselines is that now we can actually use multiple baseline light fields to perform defocusing, which will mean that the amount of defocused blur can be controlled by us, which is not possible with simple supervised networks. This is a far focus of the same application. To summarize, so we basically use self-supervised learning to predict light fields from stereo and monocular work, with monocular having a refinement network, which is optional. And our proposed algorithm also allows for applications like refocusing and novel view synthesis in smartphones, which is really a good application. These are my collaborators. Thank you, and I'm open to any questions that you have.
Thank you, Shrisudhan, for the very interesting talk. And it's really exciting to see the possibility of constructing the light field video from just monocular video input. If you have questions, you can type in the chat room. While waiting for the questions, we can ask one. So your method actually requires an input depth map, and I suppose that is obtained from a prediction estimation model. That is
so for the first stage where we use stereo input, we do not take in an input depth map. But then for the second stage where we use the monocular input, we use an input depth map, and that depth map is scaled to what you want the light fields disparity to be. So you can give it in 2x or 3x fashion, that is your choice. And that depth map is estimated using depth prediction transformers network.
I see. Okay. Okay, that's a question from the audience. What is the runtime or computational complexity for your monocular light field video work?
Yeah, so for estimating a monocular light field video at 3 frames per second, we take 1 second. So that would mean that like for every predictions, we take 0.3 seconds.
I see. Okay.
Yeah.
And maybe one more question from me. So
Sure.
you are currently assuming a molecular video input. So would your algorithm benefit if we have like a dual camera setup or triple camera setup, like the one we can get from like Google Pixel 7?
Yes, so actually we are currently working on another iteration of our monocular setup where we use dual pixel input from Google Pixel 4. So that is an ongoing work which we do not have much like complete setup as of now, but we are currently working on it, and we believe that that could give better results when compared to just a monocular input.
Okay. Okay. Probably what the last question we have here.
Sure.
What do you think the major benefit and difficulty of novel view synthesis from molecular video comparing to that from single image?
Depth from single image compared to monocular. Okay, novel view synthesis. So with novel view synthesis from monocular video, as I said before, you have more information in terms of the video sequence where you have motion and all these things. If you do not have motion, you do not benefit much from just a static scene. But if you have a moving scene and a dynamic scene, that actually helps you in getting more information, which will help you in better novel view synthesis application, which is not possible with just a single image. So that would be one of the main advantages with having a video rather than just a single image, as far as I know.
Okay. Okay. Thank you, Shrisudhan, for the very nice talk. So let me share the schedule. Okay. So we have finished the first session here, and we are entering the tea break. So because of the slight delay, then we still have our next sections starting at 11:20, and we will have two winners of the different of two tracks to share their winning solution, and we have two invited talks before our lunch break. So we'll see you later at 11:20. Okay, so basically 5 minutes later. Okay.
Welcome back to MIPI workshop. Doan, are you there?
Yes.
Okay.
Can you hear me?
Yeah, yes. Okay, our next speaker is Dewan Hou. Dewan is a student with Peking University. He will present the winning solution on top depth completion track. Dewan, the floor is yours. You can start your presentation now.
Oh, thank you, Professor. Hello, everyone. My name is Dewan. I'm from Peking University. Today, I'm going to give a presentation on our solution for RGBD depth completion, learning an efficient multimodal depth completion model. There are four main aspects to this topic: the background, our methods, our performance, and finally, a brief summary. Let's move on to the first part, the background. Why did we choose this item? As you can see, depth information can be used for many downstream tasks. It can be obtained in many ways, but a few can directly obtain dense and accurate depth maps. So we need a depth enhancement or depth completion algorithms. Now, for this computation, the depth is obtained through sparse time-of-flight sensors. It has several benefits: lower power consumption, higher energy of each laser beam, and avoid multipath interference. Finally, it is affordable. However, it is extremely sparse and still noisy. There are a dozen of algorithms that can be used to calculate the depth measured by time-of-flight sensors. Among them, the method based on RGB image guidance is the mainstream and has better performance. But there are still some major concerns here when designing the algorithm. First, multimodal fusion problem. Second, heterogeneous distribution problem. Third, structure preserving problem. We will now come to our methods for these problems. First, look at the overall structure of the neural network, mainly including global depth prediction branch, local depth prediction, and the depth refinement part. Let us first focus on the global and the local depth prediction part. The input of the global network is RGB image and spot depth. In the encoder of the global branch, we use pre-trained MobileNet V2 because we want a lightweight structure and want to obtain strong learning capability. In the decoder, we use pixel shuffle instead of bilinear, as it don't magnify the missing value areas in spot depth map, as you can see here. And for the local network, the input is global depth prediction and spot depth. Since the inputs are simple homogeneous depths, we use only a few convolutional layers in this branch. And we also remove batch normalization layers here. Once we got a global and local prediction, how can we fuse these two feature maps more reasonably? Here, we adjust the pathways of the features to reflect the relative certainty of global and local prediction directly. Further, we improve the relative fusion module by re-zero mechanism, which can achieve faster convergence and better results in our experiments. The visualization results are as expected. For example, in areas with missing depth measurements, it is more confident to predict the depth based on the RGB image of the global branch. We will also calculate the losses on the global and the local prediction here. At the same time, we set the weight of losses in a way that two branches are trained almost synchronously. This makes their value to be the same. And in this way, we can prevent model mismatches. We also designed a funnel-shaped convolutional spatial propagation network for depth refinement. This is nothing new. We surveyed from the historical context, from locally connected layers to kernel prediction network, and then to spatial propagation networks. And finally, this is our proposed propagation network. Limited by the time available, we will not go into detail on it. What we do, we just list here. We forming kernels with different dilations and updates kernels. And more importantly, we implement it with a faster speed. Next, I would like to turn to an introduction to our loss functions, especially the last item here, the gradient loss. Gradient loss was originally proposed to preserve the structure of natural images. Intuitively, it is also helpful to refine the blurry prediction obtained from MSE loss. However, the gradient between unreachable, such as the red regions, between the unreachable areas and the other areas, is unreliable and even reversed. Our approach is to fix this problem. And as the third section, I shall show some results here. First, our method achieves real-time on NVIDIA graphics. But there is still a long way to achieve real-time on CPU and integrated graphics. And this is our results on real data. As you can see, we have more details, and for the platform, we have a smooth result. Here are more results showing our good generalization capability. This one is our results. We will discuss the many points today. Let me quickly summarize the principal points. First, for the model, we design a better fusion module and a funnel convolutional spatial propagation network. For the losses and the training, we design a corrected gradient loss. And when training the network, we set the loss weights to prevent model mismatch. Finally, our performance shows our model has a better generalization capability. And thanks for your attention.
Thank you for your presentation, Dewan. I have a very quick question. The format said for the top depth completion, the challenge part is how to align the RDB and top depths, and how in your work how to deal with this issue. I mean, how to align the RDB feature and the top depth feature. I saw you just use the concatenation in your fusion block. Is there any other trick or the techniques for this issue?
Oh, for this part, we just concatenate them because we want a better speed performance. But we use a later fusion mechanism, and when we fuse those feature maps, we first we use the ReZero mechanism, and it can help us help the model to converse faster.
Okay.
And yes.
Thank you, Dewan.
Thank you.
Okay, now we move to the next presentation, and our Dewan, you can stop the sharing. Okay.
Yes.
Our next speaker is Chen. Ling Chen is with Oppo Research Institute. She will present the winning solution on quad-bear mosaic track and RGBW sensor mosaic track. Ling Chen, the floor is yours. You can start your presentation now.
Okay, can you hear me?
Yes.
Okay. Hello, my name is Ling Chen, and It is my honor to represent the team to give a presentation. The members of the team are Sunling Chen, Wu Rongyuan, and Yiqiao Si. The name of this presentation is Your Resnet for Joint Remosaic and
Sorry,
Denoise.
Chen. Sorry, I'm sorry. Can you share your screen?
Okay, you cannot see my screen.
We can't see your screen.
Okay, I share my screen again. Sorry. Can you see it?
Yes, yes.
Okay, sorry.
You can start your presentation.
Yeah. The name of this presentation is Your Resnet for Joint Remosaic and Denoise. We are all from Open Research Institute. The presentation is divided into 3 parts, including image signal processing in camera system, CFA pattern and low light conditions, and the applied methods and results. Image signal processing is the process of obtaining images from the image captured by the sensor in the digital camera device. When the image is captured, the noise exists, mainly including red noise and short noise. The red noise of the sensor is the equivalent noise level at the output of the camera in the dark and at 0 integration time. The short noise is from the discrete nature of electrons. These 2 types of noise are signal dependent and signal independent, respectively, so the denoising operation is necessary. To reduce the size, complexity, and cost of a camera, most digital cameras use a single sensor capped with a color field array that is CFA. A CFA is a physical construction which has the same size as the sensor image and allows only 1 color component to be sensed at each pixel. The procedure of reconstructing a full color image by estimating the missing 2 color components in each pixel is called demosaicing. The subsequent white balance is performed to ensure that same objects appear as the same color, even when imaged under different illumination conditions. So white balance is intended to normalize the effect of the captured thing's illumination so that all objects appear as if they were captured under ideal white light. So then the color space transform is used because the color space of the camera mismatch that of the human visual system. The same as the color space, the luminance of the camera also mismatch that of the human visual system. So the gamma correlation is required. Mapping operators can compress the range of HDR images so that they can be displayed normally on the LDR devices. Finally, the processed images are saved. The most commonly used CFA is Bayer CFA, as shown in this figure. It was designed based on the human visual system that is more sensitive to green channels. So sample rates for green, red, and blue are 1/2, 1/4, and 1/4 respectively. But when in the low light condition, its performance gets worse strongly. So based on the classical Bayer CFA, other CFA patterns are designed. To enhance the image quality in low light condition, there are many ways to design a stronger pattern. We categorize them as integrating more pixels and increasing sensed light. For the first type, the code Bayer is the representative pattern. Its binning mode is used under low light to enhance image quality by average 4 pixels, But with this operation, the spatial resolution is also reduced. So the remote sec operation can be applied to directly get the full resolution Bayes pattern. And for the first type, for the the second type, the RGBW and IYYB patterns are representative because there are some pixels can sense more light, so that the quality of the collected image in the low light condition becomes significantly improved. Also, to adapt to the Bayer ISP, the remote sec operator should be applied. So in this challenge, we need to do jointly remote sec and denoise for real-world applications. To be more specific, the input is the Coda Bayer or RGBW mosaic images, and the designed joint mosaic and denoise network is used to output the clean Bayer mosaic images. Then the output images are put into the other ISP operators to obtain the final sRGB images. The evaluation standard consists of the comparison of the mosaic output and the GT Bayer, and the comparison of the RGB image from the predicted and GT Bayer using a simple ISP. 4 metrics are used, including PSNR, SC, KLD, and LPIPS. PSNR measures the fidelity of the reconstructed image, which accesses the pixel-wise accuracy. And SC, KLD, and LPIPS are used to measure the perceptual quality, which are related to the distribution of natural images and the human visual quality. So this combined metric can provide complete evaluation for the performance. So this is the task that we should do in this challenge. And fortunately, we won first place in 2 tracks. Before the detailed methods, we asked ourselves 4 questions. The first is, what are the differences between these 2 tasks? The main difference is the CFA pattern. There are also RGB channels in the Coda Bayer, so the color sampling rates of the Coda Bayer for green, red, and blue are the same as that of the Bayer pattern. But for the RGBW, there are half of the pixels that sense the luminance. The color information is missed, but the luminance information increases at the same time. Therefore, we may leverage the enhanced details in RGBW. So the loss function we designed for the Coda Bayer pattern is L1 loss function for both raw and sRGB domains, and also a LPIPS loss in both domains for the RGBW pattern. Through the experiment, we found that the LPIPS loss can help the RGBW remote sec improve performance significantly, but there is almost no improvement in Coda Bayer pattern. The third question is, what are the differences between the forms of the input? We conclude 3 input forms generally. The first input is the full resolution mosaic image. The second input is splitting the mosaic image into 4 low resolution image. And the third input is restoring the 4 resolution images by interpolation. They all have their specific drawbacks. The RGB channel of the first input mismatches with the output, and the pixel deviation exists in the second form, and the interpolation leads to details loss in the third form. It is quite difficult for us to analyze which input form is the best, but through experiment, we found surprisingly that the first form gets the best performance, which may mean that the channel mismatch has minimum bad effects. The last question is, what is the network architecture that we really need? This is the task that joined Remosaic and Denoise. For the Denoise, it is the U-shaped network that obtains the great performance from the expert experience. This is because the U-shaped network can enlarge the receptive fields. That is very important in Denoise task. Furthermore, a simple but effective rest block and skip connection are introduced. In conclusion, the combination of the U-shaped network and RESTnet, that is, the U-RESTnet is applied for both tasks. These are the numerical and visual comparison with other teams in both tracks. So that is all our presentation. Thank you.
Thank you, Liu Chen. I have a quick question. First, I congratulations on winning two champions. My question is, what's the key point for winning two tracks? I mean, what's your most important design in your pipeline or your frameworks?
Okay, actually, we have done many experiments about these input forms. I mean, there are many input forms that we can use instead of these 3 input forms. But we found that the first form is very important. That means the pixel deviation and details loss are have the bad effect in the final performance. Yeah, so this is the most important part.
Okay, I see. Thank you, Lin Chen.
Okay, thank you.
Okay, we have a question from audience. The question is, what kind of augmentation did you use?
Augmentation?
Yes. Data augmentation.
One-way inference. We use some inputs of augmentation, such as flip, rotation, and just it is the very usual augmentation.
You mean you just use rotation, right?
No, rotation, flip.
You mean rotation and flip, right?
Yeah.
Okay. And there is another question. How you deal with noise with different levels?
Actually, when we train our network, we directly input all level noisy images. Yeah, we do not use some special observation about the different levels noise. Yeah.
And okay, that's all for the. Okay, that's all for the question.
Thank you.
Thank you, Lin Chen. Next speaker is Zhihang Zhong. Zhihang is a student with the University of Tokyo. He will present his work on the animation from motion blur or rolling shutter distortion. Zhihang, are you there?
Yeah, can you hear me?
Yes. The floor is yours. You can start your presentation.
Okay, can I share my screen?
Yes, you can share your screen.
Okay, can you see my screen?
Yes.
Okay. Okay, hello everyone. This is Chen Hanzong from the University of Tokyo, and my supervisor is Professor Imari Sato. So first, I'd like to thank the organizers of MIPI workshop for having me give a talk about my current research. I will present two different works and this topic, animation for motion blur or rolling shutter distortion. Namely, one is about motion blur and the other one is about rolling shutter distortion. Okay, so first is about the introduction. We believe that motion artifacts are not always the bad things. On the contrary, they have temporal image information. Motion blur can be considered as the result of averaging consecutive sharp frames of short exposure times, like the left figure. And similarly, each line of the pixels in the rolling shutter distorted image corresponds to partial information of the group shutter for that instance, like the right figure. So that's instead of treating these motion artifacts, motion blur and rolling shutter distortion as nuisances, we extract the video clips from low quality images by fully utilizing these artifacts. We call the inverse process of motion blur as blur decomposition. And in the case of rolling shutter distortion, we call it rolling shutter temporal super resolution. Yeah. Then first, let me introduce our first work about motion blur. The title is Animation from Blur Multimodal Blur Decomposition with Motion Guidance, and this one is accepted by ECCV as a poster. Yeah. Commercially, the deblurring task is treated as a one-to-one mapping problem. It takes a motion blurred image or maybe video sequence as input and produce a single output image for each blurred image. So you didn't increase the FPS one-to-one mapping problem. And recently, attention has been drawn to a more challenging problem of extracting an image sequence or video clips instead. We name it as blur decomposition, as shown in the both figure. And about the existing challenge in the blur decomposition. Blur decomposition from a single blurry image now faces the fundamental problem of directional ambiguity. Each independent and uniform motion blurred region, like the hand, maybe the legs of a human, can correspond to either forward or backward motion sequence. So this directional ambiguity will result in an expansional increase in the number of potential solutions for blur decomposition. Yeah, maybe you have 100 possible solutions for single blurred image to do the blur decomposition. However, existing methods for blur decomposition are designed to predict a single solution. Yeah, this directional ambiguity may, not only brings stability to the training process, but also leads to poorly diversified and low quality results. Okay. And therefore, we propose a novel motion guidance representation, hope to address this directional ambiguity problem. The motion guidance is, in our case, is optical flow representation, quantized into four major quantitative directions, describing the motion field roughly. Given the inputable image conditioned on the motion guidance, the blur decomposition then becomes a nearly deterministic mapping problem. The rough information for direction. So the network does not need to guess the direction. So this problem becomes without directional ambiguity. So in addition, we propose a two-stage network to predict the image sequence. The first stage, expands the blurry image into the image sequence. based on the motion guidance. And the second stage, it will refine the visual details in a residual fashion. Conditioning on additional guidance include the decomposition network shows significantly by the tuning convergence, as shown in the right figure. The blue curve is without any additional input motion guidance, and the right curve is with additional motion guidance. Okay. And due to the compactness of motion guidance representation, our unified framework only need to be trained once while supporting various decomposition scenarios and different modalities. Specifically, like we provide 3 interfaces to get motion guidance. First, we train a network to predict the possible motion guidance. And second, maybe we can get the motion guidance from the video by estimating the optic flow. And last, maybe the interface can, provided by the users, and the users can enjoy the annotation by themselves. And regarding the guidance prediction network, we mainly follow the CVA Gantt model length and guidance distribution. The encoder will project the ground truth guidance into the potential guidance space and use the KL loss to approximate the space to a normal distribution. And the generator will combine a sample length embedding with the Deblurring input to produce a possible guidance. That's in the inference stage, we can generate different guidances by sampling different embeddings from this normal distribution. Okay, let's see some video results of our pipeline. First, we use the same sample and present the results by using different interfaces of our framework. So giving the same blur image, different motion guidance can generate different results. Yeah, and we show some results on the synthetic data side. Giving a blurry image, our method can generate multiple physically plastic motion guidance and recover the distinct sharp image sequence based on each motion guidance. More samples. Okay, and then giving a blurry video, the deterministic decomposition results from our method still outperform the previous state of the AF method. Finally, we show some results on the real-world data from the model training using the synthetic data side. And the annotation is provided by the users. Okay, and in addition, we'd like to show some experimental results about the robustness of our method. We found that our model may tolerate the guidance errors in the sharp regions. We demonstrate this by showing results using fit, dilated or eroded guidance, as shown in the above figure. And also, On the other hand, we using the proposed guidance predictor. Our method can generate multiple possible solutions, owning sharp details for real-world data. Okay, then let me introduce the other work named Bringing Shot Images Alive with Dual Reversed Distortion. And this one is accepted by ECCV as an oral presentation. As I mentioned in the beginning, rolling shot distortion can be interpreted as the result of picking a row of pixels from the instant global shot frames over time during the exposure of rolling shot camera. This means that the information of each instant global shot frames is, partially gets sequentially embedded into a row-dependent distortion. And inspired by this factor, we aim to address the challenge test of reversing this process, namely extracting distorted global shot video clips from rolling shot images. Yeah, that's the background. And the important thing is here, we propose a dual reversed rolling shutter setup, especially for this test. The differences between our setup F with other tests like A, the normal video frame interpolation, B, rolling shot correction, C, dual rolling shot correction, D, blur decomposition, as we introduced in the last work, and E, rolling shot correction and interpolation, can be summarized as this figure. Then the question is why we need dual reversed rolling shot setup. The motivation is for the rolling shot correction and beauty problem. Suppose there are two similar cylinders and one of them is tilted, the bottom one. Then the two rolling shot cameras moving horizontally at the same speed but with different readout time setups can produce exactly the same eyes image as shown in the eyes view. Yeah, the eyes view is exactly the same, but the GS view is different. Therefore, the models, that take consecutive frames as input, say using data taken by the camera above to the rolling shot correction, actually do not know how much correction is suitable, is correct facing the data beyond the training data side. For images taken from the bottom camera, the model will overcorrect the image. Yeah. However, dual rolling shot images taken simultaneously, but with reversed distortion, can avoid this kind of rolling shot correction ambiguity, because the correction pose can be estimated based on the symmetry. Yeah. As you can see in the right figure. And accordingly, we design a model for this setup. We propose a dual time cube as the rolling shot prior, requires the dual velocity cube to indirectly estimate the dual optical flow for backward mapping, because directly estimating the optical flow is very difficult in the case of rolling shot images. Then we try to efficiently merge the symmetric information using a encoder-decoder branch to extract the potential global shot frames. Yeah. As shown in the visual results, previous method cannot generalize to the case of the camera-only motion, the left example, or the case of the object-only motion effect in the right example. But our RSA is robust to the different motion patterns. And grounded on the symmetric and complementary nature of the dual reversed distortion, our method can successfully generalize to different readout sightings without artifacts and anti-sign distortion like the previous method like DUN. Yeah. Then let me show the video results for the reference. And first, it's the case on synthetic data. The left half is the mixed input images with dual reversed distortion. and the right part is the extract video clips from the two reverse icing images with different distortion. Yeah, then it's the cases on the real world data. We customized the spatial camera system with two rolling shutter cameras at different scanning directions used with a beam splitter to capture the real world data. Okay, then let's go to the conclusion. We exploited the unique imaging properties of specific motion artifacts to achieve visual enhancement of low quality photos. In the task of blur decomposition, we propose a novel motion guidance representation that makes the training process deterministic and more convergent, and provide multimodal decomposition interfaces. And in the test of rolling shutter temporal resolution, we propose the dual reverse distortion setup to overcome the correction ambiguity problem and achieve byte generalization and visual parity. Okay, that's all. Thanks.
Thank you, Zhihang. Thank you for a nice talk. I have a question for your first work. Is very interesting.
Sure.
I'm curious about what's the practical application for the motion blur decomposition?
Yeah, that's a good question. So basically, you can understand this is a kind of the joint task. Today the deburring task, they treat this problem as a one-to-one mapping problem. So you deblur the inputted video or image, but you ignore the potential temporal information embedded in the blur. But in our case, we can not only deblur the video or image, but also increase the temporal super resolution, the frame rate of the video at the same time. Yeah.
Okay. Thank you, John. There's a question from audience. The question is how to synthesize RS dataset. I mean, how to synthesize RS dataset.
The next for this one, right?
Yeah. Yes.
Yeah. If you want to create the synthetic dataset, yeah, the idea is maybe you can use the pipeline like this. You can first get some videos with very high FPS, say like 240, something like this, and you can use existing video frame integration method to further increase the FPS. Then to synthesize one RS image, for example, the height is we have 640 lines of pixels, then you need to use 640 interpolated group sharpening image. For each one, you can pick one row of the pixels to synthesize this kind of data set. And in case of real world data, yeah, we have a plan to create a real world data. So in that case, you need align two rolling shutter cameras with different directions, and also maybe you also need a third camera to capture the high FPS group shutter image. So that will be quite complicated. You need very high, physical, precising when you do the alignment. Yeah.
Thank you, John.
Yeah, you're welcome.
Okay, let's move to the next presentation. Our next speaker is Lei Sun. Lei is with the ETH. He will present his work on event-based fusion for motion deblurring with cross-module attention. Lei, are you ready?
Yeah, I'll share my screen.
Okay.
So can you see my screen now?
Yes, I can see your screen.
And okay, should I open the camera, the front camera? My computer?
It depends on you.
I see. Okay, thank you, Chongyi. So let's start. Hi everybody, I'm Lei Sun, and I'm glad to be here to share our work named Event-Based Fusion for Motion Deblurring with the cross-modal attention. It is a joint work by Zhejiang University, ETH Zurich, KIT, and KU Leuven. It's the same topic like deblurring with the last work, but we use like different methods or sensors. Yeah, firstly, starting from the background, is traditional frame-based cameras suffer from motion blur due to the motion within the long exposure time. Camera shake and object motion are two typical causes for motion blur. Here we show two blurry images and corresponding event strengths. Events encode information which is related to the motion in the image, and therefore they can be useful for motion deblurring. So please allow me to briefly introduce the basics of event camera so that we can then move on to presenting our event-based method for deblurring. So unlike frame-based camera, which record images at a fixed frame rate, the event camera records the intensity changes in an asynchronous way with high temporal resolution, which is in the order of microseconds. The high temporal resolution of event cameras provides valid image motion information within the exposure time. And the motion information actually indicates how the image gets blurred. So all the advantage of the event camera makes it a perfect choice for image deblurring. Based on the principle of image blur and the mechanism of event camera, the event-based double integral method calculates the intensity of the latent sharp images by accumulating probabilities of events, and they optimize the contrast threshold value by minimizing an energy function. But it cannot deal with the sensor noise and especially variation of the contrast threshold, which is the natural drawback of the event camera. And some learning-based methods combine events with flow, but the estimation of optical flow already introduced error. We believe that the event stream already encodes the process of image degradation. So we focus on studying how to fuse events and the images effectively through a neural network. So the ideal formulation of physical model for event-based deblurring accumulates a probability of events and calculates several latent sharp images within the exposure time. And the average of these latent sharp images is the blurry image. So we can model the relationship between blurry image, sharp image, and corresponding events with an equation. But this is not suitable for real-world image blurring because the contrast threshold of event camera changes, and the intensity changes that are lower than the threshold do not trigger an event, and the spurious events occur over the entire image. So we revisited the model and formulated it with neural networks and approach the deblurring method, a deblurring problem as an deblurring plus denoising problem, and decide to refine the result with the second stage, So firstly, the CNNs only process synchronous signals, which is incompatible with the event stream. To feed the CNN with asynchronous event stream, we designed a symmetric cumulative event representation, or SCR. It accumulates the plurality of events. The accumulation starts always at the middle of the exposure time and ends at symmetric time stamps around the later. This image shows the construction of SCR, and the smaller figures below are the visualization of each channel of SCR. It still holds temporal information as the endpoints of the time interval in which events are accumulated different across the channels. So this figure shows the architecture of our proposed event fusion network, or EFNet. Our model is a two-stage model and consists of two UNet-like blocks. And in the first stage, we fuse the event feature maps and image feature maps at multiple scales. We designed the event image cross-model attention module to fuse the event and the image effectively. We also proposed the event mask-gated connection module to connect the first stage and second stage. So the first stage models the physical model of event-based deblurring, and the second stage refines the results from the first stage to handle the drawbacks of the physical model, like sensor noise, like spatially variance threshold. The previous methods merely concate or multiply event future maps with the feature maps from the image. However, these method solutions are not enough to model the long-distance dependencies between feature maps from both modality. Hence, we propose event image cross-model attention fusion to apply cross-model attention. But for the image restoration task, with high resolution feature maps, vanilla multi-head attention takes too much memory, and we choose to transpose the queries from the image branch and apply multi-head attention. By this means, we can reduce the computational cost from the square of H times W to the square of C, and we place the ACCA model after each rest block for multi-scale fusion. And another thing that we observe is that the areas with events, which is the white part in the binary mask, are usually more blurry than the rest part of the regions. This is an accurate prior about the shape information of the blurry areas. So we design an event mask-gated connection between stages and between encoder and decoders. So sharp areas from the encoder, which are more close to the input, and the blurry areas from the decoder, which are better restored, are combined and connected to the second stage. So here we do ablation studies to verify the beneficial of each component of proposed method. As we can see in the introduction of events improves the performance substantially. And our proposed two-stage model and event image cross-model attention module also contributes about 0.6 dB of PSNI improvement, and our MMGC Eyal's improvement of 0.15 of PSNR, and by only introducing 0.87 million additional parameters. And we also compare our different event representations based on our proposed network. And it is interesting to see that if we just accumulate pluralities of event across the entire exposure time, which is called the stack in the right table, the performance decreases compared to the image-only baseline. So how to represent the event is very crucial for most event-based motion deblurring. And we train our network on the global dataset with synthetic events on this benchmark, our methods pass the previous both image-only method and event-based methods. So here we show some qualitative results. We compare our model with state-of-the-art image-only method and event-based methods, and our model performed better, especially in the situation with rich textual information, like license tag in the figure. So the visualized score shows the motion in the exposure tag, which encodes the motion information, and it helps to restore both high and low contrast areas. So one problem about event-based deblurring methods is the lack of the real-world dataset. So to evaluate the proposed method on the real-world dataset, we collect a new dataset, which we call real events blur dataset, or RE blur. So this is a relatively small blurry image dataset with corresponding real events using an event camera that outputs gray images and events at the same time. So we fine-tune model on the reblurred and to evaluate the performance on real-world blurry scenes. So our method also achieves sort-of performance on our proposed RE blur dataset, which shows the effectiveness of EFNet on both synthetic and real-world datasets. Here we show two videos about comparing our method to RGB-only baseline. So both methods are trained on GoPro and fine-tuned on RE blur, which is a real-world dataset. And as we can see, the image-only method failed to deal with the blurry scene, especially the extremely blurry scenes in the real world. And our event-based deblurring methods perform robustly, both for fast object motion conditions and intense camera shake. Okay, the conclusion part. In this work, we have looked into single image motion deblurring from the perspective of event-based fusion, and we introduced EFNet, an end-to-end motion deblurring method with attention-based event image fusion model applied at multi-level of the network, score a novel event voxel orientation, which is especially designed for the motion deblurring, and I built a real-world dataset for event-based image deblurring, which provides a challenge evaluation setting. So that's all for my presentation, and thank you for your attention. Yeah.
Any questions? I can ask a question. Like,
yeah.
My question is, I saw you use a vanilla transformer block in your method, right?
Yeah, I didn't use vanilla multi-head attention mechanism because it costs too much memory to train on. Yeah.
Is this the first work using a transformer for event motion deblurring?
Yeah. In the event-based motion deblurring field, it is, but it's also like initial idea is also from the NLP, which is called transpose mode attention, which you transpose the attention map to reduce the computational cost. Yeah.
It seems this kind of transformer structure is very suitable for event deblurring, right?
Yeah. It models the long distance dependency in both modalities. Yes.
Okay. Thank you.
Yeah. Thank you. Thank you for organizing this workshop. Thank you.
Okay. If there's no questions, now we will have a break and come back soon. Dongji, the floor is yours. Yep. You can start your presentation now. I can see your screen, Dongji.
Yep. Sorry for the delay. Hello, my name is. Can I start the presentation?
Yes, please.
Yep. Again, sorry for the delay of the presentations. And my name is Dongja Lee from KAIST, and I participate the MIPI challenge for the RGBW joint fusion and denoising track. And before starting the presentation, I really appreciate to the committee of the challenge for their great and hard work. So the RGBW joint fusion and denoising track is the test for the convert or the RGBW raw data into the Bayer format so that it can be processed with standard ISP. So the given Bayer pattern and white pixels, the network generate the denoised Bayer patterns. So this is the overall architecture of the method that I used for the challenge. The method I used for the challenge is composed with the Reconstruction and test time local converter. Reconstruction is the transformer-based architecture for image denoising and deblurring, and test time local converter is for the reducing the gap between the training time image size and test time image size. So what I really focus is not the network architecture itself. So I didn't really change the network and just feed the given RGBW image into the 8 channels and fed to the network and generate the denoised Bayer patterns. What I really focus is the data sets. So the provided RGBW training data sets is only consists of 17 scenes. So it is too small for the training network, especially for the transformer-based architectures. Another problem is there are no other public large data sets for the RGBW denoising test. So I tried to synthesize the new RGBW datasets from the regular Bayer pattern denoising datasets, specifically the SIDD datasets, which is largely used for the denoising task. So again, the provided RGBW dataset is too small, so the training neural network-based generation network is hard. So, and considering that the white pixel spectral contains each RGB channel spectral, I use simple linear regression methods for generating the white pixels. So the 4 white pixel is generated for paired regular Bayer patterns, BGGR, and used for the synthetic data sets. And in details, what I have is 24 decibel and 42 decibel noisy RGBW and GT Bayer patterns. So I don't have any white pixel ground truth, so I assume that 24 decibel white pixel is the ground truth white pixels, and pair with the ground truth Bayer patterns, I calculate the coefficient with linear regressions. For the synthetic data set, I use SIDD data sets and specifically the 20,000 scenes with normal exposure. So the white pixel is generated from the below equations, and for synthetic noise, I add the Gaussian noise to the Bayer patterns, and considering that I used noisy white pixel as GT ground truth white pixels, I add some Gaussian noise to the coefficient itself. So for the experiment details, I use random flip, rotation, conmix, random crop, and I train the aforementioned model with synthetic RGBW datasets and fine-tuning on the provided datasets. So this is the experiment result for the synthetic and provided datasets. So the experiment is conducted before the validation set is open. So I divided the training sets into 60 scenes for training and 10 scenes for the validation. So the below table shows that using synthetic dataset pre-trained model shows better performance compared to using only the provided datasets. But comparing with other denoising tests that use some pre-trained large datasets, some large dataset pre-training models, the performance increasement is quite small because I used the 24 decibel noisy white pixels and as ground truth white pixels. So pre-training on the synthetic datasets means that pre-training on the really noisy datasets. So the performance increasement is quite small. And this is the result from the test set, and this is from the official report. So as you can see, the table shows that proposed method shows first rank on the challenge, but the limitation is that proposed network is too complex and large for the mobile device. So for the right table, you can see the running time on Tesla VBAG. So thinking that the workshop is for the mobile intelligent, proposed model is incompatible to the mobile devices. And this is the qualitative result from the official reports. And as you can see, the proposed method shows better performance compared to the other methods. And this is the end of the presentations. Any questions?
Thank you for your presentation. There is a question from audience. How did you convert SIDD data to RGBW?
So like I said, with
I can repeat the question. The question is, how did you convert SIDD dataset to RGBW?
Yep. So as I can say, for the noisy white pixels and paired ground truth Bayer patterns, and calculate the linear regression coefficient for the ground truth Bayer patterns. So sorry, I have to say again, with the noisy white pixels and ground truth Bayer patterns, I calculate the coefficient for the white pixel generation. So each coefficient is multiplied to the each pixel's value and generate the white pixels.
Thank you, Dongji. Any question? Now we move to the next presentation. Our next speaker is Qiao Si. Qiao is a student with the East China Normal University. She will present the winning solutions on the RGBW sensor remote sick track. Qiao, the floor is yours. You can start your presentation.
Oh, yeah. Oh,
I'm sorry. He will present the winning solutions. I'm sorry.
Wait. Can you see the screen?
Yes.
Okay. Hello, everyone. My name is Qiao Si. It's my honor to represent the team to give a presentation. In this challenge, our team participated in the text of RGBW, joint mosaic and denoising. The other member of the team are Rongyuan, Lin Chen, and Fami, who are from Oppo Research Institute and East China Normal University. The name of this presentation is UNET Transformer for RGBW joint mosaic and denoise. If you are interested in our work, you can follow our work by visiting the blog link. The presentation is divided into three parts, include the background, the method, and the experiments. Next, we will introduce the background. The background, we will introduce the RGBW joint mosaic and denoising task. The main purpose of this challenge is to convert the RGBW image acquired by the sensor into a blur image. In addition, since the captured image may contain noise, we also need a denoising step in this procedure to obtain a clear blur image. After obtaining the blur image, we can display the image through the conventional ISP pipeline. It mainly contains data normalization, interpolate, Welt balance, gamma correction, and so on. During the denoising and the demosizing may lead to loss of information. So why do we use RGBW sensors? We list the proportion of RGB and W in the RGB W pattern and Bear pattern. From the table, we can obviously find that compared with the Bear pattern, RGB W pattern had a very significant advantage. That is, the proportion of W is higher, while W is the white pixels in sensor, which don't add any color filter. In addition, white pixels contains light of various wavelengths and have a higher optical transmittance than conventional red, green, and blue pixels. Thanks to the higher optical transmittance of white pixels, the signals to noise ratio of the PI of the sensor output becomes significantly improved. Thus boosting the image quality, especially under low light conditions. So at present, some mobile phone manufacturers have begun to use the RGBW sensor to capture image. Since the RGBW demosaic pipeline is incomplete, it's necessary to RGB remosaic step. And then we will present our proposed method UNet transformer. Since the noise may exist in both high frequency and low frequency information, our proposed method adopts the UNet structure. Meanwhile, in the image restoration task, global information is very important. Therefore, we proposed a UNet transformer network, which is able to run the local and global information simultaneously. As shown in the figure, our proposed method adopts a encoder and decoder structure and have 4 levels with 64, 100, and 28, 256, and 512 channels respectively. In each level, we design a multi-res transformer block to mapping feature. The multi-res transformer blocks concate the multi-res transformer IEST blocks, which can study local and global information simultaneously. The structure of IEST is illustrated in the figure. In the IEST, the first 2 convolution layer will adopt to study the local information, and then we employed a multi-head self-attention to learn the global information, while R is the reshape operation. In addition, to estimate a clear Bear image from the corresponding RGBW image, we decrease the distance between the output and the ground truth raw Bear image by minimizing LE loss. Next, we will introduce the experiments in detail. First, we will introduce the data generation procedure. Since the paired RGBW and the Bear image are difficult to obtain, the challenge adopts the way of data synthesis to generate the paired data. The data is generated as shown in the figure. Firstly, the RGBW raw data is captured using a RGBW sensor and cropped to be a size of 2,400 by 3,600. A Bear and a white image are obtained by averaging the sun color in the diagonal direction with a 2x2 block. Then we demosaic the Bear to get a RGB using the demosaic net. The white is concatenated with to the RGB image to have RGBW for each pixel, which is in turn mosaic to get the input RGBW and align the ground truth Bear. By this way, the generated training data include 70 paired image, validation data and testing data include 15 paired images respectively. In addition, the noise is added, which consists of read noise and shutter noise. And then we will introduce the results on the testing datasets. The evaluation consists of the comparison of Bear image with the ground truth Bear and the comparison of the RGB image generated from the output Bear and the ground truth RGB image. The PSNR SIM and LPIPS are computed in RGB domain, and the KLD is computed in barren image. Moreover, the final score is computed by M4, which combine the PSNR SIM, KLD, and the LPIPS. From the table, we can see that all proposed methods I choose the second place in M4 index. Although achieve the better performance, all proposed method consume more time than other method, since the self-attention is introduced in all proposed method. As shown, we illustrated some results generated by all proposed method with different noise. From the figure, we can find that all proposed method can generate a present result from different noise image in some things. Albeit all proposed method can achieve better performance and generate a present results. All proposed method still exist some shortcomings. First, because of using the transformer in our proposed method, all proposed method consumes longer time than other method. In the future, some efficient and effective operators should be designed to run the global information. For example, the pouring transformer is effective than all used. Second, the proposed method cannot adaptively handle different levels of noise. When the input has a large amount of noise, the generated results change to over smoothing and loss a lot of detail and texture. In the future, we can firstly learn the noise prior and then use this prior to guide the noise denoising and demosizing. Third, the output image contains chiral artifacts, which is a troublesome problem. That's all my present. Thank you for your listening.
Any questions? Okay, let's move to the next presentation. Thank you, Xiaosi.
Oh, okay. Thank you.
The next speaker is Yurui Zhu. Yurui is a student with the University of Science and Technology of China. He will present the winning solutions on the display camera image restoration track. Yurui, the floor is yours. You can start your presentation now. Yurui, are you there? Hello, Yurui.
Hi, Ray. I think you should unmute your voice.
Let's wait Yurui for a moment.
Okay, I'm coming.
You can start your presentation now, Yuri.
Okay, I'm coming. Could you see my screen?
Yes, you can.
Okay. Hello, everyone. I'm Yuri Zhu from the University of Science and Technology of China. It's my pleasure to, on behalf of our team, to present our challenger window solution for UDs in the UDC image restore track. This is a joint work with Xi Wang, Xu Yangfu, and Xiaowei Hu. Here, I would like to describe the motivation behind our solution. Firstly, we would like to introduce the degradation process of UDC. Refer to the below reference 1. A common UDC system places the camera module beneath and near the semi-transparent OLED display. Because the gap between the display pixels are often on the micrometer scale, significantly distract the incoming light. Hence, there often exists a hybrid degradation appearance in images from UDC, including strong flare is blue and noisy. Moreover, the challenge is this challenge. The dataset of this challenge consists of many high resolution appearance. To better deal with the hybrid degradation conditions, we adopt the classical cross-to-fan scheme in the low-level vision to remove such complex degradations. Secondly, we attempt to analyze the complex degradation from the frequency perspective. Specifically, as shown in the below figure, we first provide a visualization of a difference map in the frequency domain. This indicates that various degradation brought by the UDC mainly affect the information in the middle and high frequency regions. And such information loss patterns are not only obviously on the single pair images, but also on the entire evolution datasets. Our proposed enhanced call-to-fan network is built with multi-inputs encoder and multi-output decoder ULIT-based framework, which gradually generates the high-quality result of multi-scale sets in a cross-to-fan manner. Moreover, we have made further adjustment from the basic network models, feature interaction manners, and network levels to deal with the UDC restoration task. The first core design is our proposed enhanced residual dense block, which implies 3 convolution layers. Additionally, there are serious scale connections across the various levels to construct the dense network structure. Such residual dense connection manner could extract richer contextual information and transfer the information flow from the shallow to dense layers. Moreover, motivated by the current popular transformer architecture, we place the orange linear activation functions with JLO in our enhanced residual dense block, which brings obvious performance gains. Hence, we utilize the enhanced block as the basic block of our work. Second core design is that we propose a multi-scale cross-gating fusion model to enhance the information flow between the encoder and the decoder. This block first collects the feature at 4 scales through the concat operation, then adjust the number of the feature channels through convolution layers Then the features are evenly divided into two parts and perform gating operation on the two parts alternately. Finally, the enhanced features to the contact operation could be obtained. Besides the further loss of functions, besides the content loss, we also employ the frequency domain information to provide additional guidance for our network. Furthermore, to achieve a better restoration performance, we adopt two training strategies, including the progressing and the model ensemble. Progressive training refer to train the network with larger image patches. For example, at the first stage, we adopt the dynamic optimism with a batch size of 3 and pair size of 256. We obtain the best model at first stage as the initialization of the second stage. The similar process is performed again in the second and third stage. We also adopt the model ensemble strategies, which averages the parameters of multi-models trained with different training iterations. In this table, we report the comparison result among the different solutions on the challenge track. Obviously, our method performs best performance in terms of all evolution metrics, even 0.7 higher than the second place method. In next table, in table 2, we compare the performance of models with different non-linear activity functions, including ReLU, LiqReLU, PReLU, and GLU. Obviously, use GLU performs better than other activation functions, both the embedding in the standard residual block and the standard dense residual block. In the table 3, we compare the connection manner between the encoder and decoder, which indicates that the feature flow, feature information flow after the gating operation really brings better performance. The network performance with different losses are reported in the table 4. It seems that using the nonlinear loss brings a better generalization capacity. Obviously, frequency loss play a larger useful guidance could help the network to restore more details and boost the network performance. Also, as shown in the table 5, the models trained with different stages are marked as S1, S2, and S3. Experience shows that training with progressively large patches often lead to a better generalization performance gains. Meanwhile, they are existing around 0.09 increase on the evolution dataset with help of the modern example extractors. Here, we also provide the comparison vision result. To increase the vision inference, we compress the residual maps, which is the difference between the estimated result and the ground truth. We find our method always recover more details. Here is our conclusion of our method. We present an effective enhanced cost-to-fine network to restore image captured by the UDC with various types of degradations. we designed a two-core enhanced model called Enhanced Residual Dense Block and the Multi-Scale Cross-Gating Fusion Model to enhance the network by exploring the effect of the linear activation function and the feature interaction strategies among the different scales. Finally, experience result demonstrate that our method signified outperforms other UDC image restoration solutions. And in the challenge, our solution achieved the fourth place in terms of all evolution scores and outperforms other solution by a large margin. Thank you. Thanks for listening. My presentation is over.
Any questions? I have a question for your for your presentation. My question is, from your side, what's the challenging part in solving the UDC restoration task? I mean, which part is most challenging?
Before I take part in the challenge, I'm not understand the HDR data, such the data format. I'm not. I tried to understand this data format first. Then and other the data operation. This is similar to other low-level vision tasks. I think it's okay. Just the data format for me.
Okay, thank you, Yuri. There's a question from audience. The question is, what the design specific for UDC image restoration in your work, and what improvement it brings?
I have two. First, for example, is the frequency losses. We analyze the UDC image pairs on the all data set. On the all data set, if we find the such we analyze the hybrid degradation from the frequency domain. This is close to the UDC degradations, and others block we also refer to other low-level visions task.
Okay, thank you. There another question from audience. The question is, the solution involved many module and training strategies. Which module and training strategy do you think improve the performance the most?
Here we will provide the evaluation of the basic block and modules. We can find the dense residual block performs better than the residual block, but when both the residual block equipped with the GLO activity functions, it will perform better.
Okay, thank you, Yuri. And
thank you.
And I will hand over the stage to Prof. Lloyd.
Okay, thanks, Cheng-Yi. So we are going to have 3 keynote speeches before we end the workshop today. So this is the second keynote, and we have Mr. Tomo Michinaga to share his view about the recent evolution on image sensing. So due to unforeseen circumstances, so Mr. Tomo Michinaga cannot join us today. So we will play a recorded video. And before we start, let me briefly introduce Mr. Tomo, Mr. Naga. So he's the general manager at Sony, and he received his Bachelor of Engineering and Master of Engineering degree in Biophysical Engineering from Osaka University, Japan. In 1989 and 1991, respectively, has been working for Sony Corporation since 1991. So he studied computer vision and computational photography as a visiting scholar with Prof. Chen in Columbia University from 1997 to 1999. And since 2016, he is appointed as the general manager and is leading a team of development on signal processing for image sensors. Hi, David, can you play the video? Thank you.
Hello, everyone. Thank you for watching the video. This is a talk on recent evolution on image sensing. Let me introduce myself. I am Tomo Mitsunaga. I have worked for Sony for a long time. Recent 10 years, I have worked on signal processing algorithms in and near image sensors. Not only RGB image sensors, but also image sensors for other than RGB. Let me explain my current company. I work for Sony Semiconductor Solutions Corporation. The company mainly manufactures image sensor devices. I guess that Sony is regarded in public as a company for consumer electronics, pictures, music, and games. But the imaging and sensing solution business, which Sony Semiconductor Solution does, it is also one of the major business segments of Sony Group. For now, image sensors are used in various places and various situations. Our company has the top share in the image sensor market worldwide. As an introduction for today's talk, let me give an outlook of the image sensor market. The graph in this slide shows the amount of the shipment of image sensors by our company for each year. Gray bars indicated the amount of the CCD image sensors, and blue indicates the amount of the CMOS image sensors. As you can see, the growth trend for CMOS image sensor is obvious, and the growth is synchronized with the expansion of the mobile market. The graph in this slide shows the same trend in recent years and forecast for near futures. Here, blue bar indicates the trend for mobile imaging. We understand that the current growth of the image sensor market is driven by demands for the mobile imaging, whether the driving force is expected to continue at least for several years from now. On the other hand, we also see other demands are emerging from sensing applications. They are beginning to grow in these several years. The sensing application is to utilize image sensor data not only for taking pictures, such as for person identification, product inspection, obstacle avoidance, and so on. That kind of the demands are increasing in automotive and industry market mainly, but not limited to those markets. A characteristic of the sensing application is that it utilizes non-RGB information as well as RGB images. Based on the market outlook which I have explained, it is worthy to consider what kind of demands come from the mobile imaging so as to understand what kind of the imaging technologies are required. It is also worthy to consider not only RGB image sensing, but also sensing other than RGB information. In this talk, I would like to introduce recent evolution of image sensors for both RGB and other than RGB in the order that is explained in this slide. In the first section, Recent RGB image sensor technologies for mobile imaging applications are explained. In the second section, some new generation image sensors which are to acquire information other than RGB are explained. Those image sensors are for now supposed as for automotive and industry market. However, those image sensors may be utilized for future mobile applications. I would like to explain that possibilities by introducing some recent researches of related areas. Let's start the first section. As I showed so far, mobile imaging is one of the most important markets of image sensors. Therefore, it is good worthy to consider what kind of imaging technologies are demanded from future mobile uses. Photography and visual communication are major uses of mobile imaging so far and in the future. Recently, mobile devices are also being used as personal assistance tools. Considering the recent progress of the computer vision and image recognition technologies, it is expected that image sensors will be used more in personal assistance uses. Despite the expansion of the imaging uses to other than photography, I would say that image quality improvement is still being one of the most important demands, because performance of the computer vision and image recognition highly depends on the quality of the input data. Another important demand is utility. Recently, AI-based technologies are becoming used more in mobile devices. Thus, using image data with AI-based technologies are increasing too. Therefore, image sensors should become useful for those new technologies. From here, I would like to introduce a couple of recent image sensor technologies developed for mobile imaging. One is new color coding image sensor. The other is always-on image sensor. These technologies, in fact, have realized some features which are demanded from mobile use cases. Blue levels indicate features on image quality improvement, and orange levels indicate features on utility improvement. First, I'd like to explain about new color coding for mobile image sensors. The Bayer color coding, that is 2x2 RGB coding, has been used for traditional RGB image sensors. Bayer coding brings a well-balanced image qualities in terms of the spatial resolution and SNR. However, the number of pixels in mobile image sensors has increased in recent years. As a result, performance balance of the Bayer coding is no longer optimal for mobile imaging use cases. The quad Bayer coding has been developed in order to optimize for mobile imaging. According to increasing the spatial resolution due to the increasing of the number of pixels, autofocusing is becoming severe in mobile imaging. The dual PD technology has been developed to improve the performance of the autofocusing. Recently, Sony has developed a new color coding which is called Octa PD. The Octa PD has advantages of both quad Bayer and dual PD technologies. In the slide, quad Bayer coding and Bayer coding are compared. Recently, it has become usual that an image sensor for mobile has several tens megapixels. A high number of pixels brings us very fine still images and flexibilities for post-production. In such higher pixel number images, much smaller pixels are implemented in order to avoid increasing of the image size. As a result, the SNR in dark scenes is becoming severe. Further, the current major movie format is 4K and it is 8 megapixels. Thus, the image quality at the half resolution is becoming important. The table in this slide compares the image quality at half resolution. Usually, megapixels of a same color are summed in order to produce a half-resolution image. A pixel in Bayer coding has same color neighbors in two-line distance in vertical and horizontal. Summing the four neighbors results in irregular resampling positions. On the other hand, quad Bayer has 2x2 packed same color pixels. Because of this 2x2 packing, regular resampling is available to produce a half-resolution image. Further, binning just neighbor pixels has an advantage at SNR. Similar comparison for high dynamic range imaging is possible. Multiplexed exposures with same color pixels is necessary for high dynamic range imaging. The 2x2 packing of the quad Bayer enables multiple exposures without degradation of the spatial resolution. Currently, up to 3 exposures is available in products. With Bayer, on the other hand, only 2 exposures multiplexing is available, and it results in some degradation of the spatial resolution. Autofocusing in dark scene is another problem for mobile imaging. In this slide, a couple of methods of autofocusing are illustrated: phase detection autofocusing and contrast autofocusing. Phase detection autofocusing exploits incident rays which arrives from same position of the subject through different optical passes. The different optical passes project images at different positions. By measuring the difference, it is possible to know both the direction and the amount of out of focus. Contrast autofocusing, on the other hand, measures only the amount of the out of focus because the projection is single. Therefore, phase detection autofocusing is much faster than contrast autofocusing. An issue is how phase detection autofocusing can be realized with mobile image sensors. A comparison of 3 different ways of the realizing phase detection autofocusing with a quad Bayer image sensor is shown in this slide. A left column is a quad Bayer color coding with partial phase detection pixels. Because only 2 green pixels of the 8x8 pixel area are used for phase detection autofocusing, it is expected that a limited improvement of the autofocusing in dark scenes. In order to realize 100% pixels utilization for autofocusing, one way is to use 2x2 size on-chip lens as illustrated in the center column. However, this image sensor is optically equivalent to a Bayer image sensor with 1/4 number of pixels. The Octa-PD image sensor that Sony has developed recently is illustrated in the right column. Octa-PD image sensor is a quad Bayer image sensor in terms of the color coding. Further, each pixel in an Octa-PD image sensor has a couple of isolated photodiode under an on-chip lens. With this dual PD structure, phase detection autofocusing is available with all pixels in an Octa-PD image sensor without degradation of the spatial resolution. I would like to show a benefit of all pixel autofocusing in dark situation. In this slide, the left image is an example of the partial pixel phase detection autofocusing, and the right image is the same thing with an all-pixel autofocusing. You will see that the all-pixel autofocusing is more stable to follow the movement of the fine textures of the markup. I would like to show another example. OctaPD image sensor also has advantages of quickness of autofocusing in high dynamic range scene. Because the face detection is available for each pixel in an OctaPD image sensor, autofocusing works well in every exposure ranges of 3 multiplexed exposures. Next, I would like to introduce always-on image sensor. Recently, mobile devices are also being used as personal assistant tools. People expect the personal assistant tools to work more proactively and autonomously. Further, it is also expected that it stand by always to respond quickly to variety of the user demands. Thus, the personal assistant tool requires sensors in mobile devices to work at background. In order to realize such always and background sensing task, Sony's always-on image sensor provides a multi-resolution environment recognition function. On the slide, how the multi-resolution environment recognition works is explained with an example. In this example, a personal assistant wants to know existence of a certain person in front of camera. Always-on image sensor provides a human presence detection with low-resolution images. The presence detection is followed by a personal identification that is performed by a main processor with high-resolution images. Further, always-on image sensor also provides a motion detection with ultra-low resolution images that is followed by the human presence detection. This kind of the step-by-step recognition makes the total system efficient and makes the main processor work for more intelligent and sophisticated tasks. One of the challenges of always-on image sensor is to realize an ultra-low power standby mode. In the standby mode, the image sensor in the whole system solely operate continuous capturing and recognition with low power. Power getting system in always-on image sensor realize the fine control of power supply to circuit in the chip. Optimization of the power consumption of each circuit is realized as low as possible. In order to realize the standby mode, which is operated by the image sensor solely, always-on image sensor has integrated a lightweight neural engine. The neural engine has been developed dedicatedly for always-on sensing. Sensor raw data is inputted directly to the neural engine to minimize computation. Sony's lightweight computing technologies are also exploited to minimize power consumption. Although it is for now limited for some simple object presence detection tasks, it will be expanded for more variety of tasks in the future. I would like to show how the object presence detection works with an example of UI control task. The example is automatic display on-off control. In this case, always-on image sensor continue to find an upper body of a human. Canon signal is outputted only when an upper body is detected. From here, we move to second section. In the previous section, I have explained that recent RGB imaging technologies satisfy some demands on mobile imaging. However, of course, there are still challenging demands left. Some of them may be difficult to solve with only RGB, which captures visible appearance of objects. In the second section, I would like to introduce new generation image sensors to acquire information other than visible appearance of object. Time-of-flight image sensor, polarization image sensor, and event-based vision sensor are introduced. Those image sensors are expected to realize features which are indicated with blue and orange labels in this slide. First, the time-of-flight image sensor. Time of flight measures the time for a round trip of the light between sensor and an object. The output of a time-of-flight image sensor is a 2D map of the object distances. The benefit of the time-of-flight image sensor is that such distance map is obtained without computation. 3D geometry information of the scene or subject in front of the camera is required by some mobile applications related to visual communication and personal assistance. It is easily imagined that time-of-flight image sensor works well for such applications. Sony has developed two kinds of time-of-flight image sensor products. Direct time-of-flight image sensor directly measures the time difference between light emitting, light receiving. SPAD, single photon avalanche diode, is used as the photo detector in the direct time-of-flight image sensor. When a photon incident into SPAD, an avalanche of electrons build up very quickly. This high-speed avalanche is very suitable to measure time of arrival of photons from objects at a long distance. Indirect time-of-flight image sensor, on the other hand, measure time correlation of emitted light signal and received light signal. Due to that computational principle, the photodetector for indirect time-of-flight image sensor can be similar with conventional CMOS image sensors. Thus, indirect time-of-flight image sensor can be a high resolution and low cost than direct time-of-flight image sensors. Second, the polarization image sensor. The polarization image sensor can capture the difference of the polarization of the incident light. Polarization imaging is expected to have a variety of applications. Images in this slide show examples of the applications of the polarization imaging. Visual inspection. Inspection of dust and scratches on the surface is a tough task for human eyes. Polarization imaging lets such small deviations be distinguishable. Reflection removable. Specular reflection on the surface of the glass or water often inhibits to see subject behind the surface. Polarization imaging can remove the specular reflection. Stress visualization. Polarization imaging is also useful to visualize distortion of object surfaces and internal stress of objects. Material discrimination. Polarization of the light depends on the material of the object. This characteristic can be exploited to find objects of the different materials. Sony has developed polarization image sensor products. There is an on-chip polarization filter in the image sensor, and it can select 4 directions of the polarized light. By measuring the incident light with the 4 directions of the polarization, it is possible to compute the degree of the polarization incident light. Based on the degree of the polarization of the reflection at object surfaces, Various kinds of the surface analysis and visualization can be done, as I explained in the previous slide. With conventional types of the polarization image sensors, the polarizer is attached on top of the on-chip lens layer. However, with Sony's polarization image sensor, the polarizer is formed on chip under the on-chip lens layer. This shorter distance between the polarizer and the photodiode is effective to reduce the incident angle dependence. Third, the event-based vision sensor. The event-based vision sensor realizes high-speed data output with low latency. In the event-based vision sensor, luminance changes that exceed the preset threshold value is extracted by each pixel. The extracted luminance change is then combined with the pixel coordinate, time, and polarity information before being output as an event data. Each pixel operates asynchronously and independently from any other. The left animation in this slide shows difference how the movement of the ball is captured by a conventional image sensor and an event-based vision sensor. Because a conventional image sensor outputs every pixel values at each frame, the time interval of the motion detection of the ball is limited by the number of the pixels in a frame. On the other hand, the time interval of the motion detection by the event-based vision sensor is limited by how many pixels detect motion. Usually, the number is much smaller than the number of the pixels in a frame. With a focus on movement, the event-based vision sensor can be applied in a wide variety of the fields. The right animation shows a couple of examples of the applications of the event-based vision sensor on industry inspection of the fast-moving objects. Let me explain how a pixel in an event-based vision sensor works. Each pixel consists of a light receiving and light detection unit. The incident light is converted into a voltage in the light receiving unit. The difference detection circuit in the light detection unit detects the changes between the reference voltage and the converted incident light voltage. If the changes are greater than the set threshold value in either a positive or negative direction, then the comparator identified it as an event and this data is output. After that, the circuit is reset with the threshold value based on the detected luminance change. Repeating that luminance detection and reset operation, the event-based vision sensor can continue event output according to the incident light change. From here, I would like to introduce researches in recent hot topics on vision-based imaging. Inverse rendering, novel view synthesis, and video interpolation are picked up. I believe that technologies from this research area will be utilized in order to enhance mobile application in the future. In several years, there have been many research papers proposed on these topics. There have been also research papers which exploit image sensors to acquire information other than RGB, such as polarization, depth, and motion events. First, inverse rendering. Inverse rendering is to estimate rendering parameters from a set of images of an object to be rendered. Rendering parameters are usually 3D shape, surface reflectance, and illumination position and intensity. This technology seems to have been demanded from applications for graphics content creation so far. However, recent growth of the capability of the interactive graphics and artificial reality with mobile devices is remarkable. That progress makes us expect that inverse rendering will be also utilized by mobile applications in the future. However, we must remind that mobile applications are usually under a situation of one-person operation. Thus, inverse rendering from single viewpoint image may be required for mobile applications. Inverse rendering from a single image is a challenging problem. One paper presented in CBPR 2021 challenged to this problem by utilizing polarization information. The authors used a RGB camera, of which a linear polarization filter is attached in front of the lens with a controllable flashlight. The authors showed the results of the pixel-wise separation of surface normal, diffuse reflection, specular reflection, and depth information of a single object in an image. The separation results were better than previous works which used only a RGB camera. Another interesting research was presented in CVPR in this year. The authors proposed a camera system that a direct time-of-flight camera is combined with a circular polarizer. This all-photon polarimetric time-of-flight imaging system measures time-of-flight with different polarization for each time for each pixel. In general, direct time-of-flight has a high temporal resolution that can measure difference of the arrival time of the direct surface reflection and arrival time of the subsurface scattering. However, in fact, it is not so easy to separate those reflection components only with the time of arrival. Also, an imaging system only with polarization cannot measure the 3D geometry of the subject with single shot. The all-photon polarimetric time-of-flight system exploits difference of the polarization as well as the time of arrival in order to separate the reflection component as well as to measure 3D geometry of the subject. Second, novel view synthesis. Novel view synthesis is to synthesize a 2D image of an object from a set of different view images. This technology makes us imagine a lot of use cases with viewpoint changing in mobile interactive applications. In this area, one recent remarkable method, which is named NAF, Neural Radiance Field, has brought a large progress on the synthesized image quality. Unfortunately, the current NAF technology is not suitable for use at mobile imaging at two aspects. One is the computational cost. The other is the difficulty to learn for generic objects. The both points will be problems at using this technology at the end user side. However, at least about the computational cost problem of NAF, a recent paper presented in CBPR in this year has proposed a solution with exploiting depth sensing. Existing NAF computes a novel view image by a volume rendering which the 3D volume is expressed in a set of implicit parameters. The authors have found that exploiting explicit depth information of each known view is effective to relax the problem of the 3D volume rendering into 2D image warping and composing. As a result, the computational cost was reduced remarkably. The last is video interpolation. Video interpolation is to estimate a high temporal resolution video from a low temporal resolution video. This technology seems to be receiving attention as one of the photography features such as super slow motion movie and blurless movie. If the demand is come from image quality issue, of course we may use a high-speed image sensor. Currently, 120 frames per second with 4K resolution is available as a digital camera product. Unfortunately, up to 60 frames per second with 4K is available for mobile phones. Thus, the signal processing-based approaches are becoming promising at mobile applications. So far, RGB-based video interpolation technologies have been proposed. Optical flow estimation from a pair of RGB frames is the major principle of the RGB-based method. Despite a long history of the investigation on optical flow estimation, there are some difficulties at object boundaries and complex movements. In order to improve image quality at such complex areas, exploiting event-based vision sensor is becoming sought. One of such research presented in CVPR 2021 is shown in this slide. The authors supposed a sensor fusion system with a RGB image sensor and an event-based vision sensor. The method used two kinds of the frame interpolation algorithms that both utilize the high-resolution temporal information of the event stream. One is to reproduce complex movement based on an image synthesis. The other is to reproduce smooth movement based on an image warping. Then the authors proposed a way to merge results from the both algorithms with a good balance. As a result, better interpolation results than previous RGB-based method were shown. The authors also proposed an improved version of this method in this year. Also, I would like to introduce another research which utilizes an event-based vision sensor for video interpolation. As same as the paper explained in the previous slide, the motivation of using an event-based vision sensor is to exploit high temporal resolution information of the event stream. But unlike the previous method, the authors found a way of the self-supervised learning for their event-based frame interpolation algorithm. As a result, they showed good interpolation results without using pre-recorded high frame rate video data for learning. It is indeed a remarkable point because we always have the problem how to acquire sufficient learning data set with a newly developed image sensor. This slide is the conclusions of my talk. In this talk, I introduced the recent evolutions of image sensors for both RGB and other than RGB. For RGB, I introduced two kinds of the technologies that have been used in RGB image sensors for mobile. One is new color coding that is to pursue total balance of image quality. The other is always-on technologies that is to pursue system optimization for realizing autonomous UI. For non-RGB, I introduced three kinds of the image sensors: time-of-flight image sensor, polarization image sensor, and event-based vision sensor. I also explained that those new generation image sensors are promising for mobile imaging applications in the future. Sony Semiconductor Solutions will continue to lead image sensor technologies in order to contribute growth of next imaging applications, not only for mobile, but also to other industries. At the last of my talk, please watch a short movie that explains the thought of our company to create the future. Thank you for your attention.
Light. Its broad spectrum floods our world. Sensing light. Exploring light. Capturing light. And a curiosity fueled by light unlocks worlds unimaginable. Sony's technology will be the history of a future forged by this curiosity. A passion for sharing the beauty that light reveals drove the advances in imaging technology that brought the world recreational photography. Exploring beyond light's visible spectrum, Sony expanded from imaging technology into sensing technology, revolutionizing industries and society. This quest led to sensors equipped with AI and new solutions developed with a global community of partners. Soon, a sensing network will cover our planet. Driven by curiosity, the force behind discovery, we enhance human senses. Sony Semiconductor Solutions expands human potential through imaging and sensing technologies to usher in an exciting new future of discoveries.
Sense the wonder. Sony Semiconductor Solutions Group.
Okay, thanks, Mr. Tomo Misunaga, for the very insightful talk. Since he's not here, so we cannot take any question. And we will move to the third keynote today by Professor Michael Brown. So the title of his talk is Robust Imaging Color and the Dual Purpose ISP. So let me first introduce Professor Brown. So Dr. Michael Brown is a professor and Canada research chair at York University in Toronto. He is also a senior research director at the Samsung AI Center in Toronto. And Professor Brown's research is focused on color and in-camera image processing. And Prof. Brown has served as general chair for CVPR 2018 and CVPR 2021. Michael, your turn.
Hey, thank you. Hey, good to see you. So let me just share my screen. Okay. Chen, can you see it?
Yep.
Okay, great.
Yep.
Okay, good. Yeah, so first, thanks for having me here this morning. I'm very happy to join and be part of the excellent lineup of speakers you have. It's a really good group of people, so I'm very honored to be part of that. So yeah, I'm going to talk this morning about, this morning for me, I guess if you're in Israel a little bit later, but on this robust color imaging and dual purpose ISP. And my talk kind of has two parts. The first part's a little bit selfish. It's more related to our own papers, but then the second part's a bit more general. So I just want to start with this image here. So these are kind of classic failure images, I would say, that we all kind of recognize. So when you take a photo and you have these really strong color casts in the image, you know there's a problem. Sometimes I think non-photographers or non-image processing people may have trouble understanding what the problem is, like why we have this color cast. But this is a very well-known problem with white balance. And actually, if you go to these photography forums, so there's a lot of these places where people post kind of, images and they ask for help. I think there's kind of two questions that dominate. The first one is this one. They basically have this color cast problem and they ask for help. How do I remove it? The second one's image super resolution. They have a small image and they want to zoom it up and they're like, why does it not look good? So, the problem here is, when you take a photo, you have to factor in the illumination. And so if you get the scene illumination wrong at capture time, and this again is related to your white balance. So if you get your white balance wrong, you'll get this color cast that comes out on the image. And so typically you can manually set it. A lot of DSLRs allow that, but usually this is auto white balance. So it's really when your auto white balance fails. So just a quick reminder, how does white balance work? Well, your human eye, we naturally adapt to the illumination. So this is known as color constancy. So for us as humans, if we're looking at a white piece of paper it always looks white, even under sunlight, even indoor, even under LED light, because we compensate for the illumination. But your sensor can't do that. So you have to computationally do this. And so what you do, and Chen Cheng, this is actually from Singapore. I don't know if you recognize the area this is, but what you're doing is you're trying to estimate in the image, what is the sensor's response to the illumination? So I just happen to know in this image that this region here should be white. It's not white because of the illumination. So if I could somehow figure that out, and this is where the auto white balance comes in, the illumination estimation, we can just simply divide out the illumination. And so we get this white balanced image. But it's hard because, you don't have any knowledge about this image and you're trying to figure out this illumination. Now, I'm going to introduce this term color temperature. This is how it works on your camera. As a consumer, when you're selecting the color temperature, we typically, or the white balance, we typically do this in terms of color temperature. And there's a long story why we use color temperature, but it's just a way to select the color of the illumination based on what we call this temperature line. So you're still just selecting a color. You're just doing it on this 1D curve that we call the temperature line. And just to show you, a lot of cameras, usually we use auto white balance, but a lot of cameras have a slider. For mobile phone, it would be a slider. For DSLR, it would be a little dial that you can dial to change the color temperature. And you can see it really impacts the image. So here's why it's hard to correct this. So I introduced to you the problem, and then I showed you that on this photography forum, people are saying, how do I correct this? Well, it's a diagonal matrix, right? White balance is just a simple scaling of the color channels. But the problem is, once you've made this mistake, you can no longer just scale the color channel. So this is me trying to correct the image just using a diagonal matrix, trying to scale the color channels, even if I know what white's supposed to be. And I'll show you this compared to the actual ground truth. So this is if I capture the image with the right white balance. This is if I got it wrong and I tried to fix it. Now, the reason this is hard to correct is because when you take a photo, you have this camera pipeline, right? This image processing pipeline, and white balance happens very early in the processing chain. So you have all this nonlinear rendering or photo finishing that takes place afterwards. And so because you have all this photo finishing, you can't just simply try to apply something here at the end and think it's going to correct it. So basically, these early mistakes are propagated through this nonlinear rendering chain. And now when you try to simply divide it out, it doesn't work. And surprisingly, people just don't understand this, or there's a lot of misinformation. So you'll read like Python APIs and MATLAB APIs claim that you can post-capture correct the white balance, but you just simply can't do it. So I'm going to talk about two different strategies to correct this. And this is sort of the robust color imaging part of my talk. And these, again, this is a bit selfish. These are all my own papers. But I think we're one of the few groups that look into this. More people are starting to propose similar things, especially on this first part that's called raw reconstruction. So let me just roll back one slide. When you take a photo, you typically have two options. You can save the image in the final rendered image. So we often call this the sRGB image, or you can save it in this unprocessed image that we call the raw image. Now, if you capture a raw image, you have to render it so you can view it. And if you capture the sRGB image, then it's already been rendered, and then you get the problems of not being able to correct it because you have these nonlinear mistakes. So the first class of images techniques we're going to look at is actually trying to reconstruct or recover the original raw image from your processed image. And then we'll look at a strategy where we actually look at the ISP itself to see how we can make changes. And because this first method is really looking on how to reconstruct the image, it's more suitable for post-processing in something like Adobe Photoshop. For something like modifying the ISP, it's more suitable probably for the focus of this workshop, where you're actually modifying the in-camera capture time processing. So let's just talk a little bit about the benefits of shooting in RAW. Like, why would we want to shoot in RAW? Well, most professional photographers, they do shoot in RAW. And the reason they do that is because if they have the original unprocessed image, then they can actually reprocess the image using software. So software like Adobe Lightroom, and there's several others, Raw Therapy, and there's other ones. These are essentially software-based camera ISPs, and they give you, the user, the freedom to tune the ISP, this rendering pipeline, how you want it. But the problem is we don't always shoot in RAW, and the sort of standard format for RAW is known as Adobe's digital negative. We just don't shoot in this format, even though there's a lot of benefits to it. And one of the reasons we don't shoot in this format is that the file sizes are very large. So RAW typically is not compressed. So compared to JPEG, or Apple's using this high efficiency image encoding, you know, your image could be 15 to 50 megabytes compared to 5 to 7 megabytes for a JPEG. The other problem is RAW itself is not really, it's not a visual format. So what I mean by that is if you have a RAW image, you can't just view it immediately. You have to run it through some processing to get it into what we call a display referred color space that your computer or your monitor expects it to be in. So there's limited workflow. So if you have RAW images, it's kind of hard to work with them. So this is a problem I worked on many years ago, and I thought it was a really nice piece of work where we asked the question, what if we could somehow embed information in the JPEG image, in the processed image, that would allow us to get back to the RAW image? So imagine I have this image, it's encoded in JPEG, and somehow I can reconstruct the original RAW image. And at that time, I had a student, Ring Lin, who was working with me in Singapore. And I just tasked him. I said, Ring, I want you to look at this problem, and the maximum amount of space I'm going to give you is 64 kilobytes. So you can do whatever you want to do, but you only get 64 kilobytes of data as additional overhead. And the reason we limited to 64 kilobytes is because that is the comment size in JPEG. So JPEG has a mechanism to insert comments. The maximum comment size can be 64 kilobytes. So what Ring essentially did was, at capture time, remember you have the original RAW image because that's what the sensor gets, and you have the final processed image. This is all available to you on the camera. So what he essentially did is, and this is no machine learning here, by the way, this is just purely signal processing. He just simply modeled the core routines on the camera. So tone mapping, white balance, there's a color space transform to get you in display, what we call display referred space. And this gamut mapping, we probably shouldn't have used this word gamut mapping. We probably should have called it color rendering, but it's just essentially like a 3D lookup table or a 3D function that just warps the image, the color. So it's a rendering function. And so basically what he did is at capture time, he's parameterizing the necessary information to render this image. And he limited himself to 64 kilobytes. And in my personal opinion, the novelty really was how he did this part. He used a very interesting sort of breadth first search quad tree or octree strategy to kind of build this lookup table. But anyway, what it allowed you to do is if you had a JPEG image, and this is a little bit older paper, this is from 2016. So at that time, we were doing everything with DSLRs. So DSLR images, JPEGs are quite large, but here's a JPEG image. The ground truth would have been about 25 megabytes. He embeds only 64 kilobytes of this metadata, and we can reconstruct with virtually no error. I mean, we just have kind of the quantization error. So it was around 1% error to reconstruct the original raw image. And what's nice about that is if you have an image that does have this color cast problem, so this is me taking, this is the exact same camera. I take a photo with the wrong white balance. This is me taking the photo with the correct white balance. This is me trying to correct it using Adobe Photoshop, doing the best that I can to get the right answer. In the Photoshop, you can get kind of individual colors correct. I can get this kind of white background to match this, but the other colors are off. But with Rang's method, it was virtually identical. Because he could reconstruct back to raw and just re-render through using something like Lightroom. Here's another example, and it really helps when you see skin tones. So this is an example of poorly, incorrectly white balanced image. This is the best you could get with Photoshop, and this was our result, being able to go back, come forward. Now we've continued to improve this process. So I just mentioned a couple papers, just one slide each, but at WACV, we had a little bit better kind of processing reconstruction method where it was more spatially aware. So it adapted locally. And then recently in CVPR last year, or this year, I guess, CVPR 22, we had a method, a learning method that actually learned how to sample the image. So in this case, we're actually taking raw samples. So what are the optimal samples that we can use to do the reconstruction? Oh, and I should note, let me just go back. We had a change of philosophy from Rang's method. So Rang would actually, at capture time, compute this transform. Later, we realized on device, that's a little too slow. So instead, we just sample raw pixels. So we just uniformly sample raw pixels. And then at render time, when you want to use this, we would actually revert back to raw. And that seemed to work quite well in terms of, kind of speed at capture time. So in this case, we looked at a better method to do the reconstruction. And in this case, we were looking at a better way to do both the sampling. So instead of uniform sampling, can we learn how to sample the image and then how to reconstruct? Another thing that we actually found is when you do have the raw samples, so if you had a small set of samples, let's say, maybe 60 kilobytes of samples from the original raw image, and you had pre-learned a reconstruction network, you can even fine-tune the network on these samples. Even this small amount of like 1% of samples, you can even fine-tune a pre-computed network to get a little bit better result. And this is just showing you some results from the WACV paper. This would have been Rang's initial solution. It works pretty well, but he can't handle spatial processing. He kind of had a global approach, and this is showing the WACV approach, and the ECCV approach, or the CVPR 22 approach is similar. Now, there is one drawback of this sort of raw reconstruction methods, and it's just namely that if you do go back to raw, you are expecting the user to have access to software like Adobe Photoshop that can reapply the correction. So you have to go back to the beginning and then re-render the image. And not everyone would have access to this rendering. And a lot of the smartphones won't tell you the full rendering pipeline. Like they're gonna, even in the DNG file, they're not gonna put all the metadata to allow you to re-render properly. So that made us think about another way of doing this. And this was really, a method that required you to modify the ISP at capture time. So it makes I think the other papers are more practical in the sense that you can really do it with very minor modification. What we're proposing here is a little bit more significant modification to the ISP. And then this actually, we submitted it to a color imaging conference and is very happy that we won Best Paper Award. So I'm just going to show you what it can do. So this is actually a single image that I can retune after the fact. And so we call this color temperature tuning, and I'll just explain what we do. It's a pretty simple idea. So remember, at capture time, you have this raw sensor image, and you're going to run it through your camera ISP that has all these processing stages. And these processing stages can have, I don't show any neural processing here or deep learning, but you could have a deep learning denoiser or deep learning white balance estimator. That's fine. So what you do is you render this through. It goes through all of these processing steps. This is just kind of the internal steps of the camera pipeline. So you have these intermediate images that you process on your ISP, and then you get out the final image. So when you render on your ISP, you set it all the parameters. So you would even say, I want to render ISP and I want to render with this color temperature. And then the ISP renders it through. Now, remember earlier we talked about, well, what if this is a mistake? What if you got this wrong? Well, you have a color cast here, and it's very hard to correct. So what we showed that you could do is we said, look, let's take the standard rendering procedure and let's take a very small version of this raw image. So I think in this case we used, it was maybe a 100 by 100 pixel image, just a very tiny image. And then we took those color samples and we also ran it to the ISP. And there's a lot of tricks you can do. You could actually append it at the bottom. There's all these sort of speed up methods. But right now, let's just assume we render the thing all the way through the ISP, but it's very small. But we do it for various settings on the camera. So let's say that we actually render that tiny image at 5 different settings on the camera. So then you would get out 5 tiny images, all with these different color casts, all the different color temperatures. Now what we can do is we can downsample our full scale image. So this is the image that the camera is going to output. We can make a tiny version of that. And then we can compute a mapping function that figures out how do I map the colors of this image to all these other images. And you do this per different image. So you would come out with 5 mapping functions here that takes this image, it maps it to this one, it maps it to this. So this is just a color transform. We use a simple polynomial kernel trick. But it's just this is just linear algebra. There's nothing, no deep learning here. It's very simple. And then all we store in the image is actually those mapping functions. So it turns out we can store very small amount of data. So I think in this case, 6 kilobytes of data only. We can embed it in a JPEG image. Now, what gets interesting is now you have this metadata. Now you extract your JPEG image and you realize, oh, I don't like the color of the image. Well, if you knew exactly the color temperature you wanted to map to, you could just extract that metadata and apply the mapping. And you would get back the original image. And really what we're showing is when it comes to color, just having a small number of samples is sufficient for you to map a whole image to the other image. So this metadata would allow us to move to these other color temperatures. And if you wanted to go somewhere in between 2 color temperatures, so let's say that on the camera you save these 2 different color temperatures like 2500 Kelvin and 4000 Kelvin, you could extract the nearest neighbors and just simply blend between them, right? You just do a linear interpolation between these matrices. And that also seems to work very well. So here's an example of, this is the image color temperature that was captured by the camera. So this was a mistake. It has a very yellow color cast. And this is just me being able to tune to any temperature that I want. And all I'm doing is I'm just loading up those different color temperatures and I'm just interpolating between all of them. And you can see it's almost like giving me the ability to retune as if, and this is all post-capture time. Here's another example. This is the example we started with that was very hard to correct. And this is again a JPEG image, 6 kilobytes of data, and then we can tune it to make it look like the original image. So the student who did this work, he got hired by Apple, like immediately. So, I mean, this was really paid attention to by industry because I think it's a very nice, simple, practical solution that you can use. And the nice thing about this is there's some really hard problems. This is a classic hard problem of dual illuminant. So this is an example where I have an image with a backlight. So what you're looking at is this little toy here is being illuminated indoors. And that's why it has a yellow color cast. But there's also sunlight. So this illumination, so white balance only tries to correct the global illumination. Here you have 2 illuminations, indoor and outdoor. So if you correct the outdoor, it looks good out here, but this becomes very yellowish. In this case, if you correct the indoor, this is actually more correct now, but you have this very strong blue color cast because the outdoor wasn't corrected. So now we can correct anything that we want. So we could even segment the image, apply a correction here using the right matrix and apply a correction in the background using the right matrix. So this gives us the ability to actually correct both of these. Of course, there's some user interaction to segment this, but at least you can do it. The other thing that we showed is with a very simple modification, we can take that same idea and at least that color mapping function, it can actually work to go back to raw as well. So you can actually reconstruct raw images using that very simple mapping function. So again, we're just using, instead of the target being another color image, it turns out if the target's the raw image, this works pretty well too. Okay, so that's some of the work on robust color imaging. And I just talk about that topic because just trying to get people to think a little bit more about, at capture time on cameras, we make this assumption that we need to get everything right. We render it through, and then we hope for the best. but it does fail from time to time. And when it does, we need mechanisms to be able to recover it, to give that flexibility. But let me talk a little bit more about the bigger picture here. So there's really been a major shift in photography. So a lot of these devices now, if you just look at this, and some of you may have seen this graph before, but we used to have film cameras, we used to have point and shoot cameras, we had smartphones and DSLR. But if you just look at the market, so this plot here is the number of units sold per item. And so this is film cameras, and you can see, and this is units times in the thousands. So we're talking about millions and millions of items here. So you can see film cameras dropped off, right? And this goes all the way back to the 1930s, okay? So you can see film cameras just totally dropped off. Point and shoot camera, which is what replaced film, this is quickly dropping off. Very few of us now use this type of camera. And DSLR has a very steady market for professionals, but it's not growing. So what's replacing all of this? Well, smartphones. And it's really replacing it. Like it's really, really replacing it. So pretty much the way we do imaging these days is smartphones. And I hate to say it, but these things have kind of died off, right? We don't really use film. We don't use point and shoot. And we're trying very hard to replace DSLRs. That's really what smartphones are doing. And they're doing it by adding all these extra cameras. So now your smartphone has, 4 cameras on it. But what I would argue, though, if you look at what we did in the sort of mobile market, we really reproduced the point and shoot camera. So if you think about our strategy, we're basically saying, and this is, point and shoot camera is not a professional camera. So the point and shoot camera tries to get everything right at capture time. So your goal is at capture time, make sure you get everything right, predict exactly what the user wants. So this is very easy to use. But again, if you make a mistake or you want to customize it, it's very hard because you just have this processed image. And let's just remember, DSLRs, they took a different approach. DSLRs, they can also provide the point and shoot functionality, but DSLRs kind of target this professional imaging where they save RAW and they give you this flexibility to be able to do the editing post-capture. So, I would argue, why are we emulating point and shoot? Why not provide both functionality? And smartphones have a really interesting, or mobile platforms have a really interesting advantage. Because with a DSLR camera, you had to take the data and you had to export it to a laptop to edit it. But on a smartphone, you can do the editing on the smartphone. So I would argue that we can actually combine everything together. And let me explain. I call this full stack imaging because we own, on a smartphone platform, we own everything. We own the sensor, we own the ISP, and we own the image editing software. So unlike a DSLR where you had to export the image to a PC or a tablet, now you can do this all on the same device. And so we really should be trying to merge all of this together. And what's really interesting is right now we don't. Right now I would argue that the image editing software is completely ignorant. It doesn't know anything about what happened at capture time. But using these tricks like the metadata that we showed you, where you can keep some raw samples or you can keep some information about what happened at capture time. And if you're on the same platform, you could possibly keep some information directly about the image signal processor. If you keep that data and you pass it on to the image editing software, it can make the editing software better. Just like we showed you, you can roll back to RAW. But what's even more interesting is if you make an edit, it can actually pass those edit information back to the signal processor. So imagine over time that your camera learns what you like. If you keep taking the image and you keep adjusting it a certain way, you could feed some of that information back into the image signal processor. The other thing that's really exciting to me is that now that we know that people are walking around with a camera, so you have this imager at your fingertips all the time, there's so many more things that we can do than just photography. So if you look at, and I think this is in Asia, this is much more common. I think in Asia, people are much more willing to use their mobile phone for things. You know, you had WeChat, had WePay way earlier than the West kind of picked up on this. But there's a lot of other things other than just QR codes. You know, there's money you're trying to authenticate your money. You actually, this little device here has a camera sensor in it. You're doing medical applications. There's a camera sensor. One of my former, not my student, but from the lab that I worked in, he went to Ant Financial at Alibaba, and he showed me a demo of a really cool app where if your car gets hit, you can just go out, take photos of your car using your mobile camera. It reconstructs the 3D damage, and it immediately gives you the insurance money from Ant Financial. I just thought that was amazing, all using your mobile phone. In rural areas, you could use it to help you do like, you know, agricultural identification of diseases. So what's interesting is right now, if you look at the camera, the ISP, the image signal processor, is very photocentric. It's really designed to make photographs. But with relatively simple modifications, you can actually have it be a more scientific device. That means the fundamental CMOS sensor actually makes measurements that's, you know, it measures radiance, it measures colorimetry. You could be using those for scientific purposes or medical purposes. And if you look at the current camera pipeline, there's already a natural division of this. So if you just look at how the current camera ISP stages are done, there's actually what we call a bare processing front end that is known as scene referred image states. That means these images up until the state, they're all referring back to the original radiance, so the original light coming into the camera. And everything after this stage is now the photo finishing part. It's actually processing the image for display. So it's changing that relationship to the scene. And now you're changing the relationship to be related to the display and to the aesthetics. How does it look? So if you just work in this area here, you're a much more scientific camera. And so if you wanted to develop skin tone recognition or even color measurement, you can even buy these devices that measure color. The sensors, the same sensors in your smartphone, it's just been calibrated differently. And in fact, really what it's doing is it's just stopping earlier in the camera pipeline than a conventional camera. Even things like medical imaging, there's a big project to, especially for people with diabetes, they tend to get these wounds on their feet. So you can color grade that or wound grade it. So using a camera, well, the camera's just doing minimal processing and stopping at one of these earlier stages. So yeah, I firmly believe that just by a simple modification of the ISP, we can really, you know, make these devices much more usable. The other thing that we shouldn't forget about is you can also use this for purposes like color rendering. So we talk about it here, you know, I talk about scientific imaging, but there's a lot of reasons we may want to redo some of the display referred rendering. So for instance, now we have a lot of our display devices are, you know, 10-bit or higher, what we call color gamut. So you have UHD TV, you know, displays, and a lot of your displays are now processing the image to make it look better on the display. You know, I talked about white balance, but you can also balance the image depending on the environment that you're viewing in. So there's a lot of just kind of photo finishing things that we can do here that would benefit from having this this division in the camera of scene referred images versus display referred images. And so if we look at the big picture continuum, so if we look at this sort of imaging continuum, so we have this sensor, and depending on what we do to the sensor, and I saw in the challenges for this workshop, you know, you have the quad sensor challenge. I mean, there's a lot of new sensor designs that if you design the sensor correctly, you can get radiometric data. You can get sort of spectral data back. And not just from the sensor, you could also use controlled illumination in the scene. You know, you have your flash, you know what type of light. So at the early stages, you can actually recover radiometric, real physical information about the scene. Semi-process level, you can get what we call colorimetric data. So this is data more related to human perception, but accurate human perception. So what is the color of that item? How would it be perceived under different illumination by a human? So right now we can do this on the camera. And then of course we have the color rendering stages. So we can manipulate the color of the image, the different, this is the photo finishing stages. So this is the sort of beauty part of the image. And then of course we have the final photograph that comes out. So with some simple modification, we can get radiometric data. Stopping early in the camera pipeline, we can get colorimetric data. And then processing further, we can get all the rendering parts that we want for the aesthetics. And so for computer vision applications, we really, a lot of the applications really just need these image states. And it's very hard to get access to this now, the way the current ISPs are designed, but I do think that's changing. There's been quite a few papers that show that you don't need all this additional processing. I think a lot of our neural networks actually learn to ignore this because this varies depending on camera. And so a lot of the neural networks kind of learn to ignore color or color variations because they're really trying to understand this part of the image. So if we divide the ISP into this sort of dual purpose ISP where we could save images in this format and save images in this format, we could have this natural division where these images are more useful for scientific and industrial imaging, and these are more useful for photographic and display. So we get the best of both worlds. You can have your industry images and you can have your photographic images. And if we do the metadata trick, we should be able to seamlessly move back and forth between these. And you know, I put this in here because I think there's still a huge market here. I mean, I think this part still drives the industry, is the photographic part, but this is going to start driving the industry more, especially because of COVID. And I think, you know, being in Singapore and a lot of you on this call, I can see are from Asia. In Asia, you kind of avoided COVID by, you know, wearing masks, but in the West, we didn't do this and everybody got COVID. But one thing that happened in the West is we started doing a lot more online going to the doctor. So you would actually, instead of going to the doctor, you would do it over the phone or you would send images. And I think people would say before COVID, you could never do this. They would argue, oh, it's not good enough. COVID forced us to do it. And now you can see there's really a renewed interest. And a friend of mine told me there was a dermatologist and she realized, you know, she was having people send images, but the images weren't reliable because of this sort of photo finishing. So she would ask the people to go to a particular clinic where they always image under the same kind of lighting conditions. And I think with this sort of scientific computing, we could avoid some of that and make it so your own phone could send data to a doctor that's useful. So I'm going to stop here. I know I went a little bit early. I think it's always better to end early than late. And I always try to, for invited talks, to absorb the fact that you're probably late in your schedule. But I really like this idea of full stack imaging. I think this idea, and it's really untapped right now, that especially for mobile devices, we have the camera, the ISP, the editor, all on one platform. And we really want to find out a way to share information between the camera, the ISP, and the editor in a feedback. And you do that with AI, where you can learn this stuff. It's really an untapped opportunity. And I think we can really bring a whole new user experience beyond what we can do now with our sort of point and shoot style mobile phone. And the other thing I think that we really need to start pushing, and I saw the previous talk where there was a lot of ideas about using event cameras and these sort of non-photographic cameras. I see a lot of opportunities with those sort of auxiliary devices, plus our standard CMOSs for getting information that's beyond photography. So not photographic or not photocentric, you know, medical imaging is the most obvious one, sort of industrial imaging, but I think there's a lot of things we can do in this space, all on our mobile phone, mobile platform. Okay, so that's it for me. I have to thank a lot of people. I work with many really talented people. I'm very lucky, and I'm very lucky to have quite a bit of funding, and I even have a little bit of funding back in the Singapore days from A-Star there. So thank you very much, and I can take some questions because I'm here.
Thank you, Michael. So thanks for the very insightful talk, and I really like the idea of like full stack imaging and the idea of having a dual purpose camera ISP.
Yeah.
Yeah, it's very clever. So while waiting for questions to come in, maybe I can start to ask a question. Okay. So there are many research work on deep learning. Basically, they try to replace the various stages in ISP with a single deep neural network. Right. I'm not sure whether it's a good idea. And when it comes to the idea of that dual purpose camera ISP that you just mentioned, would it be good? I mean, if you have a single deep neural network that learn with two purposes. Yeah,
I totally agree. Yeah. In fact, I was just in Korea at Samsung, and we were actually looking at a lot of these sort of neural ISP methods. Yeah, I'm not a big fan of the monolithic one big, you have one big, it depends on your task, but one big monolithic ISP does not seem the right way to go. There's a lot of limitations in that. Like you can't tune it. You have to ask yourself what you're really learning. Like when I look at a lot of the papers, they're just learning a conventional ISP. So how can you go beyond the quality of a conventional ISP if you're just learning the conventional one? I just, sometimes I'm not sure what the goal is in some of these papers, but I do believe the winning formula would be modularity. So if you are going to go deep learning style, you definitely want to do it modular. And this is a great example of that. Now, there's people who do it, like Lei Zhang's group at CityU. I believe it's at CityU. Yeah, he does really great work. They actually had a very nice paper where they call it kind of a two-stage neural ISP, where he actually called it kind of reconstruct and then enhance. And I think his philosophy was more like, well, the first part is where you really handle things like demosaicing and noise and so on. And then the second part's where you do the photo finishing. But I like that approach because that first stage really is also where you could do your scientific imaging part, right? So I think it's inevitable that we're moving towards neural ISPs and NPUs. I think that's just, I do a little bit of kind of scientific advising for some companies, and I was actually talking to this one company, and the engineer showed me he had converted a relatively standard method into a neural method. And I was a little bit surprised. I was like, look, you don't need a neural method for that. And he said, oh, no, I understand. But my compute is only NPU now. I don't have a standard compute anymore. I have an NPU only. And so I noticed like now you're almost forced into it because that's the new compute that you have. So I thought that was really eye-opening because it wasn't a matter of efficiency, flops, or anything like this. It was more, this is what the hardware does. It's highly optimized for that. I have to kind of convert all my old signal processing methods into this new setup. So I think, whether you like it or not, deep learning's coming at everything. And yeah, so if that's the case, I think, this is not, I'm just going to go back to the slide. This is not this little kind of breakout of a standard ISP. It's a very simplistic version, but there's a reason we did it modular. So if it wasn't like the people before deep learning weren't intelligent. They purposely had modularity even in the signal processing days for reasons. And I think we're kind of blindly just moving forward going, oh, we can replace this whole thing. And as one time I gave a talk, and a person, very well-known person in our field said, they said, why don't you just learn it? And my comment was, learn what? I just explained to you what it does. I don't need to learn anything. I know what it does. It's very small number of parameters. So you're asking me to learn this thing with 1 million to 5 million parameters for something that's only 1,000 parameters. So yeah, I like the idea of monolithic I like the idea of neural ISP. I think in the future, we really need to put a lot of thought into what is the modularity. And we also need to be aware that there's not going to be one answer. I think in academics, we get caught up in like, what's the one solution that's always going to win? It's really going to be task dependent. Maybe certain cameras, you need more modules, modularity than others.
Yeah. Perhaps is a hybrid solution with some modules with neural methods or some classical
and right
signal
now, just to
processing
let you know,
methods,
that
yeah.
is in most at least flagship smartphone devices, it's a combination. You know, it's still you still have a signal processing based ISP, but you have neural units for hard tasks like denoising, and I think it's going to be this hybrid method for sure.
Okay, Michael, we got some questions for you from the audience. One question sounds like this. In the literature, there exist several works that directly learns raw to sRGB mapping. Would it be possible for these methods to recover more details from DSLR sRGB images?
So was this posted in the chat? Maybe it's better if I read it. Let me see.
Yeah, it was posted in the chat.
I think the problem I have is in full screen mode. It makes it hard for me to see the chats.
Yeah, you need to check the website.
Oh, well, then can you read the question one more time? Because I just didn't understand. Were they asking, can you read it one more time?
Yeah, I'm trying to understand the question too. There exist several works that directly learns raw to sRGB mapping.
Right, okay.
Would it be possible for these methods to recover more details from DSLR sRGB images?
Oh, I see. Yeah, maybe it's a little bit related to what you and I were just talking about, if I understand the thing properly. Yeah, I think one of it kind of goes back to what I mentioned, like, what are you really learning? For instance, if your training data is the conventional ISP and you're using like a reconstruction loss, like how can you go beyond it? Like at most, what you're going to do is you're going to learn you're going to learn what the camera can already do. So I think it is possible, but we need to be, let me reshare my screen here. But we need to be, it kind of comes down to the loss functions we're using. I think right now we're still using these kind of reconstruction losses that don't really allow us to go beyond what the ISP can do. But when you start putting GAN losses and these sort of perceptual losses like LPIPs, yeah, I would argue that you can produce things with more detail than you may not have been able to get with the conventional signal processor. And that's what everybody wants, right? You clearly want your neural thing to be somewhat better than the conventional ISP. What's the point? The places that at least to me, deep learning really wins are the hard problems like image demosaicing. The way in my little group and in the little group I work with at Samsung, our philosophy is if we can't write down an equation for the problem, that's a great place for deep learning. It's hard to come up with a single equation that works for denoising. It's hard to come up with an equation that works for demosaicing because it's an ill-posed problem. That's a great place for data-driven methods. And they really do work well. I mean, you got to admit the denoisers, the deep learning denoisers are pretty amazing. You shouldn't rule out the older methods. Now I'm kind of diverging on the question, but I will just highlight that a lot of students forget things like non-local means actually work really well too. For a long time, the BM3D was hard to beat. It doesn't require any training data or anything. It's still one of the top contenders. It also doesn't need to be trained per sensor. So yeah, I do think that these methods that learn going from raw to sRGB, they have the potential, if done correctly, to bring out more detail and do a better job. And you probably know there's some work like by Radu Timofete, where he was doing really nice stuff, where he was actually learning how to take the mobile phone, but the training data, the target was a DSLR. I thought that was pretty clever. So he's like, okay, I'll actually make my Huawei P20 look like, a Canon 5D, which I wonder the legality of that personally. What are you're basically reverse engineering, or you're learning this other thing, but that's a nice method to kind of get you a better image quality out.
True. Yeah, Michael, we got a question from Mohit. Mohit, you can.
Oh, hey, Mohit, you're on. You could just ask it.
Yes. Hi, Michael. Thank you for the talk.
Yeah, good to see you.
And yeah, first of all, I would completely argue that even now, I think BM3D, I would say it's pretty competitive. And in some of our experiments, especially with unconventional sensors where there is not much training data, BN3D, in my opinion, works much better than many neural network methods.
Yeah, absolutely. And it doesn't require training data, right? You have to tune it, but tuning, sometimes I think we think that tuning's bad, yet we pretend that you didn't tune the training of your network. I'm like, come on, give me a break. How much time did you babysit that network versus tuning it? Yeah, I think in your space where you're working with, it's hard to get training data. They're very unconventional sensors. BM3D is a great choice, right?
Right. So I had a question about something else actually that you said earlier, and I think you made a very interesting point about storing some minimal amount of metadata for downstream editing applications.
Right.
And I was wondering whether we could store some kind of metadata which keeps track of the chain of image processing operations that have been applied on the image, so that maybe an end user perhaps can take a look at those and understand what has gone on with the image. Maybe because they want to preserve the integrity of the semantic content of the image.
Yeah, no, totally. I think there's a lot of things you can do in this space. I completely, utterly agree with what you're saying. And you could even imagine, all of this comes down to, and I think this is where I'm probably limiting myself too much in this area by thinking too much like what a consumer or what an industry would accept. Because I think anytime you do this, you have to think about it has to be minimal. Like if that thing becomes too big, you just know that nobody's going to pick it up in industry. So we often limit ourselves to really small amount of metadata. So like 64 kilobytes, even smaller, even 20 kilobytes. I sometimes think that we're doing my group a disservice by being so small, but I do think, understanding the processing chain, at the maximum end, of the spectrum, a continuum of what you could do, you could just remember everything, right? You could say, well, what are all the settings? And if you look at a DNG file, in principle, the Adobe Digital Negative, you are supposed to embed kind of everything. So it is the chain of what took place, and not just the chain of what took place, the actual parameters to reproduce that. But the truth of the matter is, on smartphones, nobody puts that information in there because, one, it's giving away the secret sauce of the cameras. Like, here's what I did. So, as a competitor, I can immediately see all what you did. The other thing is it's just too much data, right? That's why we don't even save in DNG. So I totally agree with what you're saying. I think the tricky part is the cleverness of, keep it minimal. What is really necessary to figure out what happened? But I totally agree with what you're saying. And I think even for the stuff that you guys do, on the more computational imaging side, I know you often have a lot of data, and especially if you're using SPADs and stuff, you're kind of collecting the histogram of what's coming in. But I think it would even be interesting, even in that space, when you guys, like your group and CMU and like Kiros Kukalatos, you're developing kind of emerging imaging. But if you had the overarching philosophy of, well, let's develop these emerging imaging and always keep metadata to have this sort of processing chain. I think the problem is the ISP world didn't do that. And now it's really hard, even though they could have, they didn't. And now you're trying to go back and push this on them. And the hardware is just not designed for it. They don't have the right tap in, tap out points. That information just disappears. The inertia of what's already been done is really hard to break. But you're this sort of nascent, it's just, so it's your burden to ensure these future, really interesting sensors do this.
Right. I mean, I was also thinking about this from the point of view of, let's say, image forensics, where
for sure,
there's this notion of, the trustworthy camera.
Yeah, I totally agree.
Back in the day, people said that, right, any image which has been tampered with is just a no-go.
Yeah.
But I'm assuming whether there is certain sets of image processing operations which are okay. Is there almost a dichotomy there?
Yeah, so we're working on that. Yeah, that's a really interesting topic. And I think even Adobe has like a whole working group on that. But yeah, you're absolutely right. What is it now with all this AI, what's authentic, what's not authentic? I think we all know deep fakes and some of the deep fake stuff with Dolly, it's just, you just don't know anymore, right? And so having some type of forensics, and forensics traditionally are, you look at the sort of fixed pattern noise. I mean, there's all these tricks you can do. You can look at how it does its compression, out of Berkeley. There's all these really nice papers, but what about be more upfront about it? Like at capture time, we kind of have, we mark the image of what's reliable, what's not reliable. I think that's a really interesting area too. And it's going to have to come, right? We're all going to have to recognize or reckon with this, especially the one that gets me is image super resolution. So when you do a digital zoom now, the digital zoom is almost always AI-based digital zoom. And if it has a GAN and it reconstructs something that shouldn't be there, that's a very serious issue.
Yep. Good. Thank you. Thank you very much.
Yeah, thanks.
Good. Maybe it's time to move to Mohit's talk.
Move to Mohit.
Okay, thanks, Michael.
Yeah, thanks for all the questions. Thanks for having me.
Okay, let me share my screen to introduce Mohit. Okay, this is the final keynote of today. So the title of the keynote is Computer Vision, One Photon at a Time. So Dr. Gupta is Associate Professor of Computer Science at University of Wisconsin Medicine. Before joining medicine, he was a research scientist at Columbia University. He received a PhD from Robotics Institute, CMU, and he directs the Vision Lab with research interest body in computer vision and computational imaging. And his paper on single photon 3D imaging received the Madras Best Paper Honorable Mention at ECCV 2019. So Mohit, I'll pass the floor to you.
Great, thank you. So I'm going to share my screen. Okay. Can you see my screen okay now?
Yes, okay.
Yeah, okay, great. Thank you very much for the introduction and the invitation. I am going to talk a lot about computer vision, where we look at visual data, where we look at images, and then we design algorithms that can extract useful information from these images. Now, we know that to an algorithm, of course, an image is just an array of numbers, and each number here represents a pixel. For the longest time, we have thought of pixels as a unit of visual information. Right? When we design cameras, when we design algorithms, a pixel is almost always the unit of visual information. But if you look closely into a pixel, we can think of it as a bucket that collects photons. And in a conventional camera, a pixel usually needs to collect tens, hundreds, or even thousands of photons to make a reasonable image. But now we have this emerging breed of cameras called single photon cameras, and SPADs is one specific technology there, where you can think of each pixel as a much smaller bucket. It's almost a teaspoon that can hold only one photon at a time. But it can detect the arrival of that one photon very precisely, which makes it extremely sensitive in low light. And because of this low light sensitivity, these cameras are starting to become very popular in many scientific imaging scenarios, where this kind of sensitivity and timing resolution are really critical. I'm thinking about microscopy, astronomy, even now in more mainstream computer vision, going in many LiDAR systems. These sensors are starting to become the real workhorse. So that's happening, where these sensors are starting to make a mark in scientific imaging. And the interesting thing is that up until a few years ago, these sensors were available only as a single pixel or as a small array, maybe 32 cross 32 pixels, which was sufficient for many of these scientific applications. But in the last few years, something remarkable has happened. We have almost witnessed a single photon revolution, resulting in really large format SPAD arrays, reaching up to 3 megapixel sensors last year by Canon, with promises of even larger arrays in the near future. So that's been, for me at least, when I started working with these about 5 to 7 years ago, we only had one pixel. And now we already have 3 megapixels. So for any new sensing technology, this is a remarkable pace of progress. So there is a resolution, of course, but now these sensors can operate at room temperatures. And perhaps most importantly, their fabrication is compatible with regular CMOS sensors. So at scale, this tells us that we can make these at low costs and small sizes. So because of all these factors, I believe that this is the right timing to start exploring the potential of these sensors, not just for scientific imaging, but perhaps more broadly for computer vision, machine vision, robotics, and maybe at some point even for consumer photography, where they can potentially have a more direct and immediate impact on our daily lives. So the technical goal here that we are really interested in is to design computer vision algorithms that consider photons as a unit of visual information. Because if we can design such algorithms that operate one photon at a time, then they will have access to this extra dimension of information along the time axis that conventional cameras just don't have. And this can be quite powerful, as I would like to show later in a bit. So let's see how to capture a photograph with a single photon camera, right? Let's say we have this array of sparse pixels. And for now, let's look at just a single pixel. Now, if this were a conventional pixel, this would work as a bucket to collect incident photons. Now we know that the arrival of photons is a random process, right? It's given by Poisson statistics. So, for example, if the mean arrival rate of photons, in this case, let's say is 3 photons per exposure, then the pixel may see 3 photons, it may see 6, or it may be even 0. So there is this inherent randomness that we call short noise or photon noise, right? Now let's do the same thing with a sparse pixel now. But remember that a sparse pixel works as a teaspoon, so it can collect at most 1 photon per exposure. So when there is more than 1 photon, the pixel still records a 1, right? And when there is no photon, the pixel records a 0. So in summary here, this single photon pixel measurement can be considered a binary random variable. It's actually a Bernoulli variable. We can easily write the probabilities of these measurements being 0 or 1s, right? They're given by these expressions here, these exponential expressions. And the important thing to note here is that the larger the value of phi, which is the incident pixel brightness or the flux, higher the probability of the measurement being a 1, right? Which makes sense. The brighter a scene point is, the more likely is the pixel going to be 1, right? It's a pretty simple equation, actually. And here's an example image as if taken by a single photon camera. The image is binary as we expect. We're calling it a quanta image because it is just heavily quantized. It's a 1-bit image. Now the image is also very noisy, but the key thing to remember here is that SPADs directly record arrival of individual photons. And this is a discrete event. So there is no analog to digital conversion. There is no ADC, which means that there is no read noise here. All the noise here is due to randomness of photon arrival, which in some sense is a fundamental limit of capture of light, right? There is a dark count here as well. But again, the important thing is that we are not paying this read noise penalty every time we capture this 1-bit image. So here is a sequence of these binary images captured over time, let's say, for the same scene. So there is randomness here, of course, but statistically, we know that a dark pixel will be 0 more frequently and a bright pixel will be 1 more frequently, right? So this tells us that if we want to recover a normal intensity image, one way to do this is to simply add these binary frames together and just count the number of ones at each pixel over time, right? So higher the count, brighter the pixel intensity. At least that's the intuition. There's a more formal mathematical expression here, which I'll talk about later. But again, intuitively, this is what the process looks like. So here is a single binary frame. We can get a better image by adding 10 frames. And as we add more, both quantization and noise decreases. And we can keep going. The final image quality will only be limited by photon noise or short noise, right? Again, which I said, in some sense, that's the fundamental limit. Unless we use some strong priors, we cannot do much better than that, right? So then a natural question here is, why don't we just keep going? What stops us from taking extremely long sequences for every scene? And you can imagine that really the answer is motion, right? Whenever there is motion, a pixel is not looking at the same scene point during this sequence, meaning photons that come from a single scene point, they get distributed over multiple pixels. And of course, this creates motion blur. So obviously we get this trade-off between noise and blur even here. Taking a shorter sequence gives us a noisy image, but longer sequences result in more blur. And this trade-off is not specific to this imaging modality. This is one of the most fundamental trade-offs in any kind of imaging, including conventional cameras. So the question really here was, is there a way to overcome, and maybe overcome is too strong a word, but maybe mitigate this trade-off? So the problem here is that if we just do a naive averaging of this long binary sequence over time, we get this blurred image. But if you can somehow measure and compensate for motion between these frames, then maybe there is hope that we can recover a high quality image with both low noise and low motion blur. So this really is a high-level idea behind a method that we developed a couple of years ago. We called it quanta burst photography, where we use a sparse array to capture a burst of these quanta images. But now the important thing to note here is that this burst can be captured at extremely high speed, going up to about 100,000 FPS. And then we develop algorithms to compute and compensate the motion between these images. And then, if everything works the way we expect, we can finally merge them into a single high quality image with low blur, low noise, and high dynamic range. I'll get to the high dynamic range part a little bit later in the talk, right? But at least this trade-off between blur and noise should be quite apparent here. We are, in a software-defined way, increasing the exposure time while avoiding the blur penalty. And I have to say that our work is heavily inspired by recent success of burst photography with conventional cameras. When Mark Levi, when he was at Google, he and his team did some pretty amazing work over the past few years, where these burst photography methods are now robust enough that they are being routinely shipped on consumer cameras, which, in my opinion, really is a gold standard for computational photography and imaging. So it's been quite inspiring for us. So in conventional burst photography, we usually take about 5, 10, 15 intensity images. Now, the main difference in quanta burst photography is that we capture a series of these quanta images. Now, individually, each image is only binary and looks quite noisy. But again, the key thing is that these can be captured at very high speeds, which means that given the same time budget, we can capture thousands of these, which in turn means that we can do very fine-grained motion estimation and compensation, again, almost at the granularity of individual photons. And that allows us to deal with very high-speed motion and deal with some extreme low light scenarios. And again, as I will say, it also gives us a huge dynamic range, right? So I probably don't want to go into too much algorithm details, but again, if you have questions, I'll be happy to take them offline or point you to the paper. But essentially what we're doing is computing motion from these binary images. And then once we have computed the motion, then we are compensating for the motion, doing alignment, and then putting things together. But next, I just want to, again, there are many more details, but I would encourage you to either talk with me or look at the paper. But I would like to show some quick results. So here is our sparse array that we used. the resolution here is about 512 by 256, so a little lower than VGA right now. But as I said, the resolutions of these things has dramatically improved, and now we have access to more than a megapixel easily. Also, the setup right now, of course, looks bulky because this was a really research-grade prototype. But as some of you may know, these SPAD arrays are now being shipped in consumer devices like iPhones. So there is a clear path to miniaturization and commoditization, right? So here is an example, real sequence of these quanta images. So as you can see here, there is these almost these white dots. Each dot here means a single photon detection. And just to make the case, here we had a scene which was very dark. So what we had was only 0.03 photons per pixel per binary frame. So again, if you look at a maybe patch of about 5 cross 5 pixels, on an average, we had only 1 photon detection per patch, right? So just looking at this, of course, it's difficult to see what the scene is, what kinds of objects there are, because we have this very sparse sequence of photons. And if we take a really long sequence and simply add them together, we get something like this. We get the strong motion blur as we expect. But if we are able to align these images now, we can recover something like this. Now, again, clearly this is not photographic quality, but I wanted to kind of point again to the level of light that we have. It's again 0.03 photons per pixel per frame with pretty aggressive motion. So for me, it was actually remarkable that we started with each pixel getting about only 50 photons over the entire sequence, and there is strong motion. So pretty extreme scenario, but we are able to recover something like this. And again, so far we haven't done any learning on this. So I'm sure that, as Michael was pointing out, we should be able to improve image quality with more modern machine learning based denoising methods. But here really just to convey what is possible with these kinds of sensors. Now, one interesting side effect that is that we can now perform super resolution using the computed motion fields. And the high level idea is that because now we have this really dense sampling in time, the motion between individual frames is highly subpixel, which means that it is possible to warp all the pixel samples from different frames to a common super resolved pixel grid. Right? And then we can estimate the pixel values at the new grid by things like diffusion, kernels, etc., by combining neighboring samples using some kernel function. So here is another example scene. Again, this is a sequence of these binary images captured over time. The scene was a little bit this was a challenging scene because we had complex geometry, strong depth edges, discontinuities. So if we do this naively, we are able to remove the motion blur. But if we put in the super resolution, we get more details on the right. We have sharper edges and fewer aliasing artifacts. And again, this super resolution is something that we get just because we are doing dense sampling in time, not by using any machine learning based method as yet, right? We can, of course, maybe put those things on top of what we are doing right now and perhaps go further. Right? So right now, at least we're making kind of minimal assumptions on the kinds of motions. The motion could be either global camera motion, could be local object motion, even non-rigid scene motion. So as an example of Sergio is my student who actually did all the work here. He was playing the guitar. And again, with simple averaging, we have to deal with this trade-off between motion artifacts and noise. So we either get blur or noise. But with the right alignment, it was possible to recover a clear, sharp image here. we could in fact resolve individual guitar strings despite there being a fairly rapid motion here. And from here, it's not hard to imagine that you can extend this to recover a video as well instead of individual images. And one way to do this is really to simply, apply this image reconstruction process repeatedly over time. This is probably not the most efficient way of doing things, but just a proof of concept for now, that we can now recover video of these relatively complex scene motions using these single photon cameras. Okay. All right, so I'm going to switch gears a little bit. And so far we have talked about a lot of, we have talked about being able to recover images and videos, where really the goal was to create this visual data at the end with a human as the end consumer in mind, right? The goal was to do reconstruction. But now what you started thinking about is, can we go beyond just photography and start thinking about these sensors for some computer vision tasks, starting from something low level, maybe like 3D imaging, maybe going up to mid level, like tracking, mapping, SLAM, but perhaps even high level, where can we start doing things like detection, recognition, really high level semantic computer vision tasks on these photon streams, right? Because again, our thinking is that if we can not limit ourselves just to reconstruct images, but to be able to extract some meaningful information as well, then that could open some interesting opportunities for doing computer vision in challenging scenarios, right? So let's go back to a single quanta frame. As we said earlier here, this is a 1-bit image where each measurement is a Bernoulli or a binary random variable. So this was an image taken in a dark scene. It was actually my garage at night, and we purposefully switched off almost all the lighting. And as you can notice, there is not that much information here, right? It's difficult, if not impossible, to figure out what the scene is, what kind of objects there are, what's really going on here. And again, that's not very surprising. We only have a few photons over the entire image now, so not that much information. So one thing we can do is, of course, just to capture more photons. And again, this is what we're doing here. We are progressively accumulating more and more quanta frames. And as we said earlier, as we add more frames, two things happen. We do start getting more signal, so less noise and quantization, but the things that are moving start getting blurred, right? Which makes it difficult to recognize them. So here what we did was we ran an object detection algorithm, it was YOLO, on all these intermediate images. And interestingly, the detector did not return anything because the images were either too noisy or too blurred. Now I wanted to clarify that we did not retrain the detector. We used it as it is off the shelf because we just wanted to see, how would this work on these kinds of reconstructed images? What happens then? So again, not very surprising, but just interesting that in all of these intermediate images, there is either too much noise or too much blur. So this told us that it is, if you really want to design computer vision algorithms that work on these photon streams, then we have to be able to combine information from a sequence of these binary images while, and this is very important, while accounting for motion information, right? Clearly, one image is not enough. So we have to take a lot of images, but we have to somehow account for motion information across those. So we're calling these algorithms quanta burst vision now, because the goal here is to do computer vision, and burst because they operate on these bursts of quanta images. Now, broadly, there are two ways of doing this. We can either combine information from multiple images explicitly by first creating an enhanced image using the burst photography techniques that I just talked about. And then, of course, once we have a high quality image, then we can really almost use downstream learning algorithms as in a plug and play manner. So that's one way of doing it, really just explicitly. And then in this two-step way, the other approach is like an implicit end-to-end method where we pool information across this sequence, this binary image sequence, in an end-to-end manner, right? Where we directly maybe train some machine learning algorithms, let's say deep learning algorithms, that go directly from these sequences to the downstream task, right? So again, broadly, these two categories of methods, explicit and implicit, two-step versus end-to-end. For now, I'm just going to show results, really preliminary results using this first two-step approach. This is maybe not optimal in the long run from computational and maybe also from accuracy standpoint. But again, perhaps just enough to provide a proof of concept right now, just to demonstrate what's possible with these kinds of sensors. Right. So now what we're going to do is, I'm going to show a result where we do the same thing as before, where we are going to add more and more frames. But now, as we accumulate more frames, we're going to compensate for motion. And now what you see is what's happening is we are almost kind of freezing these photons in place so that after a certain amount of frames, we start getting enough signal that this object detection method, YOLO, it starts firing even without any retraining. Right. Now, again, with retraining, of course, the performance can improve. But at least in certain scenarios, what's possible with off-the-shelf techniques is also kind of valuable. Right. So here we can see that, again, when we start with one frame, there is not much here. But as soon as you get to about 200, 500 frames, because of the motion compensation, we start getting enough signal here. Right. So this was just one example, but we recently, we captured binary sequences for several different downstream tasks, which cover a wide range of lighting conditions, scene camera motions at various speeds in both indoor and outdoor environments. And really the goal here is to make the cameras are close enough to being ready for deployment in many computer vision tasks in real world applications, right? I mean, there is still a lot that needs to be done there. It's not yet ready, but we're getting really close. So we looked at many different applications, from object detection, face detection to outdoor driving applications like SLAM camera tracking, etc. Also, we looked at some low-level tasks. In many applications, we want to recover these low-level details, which are embedded in high-frequency spatial details. For example, here we are showing a scenario where there is a fast-moving QR code in a really dark environment. And with simple, naive averaging, we get this image which is either, again, too noisy or too blurred. But this burst vision method, it does give us a clear image where the QR code is correctly detected. And again, I wanted to point out that this was a pretty challenging scenario. I think the lighting level here was about 0.1 lux, and the scene was moving at really high speeds. So in a way, kind of the worst of both, low, strong noise and high-speed motion. Here's another scenario where we are doing text detection and recognition again. Burst vision gives a sharp image, which is amenable for downstream text detection, right? So far, I have tried to make the case that this quanta burst vision enables various computer vision tasks in the dark. But a natural question at this point is, how do these SPADs compare to other low light sensors? So here what we did was we captured synchronized object tracking sequences from 3 different cameras. There is this Sony night vision camera, which is designed to work in low light because of low read noise, etc. And then it does capture a reasonable image, but it does still suffer from motion blur. And because of this, object tracking kind of fails after a bit. Then there are all these thermal cameras, and they actually give a remarkably sharp image. But the challenge is that they don't capture all the visual features in the visible light spectrum, right? So because of that, again, although they can track thermal objects like the face, but some non-thermal objects like the ball here, they lose tracking. But with the SPAD, because again, we maintain high image quality, we do maintain robust tracking of the ball. And again, sometimes, looking at these images, it's hard to appreciate how challenging the sequence is, because we have done a lot of contrast stretching and tone mapping. But this was an indoor setting where almost all the lights were turned off, except for an exit sign in the auditorium, right? So this was pretty dark. Now, one thing I wanted to emphasize was that this is not meant to be a direct comparison between these different camera technologies. As you know, they have different sensor sizes, they have different exposure times and optics. But the only thing that I want to show here is that these are really challenging imaging conditions where many existing state-of-the-art imaging technologies struggle quite a bit. But SPADs, at least in the long run, may provide a potential solution. So, we also took this outdoors. So we put the SPAD camera on a dashboard of a car, which is driving on a street without any street lights. And here you can see that the SPAD was able to detect the pedestrian from a longer distance than the night vision camera, even beyond the reach of headlights. Right. And once more, this is an important capability to have, to be able to detect pedestrians and obstacles as early as possible. So here again, we can see that we detect in the top, detect the person here. Here's another sequence, another example where we ran SLAM to detect the trajectory of the car now. It's kind of interesting. I hope Zoom is doing justice to these videos. With a night vision camera, it's a reasonable image, but there is just not enough resolution here and not enough contrast. So with the night vision camera, it fails to initialize. We don't get any tracking or mapping. But with SPAD, yeah, we are able to get a reasonable result here. We are able to get we are able to track these features and able to get these features and track the camera and track the motion of the car. Right. And again, so this was an example where we are driving on a street without any headlights in the night, to the point that driving was actually quite challenging here. Right. But yeah. So I've so far been talking about reliable, high quality photography and reliable computer vision in the dark when cameras don't have enough light. But one question that we recently started to ask was, can SPADs work not just in ultra low light, which is photon starved domains, but also when they are photon flooded, when there's too many photons? And this is important, especially for computer vision systems, because for many real-world applications, these need to work not just in dark, but in all kinds of lighting conditions, right? So to answer this question, we wanted to take a closer look at the timeline of photon detection with SPADs, right? So we're going to assume that there is this entire exposure time that each SPAD pixel has, which is divided into these fixed time slots for each binary frame, right? So as an example, let's say we give a time budget of about 30 milliseconds to a SPAD pixel. Now that 30 millisecond time, we can further divide into these smaller chunks, each of which is enough to capture a binary frame, right? Because remember, binary frame capture was done at high speeds. So the setup here is that there is a SPAD camera again, which is passively observing a scene. And we're going to use this small dot to represent an incident photon. Now remember that a SPAD can record only one photon during each frame. So if there is another photon that comes in, it's not going to be detected. It will be missed. So now what we're going to do is add another timeline here, but now this one shows only the detected photons, right? So here, this is the detected photon, because SPADs, again, they can only record the first photon in each binary frame. Everything that follows is missed. What we can do is actually plot the number of detected photons on the y-axis versus the number of incident photons on the x-axis. Now, when the number of, when we're looking at a dark scene and there's not that many photons coming in, it's quite unlikely that two photons are going to hit the sensor within the same frame, right? So in this case, almost all the photons are counted, right? For now, just for discussion's sake, we are assuming that the sensor has perfect quantum efficiency. So we're not losing any photons due to low fill factor or imperfections in the material, etc., right? So at least in this low flux regime, we can expect this plot to be linear because really we're detecting every photon. But now, as we start increasing the photon flux, some photons start getting missed, right? So this curve starts becoming curved, actually. It's no longer a linear curve. And when there are even more incident photons, even more of these are missed. And the net result is that this curve, it actually starts to flatten. And then eventually, at extremely high flux, the SPAD is going to miss a large fraction of incident photons, which means that this curve will continue to approach the maximum number of counts in an asymptotic way. And this maximum limit is really just the total number of binary frames that we have in the total exposure time, right? But the key observation here is that statistically, this curve will never reach that maximum, meaning it will not really saturate even for extremely bright scenes. And we can actually represent this curve with this exponential expression here. Now, the interesting observation was that although this curve is non-linear, it is still monotonic, which means we can invert this, right? Meaning once we know the number of detected photons, once we have the photon count, we can invert this to get the number of incident photons, which is nothing but the linear intensity estimate that you may expect from a raw image captured by, let's say, a cell phone or a DSLR camera, right? So just to put this in context, for a conventional sensor, which operate in this bucket kind of mode, the curve is linear at first because the bucket fills up. But then after the bucket has filled up, this pixel has saturated. And clearly after saturation, it's non-invertible, right? So this linear and then this linear response curve with conventional cameras is what limits the dynamic range. But somewhat counterintuitively, at least it was to us at first, this non-linear response curve tells us that SPADs can work not just in low light, but can actually outperform conventional sensors in bright light scenarios as well, which gives them a huge dynamic range, right? So here is an example scene that we set up to demonstrate this. So this is trying to emulate a tunnel kind of a scene. And imagine you're driving in a tunnel and the tunnel is dark, but the outside is extreme bright. So with a conventional camera, what you can expect is if you take a long exposure, you're going to be able to see inside, but the outside is completely washed out. With a short exposure, inside now is completely noisy. You don't see any details here, but you can see outside. But with a SPAD, with a single exposure now, we're not doing any exposure bracketing or anything. with a single exposure, you can simultaneously see both inside and outside. Right? And I think in this scene, the dynamic range was about 1 to a million, which is, as we know, way beyond what conventional CMOS sensors can capture in a single exposure at least. And 1 to a million is actually getting close to what the human eye can measure. So this was kind of interesting to us, this high dynamic range capability, along with the low light and high speed performance. So here is another example. So here what we are showing is the ability to track a person as this person is going to start walking from a dark room and then transitioning to a brighter room and then finally outdoors. So across this entire sequence, the dynamic range is going to vary dramatically. And just to demonstrate that this person is carrying a light meter, and we're also capturing the image of the light meter, right? The light meter reading. And in the beginning, it is way too dark, so we don't see the reading here. But it was about 0.1 lux to start with. And I'm going to play the sequence now. So now, it gets slightly brighter. So we are about 2 to 3 lux, now 10 lux. But the thing is that throughout this sequence, we maintain tracking. So now we are transitioning to outdoors. And eventually the light level is going to go up to about 50,000 lux, starting from about 0.1. Now, the one thing to note here is that the exposure time and the aperture of the camera was kept constant throughout the sequence, which again means that we should be able to adapt to an even wider range of lighting conditions if needed, if things like auto exposure and auto aperture are implemented here. Just very quickly, so far almost all the results that I have shown, you may have noticed that they're all monochrome, because till very recently we did not have access to color on SPADs, but this is something which is also changing now. We did recently fabricate a color SPAD array, and this is an image of the sensor chip itself. So you can see these red, green, and blue filters. And we just thought that color is so important. Of course, Michael talked a lot about the importance of color. And we just thought that for these things to make a real practical impact, they need to have color, right? So what we have now started doing is thinking about how to do things like demosaicing on these photon streams. Because now each photon detection also kind of carries a color signature. So it actually becomes a very interesting problem on how do you do things like motion estimation, denoising, and demosaicing on these photon streams. Again, in the interest of time, I'm not going to go into details, but I would just say that this all these algorithms which have been kind of designed for conventional cameras, and they are kind of well understood now. To adapt them to this photon stream settings, it's a really interesting and challenging research problem. So it's been kind of very interesting to look at this in this domain. But very quickly, I want to show some results. So this is purely simulation first. So here is what you would capture maybe with a conventional camera, single shot. So of course, you see a lot of motion blur. Now, you can also do burst photography with a conventional camera. And of course, you get much better results because now you can resolve the motion and everything. But you're kind of limited by the dynamic range of what you can capture in a single shot with a regular CMOS camera. So here, for example, there is some text here, which is lost right now. And there's still some residual motion blur. And this is what we get with, again, same total capture time and everything with a single photon camera. So this was purely a simulation result where we simulated the forward simulated the camera parameters of a SPAD versus the parameters of a state-of-the-art conventional CMOS camera with a read noise, fill factor, and things like that. But now here you can see, you can read the text here. Actually, I think this is Japanese, so I cannot read this text. But if anybody here who can read Japanese, they can probably read the text here. So this is very preliminary, but this is this work is not yet published, but this is some real results now that we have with the color SPAD array that we have recently gotten fabricated. So again, we see this familiar trade-off between noise and blur if we do simple naive averaging, but if we do the right burst processing, we can get reasonable quality image, even when there was even in low light and rapid motion. So yeah, I'm just getting close to the end. So far, I've shown some I would say really preliminary results, because these things are still largely research grade, although that is rapidly changing. At the beginning, I talked about making an impact in real world applications, but to really get there, these single photon vision and photography algorithms will have to deal with this deluge of photon data. Because one thing is, because you're capturing every photon, these devices are really data and memory and power hungry. So they're really expensive right now in terms of memory, compute, and bandwidth. So this, I believe, is a key, if not the most important technical challenge, and really the next frontier in single photon computer vision, which is how to design quantum vision algorithms that can keep up with this photon stream under limited compute, memory, and bandwidth constraints, while preserving the rich source of information that these photons carry. And this is going to be extremely important, especially if these ever are to be deployed in power-constrained devices like cell phones, etc., right? Where every watt is at a premium. So we really need to think very carefully about how best to perform what we call almost these photon processing algorithms while respecting the memory, power, and compute constraints. But the encouraging thing here is that these cameras, these single photon cameras, are starting to become mainstream, as I mentioned earlier, and surprisingly fast, actually. And many of these are still research-grade devices, but now, in at least some commercial devices, even some consumer devices like the new iPhone and iPad, we are starting to get these SPAD arrays, which is quite exciting. Yeah, we often talk about timing in research. I think this may actually be a very good time to start thinking about the exciting capabilities of these cameras. There is huge opportunities in terms of research, but also potential real-world practical impact. And with that, I would like to finish. Thank you very much for listening. I'll be happy to answer any questions. Thank you.
Thanks, Mohit, for the talk. It's really nice to know the various interesting properties of SPEC sensors, and especially the large dynamic range. This is quite a surprise to me. And we are waiting for questions from the floor. Yeah, actually, I wanted to ask about the power consumption of SPEC, but you already mentioned it. This is a limitation because it comes with a lot of data and need to transfer and store it.
Exactly. I mean, the very interesting property of SPADs actually is that the power consumption is proportional to the brightness of the scene. Because for every photon that you detect, you pay a price for that photon, because you need to recharge your pixel after that photon has been detected. So it's very weird, right? I mean, you are in a low light setting. You're not paying too much power price, but as you start getting more and more photons, this starts becoming more and more power hungry. And of course, there is a power cost of reading off all this data and doing all these computations. So right now, not very practical, especially on a, as I said, a power constrained battery powered device. But this is something we have to deal with.
I have a couple of questions.
Yeah, Michael, please continue. Yeah,
yeah, great.
Michael, yeah.
Yeah, so yeah, great talk, Mahit. It's really, really fascinating to see. I think I think when SPADs first came out, they're quite amazing, but it was just kind of the limited resolution. It made you scratch your head, but now it's pretty amazing to see that they're kind of packing these things already at VGA level. I have a couple of questions on the first, let me just ask about the WACV one, because on the WACV slide, you showed kind of two strategies. One was the sort of, you kind of ran it through the sort of burst vision or burst quanta, and then you did the, but did you try the implicit burst one? I didn't quite catch if you showed you could do that too. So, I guess you could also just train the network where you just give it the stack and see what it can do. Did you, I couldn't tell the results for the explicit burst vision, right, that you were showing?
Yeah, so all the results that I showed were with the explicit burst vision.
Okay.
We have tried the implicit thing in a limited capacity right now.
Okay.
But we did not include those results in the paper.
I see. But it seems like that should, it does seem like that should work too, right? That's a pretty interesting strategy to go. Just your training data is quite different and you could probably simulate it, but to get the real data on the camera and label it takes time, right? Yeah.
I totally agree with you that in the long run, that is the way to go.
Yeah.
This is really, this explicit two-step thing is just a stopgap for now.
Right.
The key challenge right now is just the training data, because training labeled data.
Yeah.
Even if you were to simulate these sequences from high-speed cameras, you need high-speed labeled sequences that go up to 10,000, 100,000 FPS.
Yeah, no, I totally understand. Yeah, but I didn't quite catch it in the talk. Yeah, and then the other one, I really like the SIGGRAPH paper, the 2000. Just a couple of questions about the results. So I noticed that when you showed the average with the motion blur without any motion compensation, in the early work, so you can see the dust on the lens.
Yes.
But then when you actually show your reconstructed result, you don't have any dust anymore. I was a little bit surprised about that. But I guess it makes sense that it's pretty easy for you. If you know where the dust is, it's pretty easy for you to ignore it because you have multiple views.
That's right. That's right.
You did, but that's a extra little trick that you have to put in. Okay. I just want to make sure. Good.
That's right.
But then, but then show the guitar on the video. The guitar on the video is really interesting because when you locked it, when you go to the video and you fuse it to a frame, notice the inner reflection on the guitar is moving. So you got these, I assume that's what it is. That's sort of the reflection of the guitar. Because if, that guitar is very specular, it's got a shellac glaze. So I just find that really fascinating that you freeze it to a fixed frame so we can see because presumably the camera is moving. So you got the ego motion of the camera, but you want to see the vibration, but then the reflection moves. So now the ego motions push the reflection. And so I could definitely see a reflection removal algorithm like for free here,
That's right. That's right. I think, for me, the interesting thing is because you're getting this dense time sampling, and if the camera is moving, then the dense time sampling translates into dense angular sampling. So in a way, what you're getting access to is really dense light field data also.
Light field, exactly. Yeah, that's pretty.
This is extremely dense light field, which, I'm imagining something like if you train a nerve on something like this, just automatically, you may be able to deal with the specular BRDAs.
Yeah, that's pretty interesting. It's all contingent on how good your motion estimation is, right?
That's exactly right. So that's really the heart of it.
Yeah, but I think when you mentioned Sam's paper, Hassanoff's paper, that's what Google did well. They invested the time to get really solid. That paper you mentioned, 2016 paper, I think, from Sam, 15, is not a deep learning paper. The paper is really about how do you do robust motion estimation in this really low light scenario. It's a really great paper. And I think Google invested the time to get that. And now you see all this great stuff like Peyman's group and everything, because they have really good motion estimation. Like they can just leverage that over and over.
Yeah, I mean, right. I mean, the remarkable thing here is that, we often talk about, algorithms that are maybe research grade, but they really made it work.
Yeah, no, that's, we re-implemented that paper in our lab. I mean, it works. Like you just follow the procedure. Sam lays it out very nice. Yeah, we got it to work on a lot of hard scenarios. It's got very robust, it's robust as a bilateral filter behind it. I sorry for hogging all the question time, but I have one more question on your the dynamic range.
Yeah.
One thing I get the basic idea that this thing doesn't saturate out, but I didn't quite understand how you invert, because so go to the graph here, because in your case, maybe I'm missing something here, but because this was a single frame, right? It's a single exposure time under your SPAD, so it's still just a binary image. Is that correct? Like how can I run the binary image back to this curve? I only have 0, 1. So are you looking at like some neighborhood information to somehow figure out? Like I just don't. I get this part, and I understand like this thing will never truly saturate out, but I don't quite grasp how you take the quanta image and run it through this to kind of get those images you showed.
Oh, that's a great question, and I think this is probably because I rushed through this. I was not sure of the time.
Okay.
But so the model, the setting that we are considering is, let's say you have a pixel and you give it a certain measurement time budget.
Okay.
Let's say you give it maybe 30 milliseconds. Now, within this 30 milliseconds, you are able to capture a lot of binary frames because you have high speed capture. So let's say you're able to capture 1,000 binary frames. And this is what I'm trying to show here with this timeline. Each individual measurement, you're absolutely right, is binary. But ultimately what you're doing is you're capturing about 1,000 frames, let's say, and then counting the number of ones in that 1,000 frame duration.
Oh, now I understand. Okay.
Right, and now because of that you get this curve. So that's why here the limit here is the number of binary frames.
I see. And for you, that's an exposure time. That's your
budget.
Exposure time. I see. No, I got it.
Right. So there's 2 different exposure times here. One is the macro scale exposure time.
Yeah.
And then there is the binary scale exposure.
Yeah, I guess Kiros showed on their kind of multi-bucket camera, and I don't remember if you guys were on some of that. I know some of that was with CMU, but anyway, they were doing some similar tricks where he was kind of pushing, even though it wasn't really a SPAD, the fact that he could multiplex the time, he could also kind of absorb these. He could do it in a way that he wouldn't saturate out. I just thought that was really interesting. This is really this sort of having a sensor that doesn't saturate out is huge, right? It's just huge. Imagine you had these sensors that you didn't saturate.
Yeah,
it's just amazing, right? You could really all these applications that open up because we don't saturate out. It's really, really amazing.
And actually the interesting thing here is right now we are looking at these photon counts, but with these SPADs, what happens is for each photon that you get, you can also measure the time of its arrival, which is useful in many LiDAR applications. But the cool thing is actually you can use the timing information in a purely passive setting too, in that you can look at the time delay between 2 successive photons as a measure of image brightness.
Yeah, for sure.
And that actually, we can show that that measure doesn't saturate at all. That even if something is infinitely bright, there will still be certain time delay between 2 successive photons.
Yeah.
Because
you
can measure that.
You just phrase everything in the Poisson regime and you just figure out what's happening here, right? Yeah.
Right.
Very cool. Very nice work. Really like it.
Yep. Thank you. Thank you, Michael. So were there other questions on the chat? Because I don't think I can see the chat.
No. Yeah. No questions from the chat.
Okay.
So, all right, then perhaps we can end the session here.
Thank you very much.
And Yeah, thanks Mohit for the very insightful talk. And thanks to Michael as well, who came early to give us the keynote. And thanks to Peyman and Tomo who gave the keynote in the earlier session. So this is the first workshop for MIPI. So we hope we can have the second, third one, and in person, not the virtual one. Yeah. So, and we're trying to propose a new one for the next conference. And yeah, that's it. So thanks to all participants who joined us today, and then congrats again to all the challenge winners. And then we call for an end to the workshop. And have a nice day, guys.
Thank you very much.
Thanks
Thank you.
for organizing. Yeah, bye-bye. Bye, everyone.
Bye-bye.